I'm Craig Clements. I'm director of the Fire Weather Research Laboratory here at San Jose State, and I'm going to kind of open up the session or the workshop with kind of some background of kind of why we were doing this, some stuff about us, and then we'll get into more of the formal presentations. This is funded by the National Science Foundation, and so we wrote a proposal to study the 2017 wine country fires, and with that proposal, we submitted part of the grant as we're going to host a workshop for fire management, the community, and other scientists to come and actually learn about what we've discovered in our research. But that seemed very limited, so I wanted to kind of open it up to a more broader context in terms of fire weather research. And so that's why we have, I think, a very exciting agenda with our excellent research community presenting different universities and different companies and agencies. So I'm really excited that everybody came. And as you know, there was a wait list. And it turns out that we probably have plenty of room. So if anybody didn't get here because they weren't on the wait list or couldn't get in, we're recording it. So this will be available online for future reference. And because of the overwhelming popularity, we kind of went over budget. So we had to go to the Department of Meteorology, my home department, and say, hey, can you sponsor the happy hour afterwards? And they said, yeah. So once we get through the afternoon, at 4:30, we're going to go over to the Department of Meteorology. We have the tallest building so far, or the best view of Silicon Valley, until they build the new science building, which will cover our view, but that's okay. And we're going to host a reception, beer and wine, okay? So can I get who wants to go to that at 4:30 to 5? There's some people raising their hands before I even said that, so. Okay, it looks like there will be some people there. Okay, great. We just need to get a head count. I didn't count, but I'm estimating it's half of the people here, so we'll figure it out. Okay, basically the goals of the workshop are to bring the state of science research to stakeholders and to the community. So there's a lot of different people here from different groups, from private firms to the utilities, fire safe councils, CAL FIRE, local fire districts, county fire, academia, and so it's a real nice mesh. And the National Weather Service, and there's a real nice, and U.S. Forest Service, and so we'll post a attendee list and the agencies later. So it's a real nice mesh of the community. I really wanted to focus on California fire weather phenomena, and so that's kind of how the list showed up, and some new technologies as well. And offer a forum for community engagement. So people that are not usually going to scientific conferences can come and get the same content, okay? And so we'll post some of these, we'll post the presentations online as well, okay? And just connect everybody. So that was kind of the goal. So I wanted to be sort of informal. I did wear a t-shirt. We are selling our t-shirts and hoodies, and there's a raffle. So if you got your raffle ticket, we're going to raffle a hat and a hoodie. So you get, and the hat is made by Sims. It's a fly fishing hat with our logo on it. So, and it's like the last one available. So anyways, you came for the hoodie or the hat. All right, a little SJSU history. SJSU is actually the oldest public university on the West Coast. It's the first public institution of higher education in the West Coast. The oldest public university in the state, obviously. The oldest university is Santa Clara University here in Santa Clara. It's the most densely populated campus because there's 33,000 students on 80 acres. Here's what it looked like before 1906. The earthquake destroyed this building with a fire. They built Tower Hall, which is still standing. So I'll go back. That's Tower Hall. That's 1910. That's this structure. Oh, I don't have my pointer here. That's this structure here. And then what's happening in about a year, or they just did groundbreaking yesterday, we're going to get a new science building. So that's going to be the state of the science. So the first new building on San Jose State campus. 33,000 students growing to 35 and 40. I think that's the goal. That's a big university for such a small campus. 31% are from traditionally underrepresented groups, and 45% are first-generation college students. So we have a great campus, great student body. And you'll meet some of our students in the fire weather lab. They might be wearing T-shirts. Taylor's running the desk out front, and so some of our students will be presenting as well. A little bit about the lab. I established it in 2007 when I arrived here as assistant professor. We believe, and it's really the only academic fire weather program in the nation. We teach courses in it, and that's our only focus, is really looking at fire weather phenomena and studying. Now, there are a few fire weather classes out there, but they're generally not in a meteorology program. And I bet that we will see more fire weather courses in meteorology curriculum in the next few years. So all the SDSU team members are Fireline qualified. We're sponsored by the Tahoe Forest, National Forest, so we maintain red card qualifications, and we're basically, I think, the only meteorological team in academia in ROS, which is the resource ordering system. A couple of projects we're doing. We also manage some fuel monitoring sites, live fuel moisture. The students like driving out twice a month, clipping fuels for everyone, and so they don't. That's why I said that joke. Nobody was like, really? Because it's like, I got class. Well, we got to clip at 12 o'clock. Another thing we're doing is we're setting out some dowels to represent 100-hour fuels to test it and see if we can sample the 100-hour fuels locally. That's what this array of sticks are. And we have an oven. You'll see the oven when we go over to the lab tonight. We manage a small network of weather stations. We work with Henrico State Park. Mount Diablo is our weather station. We have a new one on Mount Umanum. One is a raw station. The other are just data that we ingest here and goes up on Meso West. We also manage this truck, which is a mobile atmospheric profiling system. It's the only one in the world. It allows us to go and probe fires. And besides the one in Australia, which you'll hear about a little bit later from Nick McCarthy. Anyways, one thing that I was hoping to demonstrate today was our new wildfire and cloud observing system. It's a Ka-band weather radar, dual pole, means dual polarization. You'll hear a little bit about that later. We have a second truck that's been purchased. The radar was supposed to be here. We were supposed to be out here looking at it, but the radar didn't arrive yet because they had to fix something and the truck isn't ready. So we're in the process of having this vehicle and facility available for rapid response. It's the only mobile weather radar in the western U.S. It's besides like the news radars like Storm Ranger and such, but the only academic radar, and it's really gonna shed a lot of light on plume dynamics. Okay, we teach 3 classes. Wildfire Earth System, it's a GE class. Intro to Fire Weather, it's an upper division meteorological class I've been teaching for quite some time now. And then we have an advanced fire behavior class, which we haven't taught yet. I'm going to skip through this stuff and not really show you any of that because I want to get to kind of the program since we're right on time. So I just want to acknowledge the grants from NSF and the Department of Meteorology. They're funding this, and we're going to start our program. And feel free to get up and get some breakfast, and we have the doors open here. It should be nice. If it gets too hot, we can close them, and then we have our lunch, and then I'll announce when we go over to the lab. It's a tricky way to get up the stairs. We'll have some signage, and it's the only building with like 10 anemometers on the roof, so you can't miss it. So we'll show it to you. All right. Okay. Well. Let's our first speaker starting off is Leila Cavallo from the University of California, Santa Barbara, and we are going to bring her computer up. She's a professor of geography and manages the climate science program at UC Santa Barbara. Her expertise is in climate dynamics and sundowner windstorms, and so she'll be presenting on the climatology and dynamics of sundowners. So she's going to be our first speaker. Get you started here. Your HDMI is over here. Oh, let's see. Perfect. Okay, we're all set up.
All right. Okay. Now. Thank you. Thanks, everyone, for being here. To me, it's a great pleasure, an honor to be in this workshop. Thanks, Craig, for introducing and also for organizing this important workshop. I want to know here, who heard about sundowners? Yeah, big crowd, huh? That's nice. Okay, so before I start, I want to thank my collaborators, Charles, who is here, Gerjang, who is my postdoc, Caitlin, my graduate student, and Craig, who is also part of this project. Okay. All right. So I'm going to start. Let's see if this works. Just a second. All right. First, before I start, I need to talk about these mountains because I'm going to talk a lot about this in this talk. So the region of Santa Barbara area has this interesting mountain range, the San Ynez Mountains. As you can see, it has the east-west orientation, which is very different from other regions in the West Coast. Also, the San Rafael Mountains are very important, and here you see the San Ynez Valley. So all the valley, these two mountains make a very different and distinct climate in the region. So Santa Barbara is not new to fires. And you probably heard some of them, Thomas Fire, the Resucita Fire, and so many fires we had in this region. But one aspect that is common about all these fires is that they spread really fast towards where the population lives because of downslope windstorms we call sundowners. Sundowners are not Santa Ana winds. I will show you later some more evidence about that. And so here you can see some of the pictures we see very commonly, in especially recent years, and also the cost of just the cost of fighting these fires. Now we are having the mega fires in recent years, so you see how much we have been spending in fighting these fires. And some of these fires have even crossed the 101, which is an important exit in this region. So what are sundowners? Sundowners are these northerly downslope winds that tend to intensify after sunset. That's the name sundowners, especially after sunsets. And it can increase temperature and decrease relative humidity, becoming the most important weather condition in Santa Barbara, fire weather condition in Santa Barbara. And this is a problem, a multi-scale problem, because first of all, we need the synoptic forcing of these events. And we have seen that many settings are possible for these events. Here shows some examples. This is published in a few papers, but also Blyer has been some other examples that what is necessary to have sundowner is basically have in colors you see pressure, in lines are geopotential height. But what we need for sundowners is a strong pressure gradient forcing northerly winds in this region here in Santa Barbara. And you can have this year-round, actually. I'm going to show some of these additional settings. So you see, in the region where we are now, we have very few stations. And this is a problem because when you want to understand these winds in more detail, we don't have enough observations in this area. So this is why to study this mesoscale features, we have to rely on models. So this project that we have been working together is to improving understanding of sundowners. We got this grant from NSF, and we have developed, at this point, 30 years of climatology, 30 years of data at 1 kilometer resolution. This is ready. And thanks to Charles, who did all the work. And also, we did some validations. And if you are interested in the topic of modeling winds in a coastal environment, we have these publications where we discuss a lot about the validations in these winds. So here just showing the climatology. So you see in colors, these arrows are indicating wind direction, the mean winds in the region. During the daytime, so here are some of the cities in the area. This is Ventura, this is Santa Barbara area, Carpinteria. And then you can see this is March, May, and this is daytime. And then you can see the onshore flow for the coastal Santa Barbara, it's weak, right? In the nighttime, we actually see the northerly winds. So every day there is some mountain winds with northerly direction, but they are weak. It's about 10 miles per hour. So this is the climatology normally we observe in this region. If you look at other seasons, this is the season during September, November, where Santa Ana winds are also important. That's why I put this season here. We see that the winds over the shore are weaker. And generally speaking, during the day and during the night, these winds are weaker. And this is important also for the intensification of sundowners, because what's happening in the coastal area also plays a role for what's happening in the mountains and also in the valley region. See also that winds were a little weaker if you compare with March. Now you compare with September, November. You see that winds are weaker in these two seasons. So there is some seasonality in these winds that are very important. The National Weather Service, they forecast these events. They rely a lot on the differences, just using as a rule of thumb, the differences between sea level pressure at Santa Barbara, Bakersfield, and Santa Barbara, Santa Maria. And they have been using this for 20 years. They have a table. When they have these differences are greater than 5 millibars, then they start, wow, winds are going to pick up, and we're going to get sundowners. They look at other things. They look at the presence of the jet, the pressure gradients, and everything. But this is an important, for them, indication that winds will be intensifying. Although they have done a wonderful job in predicting this type of prediction does not tell you where these winds will be strongest and what time. So using their criteria, this is a statistic of the number of events throughout all these years, 2000 to 2017, events that they classified based on one station as sundowner events with wind speeds greater than 30 miles per hour or gusts greater than 35 miles per hour. And you can see there is a very seasonal variability with the peak in spring. So sundowners happen year-round, but they peak in spring. Now, here is our study, a previous study, showing what sundowners look like. And this is basically the date where there was the Jesucita fire. Here's the ignition point at the Jesucita fire. And what is this figure is showing in colors is relative humidity and winds. What I'm showing this figure just to show you, especially if you are fighting fires, you probably are very concerned about this contrast, because as you move towards the east, you're going to find an atmosphere that's very different if you are in the western part, relative to relative humidity and wind speeds and direction, also important. But another important thing is that when you have these events, and this is what makes them very difficult to fight those fires. This is an example. It's a cross-section. So imagine we are crossing the mountains. This is north. This is south. This is the ocean. This is the island. And this is San Inez Mountains, San Rafael Mountains. This is a cross-section across the point where there was an ignition fire for the Jesucita fire. What this is showing in red is where the strong winds are. And this is daytime. So when the fire started, actually, the atmosphere winds were weak, winds near where the fire was, more or less. But there was very strong winds in about 2,000 meters. And so during the night time, what happens when you have this situation is that during nighttime, with the cooling of these mountains, increasing stability, then we start seeing the jet developing in the lee of these mountains. And this was the worst. This was May 7 at 22 PDT, when things got really out of control, and then when this jet happened and intensified. This happens all the time when we have sundowners, and we want to understand whether this was a realistic thing or not. So we had this first sundowner experiment to evaluate all this variability and profile of winds and thermodynamics and improve understanding of sundowners. We did this with using the Craig Clements truck. So his students drove the truck there, and we launched a few radio sounds to try to understand these events. The National Weather Service collaborate, the fire department were all collaborating with us. And so what I want to show, just to show quickly, this was the setting for the synoptic conditions. So it had a very strong pressure gradient showing here. And very strong winds offshore, backing with elevation, which means that, well, at low level, they should be more northerly, cross-mountain winds. So here is maybe a little technical, but I want to show you what we observed. So here is where we launched the balloons, this point. And so you see the height here showing elevation, and the colors are showing the intensity of the winds. I just want to point out what we observed, because I think this is an important issue for firefighting. We can see that during the daytime, calm winds, actually cool, the marine layer was dominating. When we got close to 20 p.m., 8 p.m., we start seeing then the intensification of the jet from being very weak to close to 50 miles per hour at this point, at this time of the day. It is very shallow. So this is the lee jet we are talking about. Very shallow, very low elevation. So during the night, this start, when you have this jet, then you have all the gust winds, intensification of the winds. But later on, because of turbulence, you have strong winds, you have also turbulence, then the winds weaken. And that's when things get really difficult for firefighting, because, okay, you see the winds weakening, and then you say, okay, this is over, this is the cycle, we can start having some strategy in battling the fires. However, later on, the winds intensified again, and then were very strong and very shallow. And then later, a few hours later, that was the end of the event. So 2 peaks, very strong. What we also found is that when you have the peak of the winds, before the peak of the winds, we see the signature of mountain waves. So the mountain waves, because you have air forcing across the mountains, and then we see very deep modification in temperature in the profile. Maybe it's a little technical, but it's just showing this is some precursor that is very important for the intensification of the jet. But we don't see similar thing when we observe the second jet. So predicting all this variability is really challenging. And so we are still in the process of trying to understand, using the models, using more observations. Well, I want to end now talking a little bit about the Thomas Fire, because I think it is a common knowledge of most of you and interest. And we talk about also the importance of sundowners against Santa Ana winds. And I want to show that they are very different. When we have sundowners, we don't have Santa Ana winds. When we have strong Santa Ana winds, we don't have sundowners. Actually, the winds are very weak in the coastal area. But they can transition, and this was an example that happened, and this was what makes so difficult for Santa Barbara region. I want to show an animation. Hopefully I can. Just showing how this started. So just quickly, we are seeing the coastal area. So this day, this is December 15. So there was a fire already going on in all these mountains in the Ventura area. But this particular day was a good day for fighting these fires, because you see the blue are indicating very calm winds. So the fires in this region was actually maybe more control. I don't know much about details about fighting these fires, but it was a very, very weak winds in this area, very weak winds in Santa Barbara as well. But the winds start picking up over the ocean area by this particular day. And then you see that over time, actually, they begin to intensify in the coastal area of Santa Barbara here, the west coast. And this is about 3 p.m., right? So as things evolve, we start seeing that the winds intensify over the mountains area, and they become northwesterly at this point, meaning that, let's just stop. Meaning that this was the time when the fire spread towards Santa Barbara and Montecito area when you get, during the night, when you get the northwesterly winds very strong. Now you see this is the morning of the next day, and now what do you see? Very strong Santa Ana winds picked up again in red, is showing very strong. Winds weakened over the Santa Barbara coastal area very much. And then at the end of this period, you get again your Santa Ana winds. And notice that this was when you have these winds in Santa Barbara, you don't have in Ventura. So that's something that needs to be understood about these winds. So to conclude, lessons we learned from all these studies so far is that standouters have very strong, very distinctive spatial variability. That's very important. They are associated with the presence of a nocturnal lead jet that is related to several processes, physical, dynamical process. Wave breaking is one important of them for people in forecast. Understand this is important. And all these issues are difficult to predict, and we hope that we are contributing in the future to improve this prediction. And we hope to have a comprehensive field campaign at some point to understand these winds. Thank you. I hope I don't have it.
Great. Do we have any? We have time for one or two questions.
You mentioned that there's a lack of weather stations in the area. I'm wondering if any of the utility companies down there are considering adding stations like PG&E is doing in Northern California.
Yeah, I believe they are increasing the number of stations in this region now. The Forest Service put some stations, additional stations, but which is important. But so far to this point, we never had some kind of climatology. We couldn't understand before now what's going on. But some stations are increasing there. Yes.
If I'm recalling correctly, you had an early slide that showed that the frequency of fires prior to 2000 was much less than after 2000. Just wondering why.
Well, it's a drought was a problem. I think this was something also related to this, basically. But, there was a fire in 2007, 2008, 2009. That were not within the period of a drought. Most of these fires are people-related, right? There was arson. There was also other. When you have strong winds, you have people do all kind of stuff, stupid things. But this is why education is so important, right? Educating the community about preventing this. But yeah. I think the warming is important, yes.
Sure.
Okay, thank you very much. That was fantastic. So we have speaker bios that'll be on the website. I won't go through all the details. We have stories of all of them that we could share, but we'll just keep it brief. But I want to introduce our next speaker. This is Carrie Bowers, who's a fire meteorologist at San Diego Gas and Electric. She received her bachelor's degree at San Diego State in kinesiology and then worked as a firefighter with the Forest Service for 9 years, and then came to San Jose State to do her master's in meteorology. And she did her master's on Diablo winds, and it's the first study of Diablo winds ever. Now you'll see lots of papers coming out on the phenomena as it's becoming very popular. We were just notified, or Carrie was just notified, that she won the San Jose State University Thesis of the Year Award for her work. So she'll be presented with the award at the graduation. So, thank you.
All right, thanks, Craig, and thank you all for coming. So before 2017, October 2017, not a lot of people were talking about Diablo winds. Most people had never even heard of them. And of course, after the fires of Napa and Sonoma County of 2017, now people are becoming more familiar with them. But these winds aren't a new phenomenon. Some people in this room already knew that. The history of these wind-driven fires, these hot, dry winds, the fire history isn't new either. The Berkeley fire, the Fish Canyon fire, and Berkeley Hills fire, or East Bay Hills fire, Tunnel fire, it's all the same thing. Those were all in this East Bay of the San Francisco Bay Area, and so we're talking Berkeley Hills, Oakland area. And then, of course, the Northern California fires of 1964, some of you may be aware, had a very similar, almost identical footprint to the Wine Country fires or Northern California fires of 2017. So they were talking about these way back in the 1800s, late 1800s. There was an article in the De La Alta, California, talking about these winds. But really, you know, the first paper that even started to look into these was Monteverdi back in 1973, talking about the extreme fire danger in the East Bay Hills area. And of course, now we know that this is expanded. We had this problem way back in at least the 60s, before that even, in the North Bay area. So the term Diablo winds came from Jan Knoll from the National Weather Service. And the winds come from the area of Mount Diablo. If you're here in the East Bay area, North Bay, of course, we didn't really have the Diablo. But Diablo in Spanish means devil. And so devil winds, hot, dry winds, and of course, they cause quite a bit of fire hazards. So Smith et al. Looked into the Diablo-like winds of the North Bay area, comparing them to the winds in the Western Sierra, but really only 22% of those events that he studied occurred in conjunction with each other. So we might have some severe downsloping winds in the Sierras at the same time as the North Bay area, but that's not always necessarily the case. You could have them separately as well. So first, we need to know how often do these fires occur, or winds occur, where do they occur? And so looking at Diablo winds themselves, with a sustained wind speed of 6 meters per second or about 13 miles per hour, lasting for 6 hours or more, with a minimum RH reaching down to at least as low as 20%, and then we put the limitation on it that it would hit at least 4 stations. Now, of course, you can see in this area here, as far as station density at the time, there wasn't a very good station density, and so this is kind of hard to do in extended climatology with these stations. So we did a 17-year climatology and then moved on to a synoptic composite, which I'll get into, using 43 particular Diablo wind events over those 17 years. So when we look at this map here, the red event, or the red dots, will show you the areas that are seeing greater than 2 events per year, and this is per each one of those little stations there. They're kind of small, but these higher elevations, Knoxville Creek up here in the North Bay and kind of lining around the Sacramento Valley, sees very frequent northeast hot, dry wind events. And the coast range here, and you can see, so here I'm talking about the East Bay here and then North Bay up here. The coast range stretches down there. This is the Diablo range. We see these events really on this downsloping side, these foothill areas, and we'll get into why in a little bit. As we get closer to the coast, there really isn't that many events. However, they do sometimes stretch all the way out to the coast, and so in years when we have very dry fuel moistures and hot, dry, windy situations, those foothill or the coastal areas could see some impacts as far as fire danger is concerned. So we have about 2.5 years or 2.5 events per year on average, and this is going back to from 2000 to 2016. So it didn't capture the 2017 events. And we have as many as 6 events in 2014 to as little as 0 events in 2016. And so there is a range. And we see that the fall, particularly October, has the highest frequency of these events. And if you look, this line here that's been put over this is our fuel moisture. This is our live fuel moisture using chemise throughout the Bay Area. And the problem is, you know, especially the firefighters in this room, is, you know, when we get those very, very low live fuel moistures and we get very dry conditions, windy conditions, you have potential for extreme fire behavior. And we can see the fall, October, November is a pretty big time for that. And even in January, in some dry years, if we don't have rain by that time. So looking at the synoptic composite, the shading here is the sea pressure, mean sea surface pressure. I'm going to say that wrong. And then the lines are the 500 millibar geopotential height. So what we're seeing here, just looking at this geopotential height here, as these lines line up, you can see they're starting to run north-south over the San Francisco Bay Area. Now, this is high up in the atmosphere where we have our driving conditions. And so this has the potential to really force a northerly wind component into the Sacramento Valley area. And then as we get this high pressure carving out over the northern Great Basin and central Oregon, we get this surface pressure gradient where winds are going to flow at the surface from the high pressure area down to the low pressure area. So we start to get these northeast dry winds coming down out of the northern Great Basin and central Oregon. So then we looked at modeling these events. We want to get a better picture of what's happening on the mesoscale level, what's happening on these mountain levels. And we looked at 3 of them: the East Bay Hills Fire, a severe Diablo event in 2000 that was not associated with any large fires, and the Tubbs Fire, which was one of the fires of the Wine Country fires in 2017. We're going to focus on this Tubbs Fire. I'm not going to go through all 3 models, but also not going to really get into this page too much, but I want you to see this domain here is what I did the modeling over, and we're going to be looking at these 2 cross sections. So up here in the North Bay, we're stretching from the Sierras down to the Coast Range in the North Bay area. And then in the East Bay area, we're going from the Sierras again to the Coastal Range. Just a quick model validation. The models did handle this fairly well. There were some little areas that didn't do quite as well with the, we have dew points here. Didn't catch it quite as well, but well enough that it would work for this modeling. So I wanted to look at the synoptic analysis, and here I did pull together these 3 events. And so you can see this matches up with the climatology that took into account the 43 Diablo wind events. Maybe at the start, we didn't have quite that sea level pressure gradient going, but then by the time that these events really got going, we can see these sea level pressure gradients really taking on that same footprint as the synoptic analysis. So here's the cross sections, and on the left side here, this is the cross section of the northern Bay Area. So we go from the Sierras on the right all the way down to the Coast Range on the left. And then in this section over here, we have the East Bay Area with, again, the Sierras on the right and lower elevation, of course, Coast Ranges on the left here. So you can see as this event started, up here in the upper atmosphere, the winds are really opposing. So we have some northwest westerly flow aloft, and then we're starting to get a little bit of this downsloping over. This would be Mount St. Helena, if some of you are aware of that area. Same thing down in the East Bay. So at the time that we were getting these wind events up in the North Bay, we were getting it down here as well. The shading is the dew point temperature, and so these cooler colors here will show you the drier air. As we get further into the event, you can see this layer of dry air starting to come through. And then down here, as we get downsloping over Mount St. Helena, as well as a little bit over the Sierras, it starts to really mix down that dry air from aloft. And so you start getting very dry air at the surface with high wind speeds, and we can see them actually coming downslope down the mountain. So this isn't exactly wind speed, but it's the wind speed that's aligned with the cross section. So how fast are the winds going along a northeastern trajectory? And again, same thing on this left side here, we have the North Bay area, specifically focused on Coffee Park. As some of you are aware, Coffee Park was hit particularly bad in October of 2017. So we begin to see early on in the event a little bit of downsloping occurring over Mount St. Helena. At the same time, in the East Bay area, we do have a layer of fairly strong north winds, but it's not really seeing a whole lot of mountain wave activity. As the event goes on, you can see here in the lee of Mount St. Helena, we're getting a good degree of very rapid downslope winds. And then above it, there's like a rotor-like activity where winds are actually opposing. They're going in the opposite direction. So we're getting a bit of a mountain wave rotor activity going on. As the event progresses, you can see here down in the East Bay, we're getting much stronger winds, and they're starting to create mountain wave activities over like the East Bay hills. And then here, we've pushed this all the way to the surface. So now these very strong winds are all the way down at the surface. And then moving on into the early morning hours of this event, right here over Coffee Park, and it's kind of hard to see in this here, but there's a little bit of a lighter pink there. And that is where, because of the mountain wave activity, we're starting to see these really fast winds lift off the surface. So we're no longer getting these winds at the surface at that location in Coffee Park. And when we went up there and spoke with the first responders, the firefighters and the police officers there, they said around this time, it was probably close to 4 a.m., they saw the column just stand straight up, which means that the fire right there at that time was not getting very much wind speeds. And so we're able to replicate that here in the model here. But looking at this as far as fire management is concerned, it's very important to realize that even here, so in Coffee Park, just 5 kilometers upstream in that area, the winds are still very strong. And so you could have, obviously, as you know, very low fire activity going on in one location, but with these winds still at the surface, you can have very extreme fire behavior going on at another location in the fire area. So I didn't show you the model of the tunnel fire or the East Bay Hills fire, but I will go over shortly Some of you guys are aware of what happened back in 1991, where on October 19th, there was a small fire start. They put it out pretty quickly, but left some crews on it overnight. And then in the morning, a Diablo wind event surfaced. And it picked up so quickly and so intensely, firefighters were not able to get a hold of it. Everybody wanted to just evacuate people. That was the main concern. Unfortunately, there were 25 fatalities and 3,000 structures destroyed. And this is in the wildland-urban interface. And so you can see in this picture here, those were homes. This was, very much like with Santa Rosa in 2017, these fires are burning through homes. And the Tubbs fire, you'll also see on this is satellite imagery, or radiance actually coming from here. You can see multiple fires, and so, I think we're all aware of all the fires that started in 2017. But, in that same way, where with this rapid of fire behavior, you can't really get out in front of it. You're not going to put firefighters out there with hoses pointed at the head of the fire. It's really just getting people out, getting people safe. There were 22 fatalities with this fire, more than 5,600 structures destroyed, and over 36,000 acres. So these events they're extreme fire behavior events. They're strong, dry offshore winds in the San Francisco Bay Area that are driven by a surface pressure gradient. We get about 2.5 events of these per year, although they could be more, they can be less. They're most common in the fall and winter, and they lead to these downsloping mountain wave activity. And as I said before, these events lead to extreme fire behavior should an ignition occur. So with that, I think I have a couple minutes for questions. Any questions? Thanks.
With respect to defining the parameters for your frequency analysis to define what you call a Diablo wind here, you set the wind speed at 5 meters per second. What was the rationale there? Was it 6? I'm sorry.
Yeah, no, that's good. Yeah, so 6 meters per second. When Monteverdi studied the extreme weather events in the East Bay Hills, he used 4.5 meters per second as, if you look at the Beaufort wind scale, if you're familiar with that, it talks about what wind does to surrounding vegetation. And at 4.5 meters per second, that's when we start seeing vegetation lifted up and moved. And so that's when we could start seeing spot fires. It's not an extreme, that wouldn't be a very far spot fire. But when I use 4.5 meters per second, it is fairly low, right? For a sustained wind speed, 12, 13 miles per hour, or 4.5 is 10 miles per hour, but isn't really that high. And so I ended up getting a lot of false Diablo events, I guess you'd say. And so when I brought it up to 12 miles per hour, 13 miles per hour, it really was catching those Diablo wind events. But at a sustained wind speed of 13 miles per hour, sustained for 6 hours or more with that very low relative humidity, we really do begin to see some good fire behavior at that time.
Thank you. I'm just curious to know what geographic radius have you measured these the Diablo wind impacts? In other words, we've seen the North Bay, we've seen the East Bay. How far south or how far west could they go? Could they affect the peninsula? Could they affect Santa Clara Valley? I think everybody in this room would like to know if there's any way of charting, of predicting where these winds might hit.
Right. So I know Warren Blyer will be talking about the prediction part of it. As far as where these occur in the Bay Area, and since the Diablo winds have been traditionally, when it's been talked about by the National Weather Service and by local meteorological people, they're talking about the San Francisco Bay Area. So I did use just the counties in the San Francisco Bay Area. I believe there's 9 of them. But it's within this domain here that you're seeing. Unfortunately, with the lack of weather stations to use, we didn't get to see a very dense network. And so what you're seeing here is that over in these hills areas, and so this stretches all the way up to Lake County, maybe? Lake County. And then all the way down, Santa Clara County is the lowest one that I used. And you can see even down in Santa Clara County, we do have some. And there's been at least one in the last 17 years where it was a very widespread event. It did register over in the peninsula. But the peninsula is quite a ways away from these hills here, and so they're not quite as frequent. That being said, though, since it is possible for it to reach there, we do have to be careful when we're getting a widespread extreme event that any drying that occurs in the peninsula, we could have extreme fire behavior in that area too.
Great, thank you. Let's thank our speaker again, and we'll move on to the next speaker. Okay, I just need a second because I got some of the talks on my laptop here. Great. So our next speaker is Warren Blyer from the Monterey NWS Forecast Office. He is the Science and Operations Officer there. A little bit about Warren. He received his bachelor's at UC Davis and his PhD at University of Washington. He did some of his PhD work at NCAR and then was an assistant professor at UCLA up until he moved to the Weather Service in 1998. So, welcome. And so this could be, we could do this.
Just put it in presentation.
Is that like that? Like that works?
Yeah, that's great.
Perfect, okay.
All right, great. Thank you, Craig. And thanks for putting this whole workshop together. So a couple things. First off, the title is a little bit different than what you have in your agenda. I sort of made a little bit of a change there and decided to kind of reorient the focus of my talk a bit. And before starting this, I'm going to go off program a little bit and just comment on the question that was brought up at the end of Carrie's talk. I think that it remains to be defined exactly what geographic area the term Diablo winds applies to. The term first came out in association with the tunnel fire in October of 1991. And that was, as winds coming upstream or downstream from Mount Diablo. So the Diablo winds then blowing across the hills of the East Bay and the tunnel fire. And then that term started applying to other fires in the Bay Area, and then with the Tubbs fire to the North Bay, and then we had the Camp Fire in Paradise, and the media picked up on it. So now it's become kind of a broad thing for strong offshore wind events across northern and central California, but the details, the geographic details are important and they vary widely across that area. So ultimately, I think we're going to need to kind of hone down a bit exactly what Diablo winds are, at least with respect to their potential fire weather impacts. With the Sundowner winds, we're talking specifically winds off the Santa Ynez range and meteorological small-scale structures that can set up in that area, the Santa Ana winds, through the, over the ridges and through the coastal gaps of Southern California. Now we have Diablo winds being applied across Northern and Central California, at least that term. All right, go on to my first slide. I want to start off just by talking, I think it'll be easier to hold this, just a little bit about us in the National Weather Service. Our mission statement for the National Weather Service, I'll mention, by the way, that we're one of the agencies of the National Oceanic and Atmospheric Administration, which itself is embedded in the U.S. Department of Commerce. So to provide weather, hydrologic, and climate forecasts and warnings for the United States, its territories, the adjacent coastal waters and ocean areas for, and these are the key words, protection of life and property, and also the enhancement of the national economy. Let's see here. There we go. So, by the way, I'll mention that we are physically located down the coast in Monterey, but we identify as the San Francisco Forecast Office of the Weather Service. And if you take my office down in Monterey and you trace it back historically, you know, Craig mentioned that this was the first university in the Western United States. The San Francisco National Weather Service Forecast Office was the first such office in the Western United States. When the Weather Service was established in the early 1870s in the Signal Corps of the U.S. Army by joint resolution of Congress signed into law by then President Ulysses Grant. That was in the early 1870s. In 1878, the office in San Francisco, first one in the Western United States, was established in the then federal building in downtown San Francisco, and that traces continuously to our office now down in Monterey. So in terms of the operations of the Weather Service, 122 forecast offices that cover all of the United States and the U.S. territories. 10 different forecast offices touch some part of California. And you can see ours, actually, compared to some of the other ones in the Western United States, our area of geographic responsibility is relatively small. On the other hand, the population is on the order of 8 million. And the economy, if our forecast area were broken off as a separate country, it would rank about number 18 in terms of economies among world countries. So, well, Silicon Valley is here. All right. So what do we do at our forecast office? Key thing that we're doing now in the National Weather Service, providing decision support services for core partner agencies, and this ranges from city office, state offices of emergency services, CAL FIRE, the FAA, the Coast Guard, any public entity that is significantly dependent on and using the kind of observational forecast material and the watches and warnings and advisories that we provide. So we have programs on the public aviation marine forecast side, also our fire weather program. Within each of these, in addition to the routine forecasts and products, we issue watches, warnings, and advisories. In Weather Service parlance, that's referred to as our WAWA activity, WWA, with a kind of extra A thrown in there to pronounce it. We do outreach, and we're also responsible for collecting a lot of weather observational data and maintaining the associated climate database. Whoops. Let's see here. Oh, I went. Need to backspace one slide here. Where is it? Let's see. Oh, yeah. Perfect. Thank you. All right. So our National Weather Service's Red Flag Program, which is related to, which is our fire weather program. Although, of course, we're also issuing routine fire weather forecasts. So the Red Flag Program is designed to alert user agencies of the potential for extreme fire behavior. Necessary components are the existence of a critical fire weather pattern and high to extreme fire danger conditions from a fuel standpoint across the relevant region. So for fuels, we're looking for conditions where the 10-hour fuel moisture is less than 6%, the annual grasses are cured, and there's been no rainfall of 1/10 of an inch or greater in the last 24 hours. From a weather standpoint, at least 8 hours of wind and relative humidity values meeting the red flag criteria, which are on the next slide. And there's also, of course, the same sort of thing, but with respect to so-called dry thunderstorms that are producing a lot of lightning but no significant precipitation. But I'm going to focus here on the wind-driven side, not the lightning side. We generally issue red flag warnings if the event is within 24 hours, the meteorological high wind event under these conditions, and a fire weather watch from 24 to 72 hours out. And these are the criteria. And again, it's assuming that the fuel moistures are low, the annual grasses are cured, that there's been no recent rainfall. And so combination of the sustained 20-foot wind speed lasting for at least 8 hours, and the relative humidity, both from the standpoint of the nighttime maximum and the daytime minimum. And when we're getting into events like the tunnel fire or the Tubbs fire, we're getting down into the far lower right-hand corner of that matrix. Okay, so something that I want to just mention here, and this is pretty obvious. Ultimately, for wildfire, there are 3 ignition sources. Stuff that has to do with people in some fashion, lightning, and in rare cases, volcanic eruptions, which is not really an issue in our area, at least we hope. So it's the people stuff for these fires that's really important. A recent study published in the Proceedings of the National Academy of Sciences, human-started wildfires expand the fire niche across the United States. Our analysis of 2 decades of government agency wildfire records highlights the fundamental role of human ignitions. Human-started wildfires accounted for 84% of all wildfires, triple the length of the fire season, and so on. But what I want to point out here is that no matter how dry the fuels are, or how strong the Sundowner or Diablo winds, no ignition, no fire. So this is a little bit different than all the other stuff that we at the Weather Service issue watches, warnings, and advisories for. There we're forecasting a meteorological event that itself could have strong impacts. Here, we're forecasting conditions in which extreme fire behavior could occur, but that only happens if there's an ignition. No ignition, and Carrie talked about a case where the Diablo winds were really strong, but no fire occurred. All right, so top 20 most destructive California wildfires from CAL FIRE, or California Department of Forestry. And this is real quick. So like if you take a photograph of this or something, I took a quick look at each and kind of what sort of wind events seem to be associated with it, but this was done in like 20 minutes. So, but I think the basic idea comes through. If you look at the top 20 most destructive wildfires in California, Diablo winds and Santa Ana winds show up for an awful lot of them. And the Painted Cave fire down there, Sundowner winds. Then we have something, and Carrie mentioned this, the Thomas fire. When it started, it was Santa Ana winds, but it evolved to a point where Sundowner winds did play a significant role. And if you go further down the list, we'd start seeing Sundowner winds showing up an awful lot. Those fires are a little bit smaller typically, but some of them have also been enormously destructive. All right, so I mean, when I saw this, when this was happening back in October of 2017, this to me was just off the chart amazing. That's 3 hours and 30 minutes. This is heat signature GOES 16 satellite data. 3 hours and 30 minutes from the left to the right in terms of what happened. I think that's just amazing. When we're talking about extreme fire behavior and rate of spread. Let's see if this link works. All right, I'm not seeing how I move the cursor here. Whoops. Someone could give me a hand with this for a second. I just want to click on the link there. Oh, there it is. All right. There is. Anyway, this was well, it's showing here, but not up there. It's progressed on, so you want to go back to the link on the page and just start it over. The National Weather Service disavows any knowledge of what might be shown on the screen here. So if you just click, I would go back to that, start over. Yeah, and then just play it, and hopefully there's sound.
I dispatched someone from the fire department.
This is a sheriff's deputy that was caught in the early stages of the Tubbs fire and turned on his dash cam.
I don't know.
All right, well, anyway, it's a few seconds. It gives you an idea. All right, good, thank you. All right, so something, where am I on time? What have I got? Yeah, okay, we'll go fast. Something that I want to point out, National Weather Service forecast models did a great job of picking up on this event on the larger scale way in advance. That allowed us to get both fire weather watches and red flag warnings out fast. I'll fly through these really quickly. Just look at the basic 500 millibar, 850, and sea level pressure patterns. And I just took 5 fires, Diablo winds, a Sundowner wind case, a Santa Ana wind case. And on the large scale, the basic patterns are remarkably similar. And in each of these cases, the fire weather watches and the red flag warnings from the respective forecast offices went out well in advance. Remarkable similarities. So the key takeaways from that, The vast majority of the most destructive California wildfires have been associated with strong offshore wind events of exactly the sort we're talking about. Associated basic synoptic patterns are remarkably similar, amplifying positively tilted large-scale upper ridge off the west coast, surface high pressure building strongly from the Pacific Northwest into the Great Basin, and with the increasing sophistication and resolution of our models, ever more timely issuance of the fire weather watches and red flag warnings. And finally, I want to just say something about our incident meteorologist program. These are people in the Weather Service, forecasters who've gone through a lot of additional special training to be deployed to the wildfires to provide on-site weather support to the state and federal agencies who are fighting the fires. They provide detailed forecasts and briefings to the incident command. At the National Weather Service office that I'm at, the San Francisco office, we have two IMETs, our lead forecaster, Ryan Walbron, and also lead forecaster, Matt Maley, who himself was deployed to the Tubbs fire, and they're both sitting in the audience over there today. So I'm delighted to have them with us. And that's it. Thank you very much. Yeah.
The connection to the fact that it's an indicator, as you said, that it's human created. How do we get it out to the general population? I've spoken to coworkers. I'm not in the firefighting business myself, but how do we get the message out broadly? Kind of like there's spare the air alerts. You get those all the time. Everyone knows it's a spare the air day. But does the general public know about red flag warnings? And they don't. Generally, my experience is they don't know what it means.
Yeah, so we, not only is this included in all the forecast products and forecast discussions that we issue, but we hit it hard in our social media presence. So we're tweeting it out, we're putting it out on our Facebook page, we're talking to the media in the Bay Area. We're getting it out every way we can and highlighting along with that the risk of fire and, that this is a time to be really careful. And agencies are taking action based on our issuance to shut things down. In an extreme case, parks will be closed down. There'll be a banning of having any outdoor fires or barbecues and so forth. So I think the message is getting out there. But of course, the problem in a really extreme weather situation, it just takes one spark in the wrong place and it goes to town.
Great. Let's have.
For the fire service, are red flag warnings, are there other weather predictions or other weather factors where an agency might need to upstaff? For example, if the RH is going to be 1% above, 2,000 feet, but it's only going to be 5 miles an hour northwest winds. So are the red flag criteria enough for an agency to go upstaff, downstaff, or are there others that they should be considering that don't meet the red flag warning
That's
criteria?
a good question. And actually, so we issue routine fire weather forecasts. Those go out twice a day during the fire season. And we'll headline those. So let's say it's a situation kind of along the lines of what you're describing. It doesn't really meet red flag criteria, but it's looking a little potentially dangerous from a fire weather standpoint. We'll put a headline in that product. Hey, really poor humidity recoveries and, dry offshore winds. And we'll talk about that. And that goes out to the firefighting community, but it isn't actually issuing a red flag warning because the criteria for that haven't been met. So there's all sorts of forecasts and messaging that go on independent of this actual warning issuance itself.
Hey, Warren, question over here. This is Scott.
Yeah.
So I know not all red flag warnings are created equal. So in the future, are you looking at ways to potentially put that in historical context, like this is a 1 percentile event, et cetera?
Yeah, a discussion about that has started. I think it really started after the North Bay fires. You know, I didn't say this, but I see this future where we start having count 1 to 5 red flag warnings kind of things, you know, following with tornadoes and hurricanes and the rest of it. I'm just speaking for myself here. I think that I think that might be going a little far, but I think, you know, highlighting conditions, say that with either the tunnel fire or the North Bay firestorm of October 2017, hey, this is really extreme. This goes beyond your run-of-the-mill red flag case. So we'd have a kind of, you know, red flag warnings, extreme fire hazard sort of thing. But this is the National Weather Service, this is the government, this sort of thing has to be worked through a national policy and framework and so forth. But discussion of that is ongoing.
So just a very brief comment. I thought that the slide that you had was very compelling, where you had the 20 most destructive fires, and in 20 minutes you're able to like assign 3/4 of those to one of these basically dry east weather
Yeah,
phenomena.
and I'm not going to say that this is like what would get published.
But my
It's-
comment's pretty important, I think, in the sense that at least one of those fires that was not so labeled actually occurred under extreme wind events in a prefrontal environment. And that was the 1992 Fountain Fire in Shasta, and really phenomenally extreme fire behavior. So the notion that just east-north winds are the only kind of mesoscale phenomenon that drive extreme fire behavior is not entirely accurate.
Well, right, and I
good
think
point.
that's a really good point. And as I said, I did this really fast, and yeah, there were a couple of cases that weren't labeled, and I just didn't have the time to track down exactly what was going on with them. But yeah, I think that's an excellent point.
Great. We're need to move on to our next speaker. We have a little bit of time to transition. Let's thank our speaker, Warren. Great. Thank you, Warren. Yeah, so since we're jumping into the next session, feel free to get some coffee. We're not going to have a little coffee break. We're going to go straight to an early lunch, and then we'll be able to mingle for an hour. Oh, there it is. Okay. I'm going to wait till a couple people get back. And people will roll in, so. Okay. Is it not on? It's on. All right. This one's not working. I'll check. There we go. Okay. We're going to start with our next speaker to stay on track, but feel free to get coffee. All right. So our next session is basically focused on fire weather indices, new generation fire weather indices. And so this session is basically set up for not only looking at these new indices in the next talk, but also looking at some other fire danger applications here in the Bay Area. So I'd like to introduce Heather Kane, who is a meteorologist at Southern California Edison, but also finishing her master's degree in meteorology here at San Jose State. So she's in the process of wrapping up her thesis, and she'll be presenting some of her thesis work here now. So.
Okay, so I'm going to talk about fire weather index performance. Oh, yeah. Cool, thank you. So I'm going to be talking about fire weather index performance on large wildfire events in California. So I'm going to be comparing 3 different indices, so the hot, dry, windy, Fosberg's fire weather index, and the SAW-T's weather component of large fire potential. And I'm going to use raw stations for this analysis and to look at the 4 recent large wildfires in California. So it's going to be the Thomas Fire, the Mendocino Complex, the Camp Fire, and one other one, the Carr Fire. And I'm going to show you the plots of the 3 indices together for those fires and the correlation. And then I'll end with some future work that I'm doing. So hot, dry, windy, I'm sure you guys have heard about it. It's the new index that was introduced by Sirach et al. In 2018. It's calculated using the maxima of both variables for vapor pressure deficit and wind speed at 500 meters within that mixed layer. So they used CFSR data, which has 38 kilometer resolution, and they used those 50 hectopascal intervals to approximate the 500 meters. So their whole goal was to present it as strictly an atmospheric index because they didn't want to take into account fuels or anything else. They just wanted to look at fire weather in general. And how you calculate it is just the wind speed times the vapor pressure deficit. And the next one is Fosberg's fire weather index that I'm looking at, and it's calculated using Byram's flame length, Rothermel's rate of spread model, and Simard's equilibrium moisture content. And it's supposed to create that link between atmosphere and fires. So he also made it to supplement the fire danger rating system so that it can go down to fine scale areas to just add some support. And it's a lot more complicated than hot, dry, windy, as you can see. And there's a lot of if statements for less than 10 relative humidity, and it takes a lot more into it with the temperature, relative humidity, and wind speed. And then we get into the Santa Ana Wildfire Threat Index, and Tom Belinsky is somewhere in this room, but he helped make this index it's to focus on the wildfire threat for the Santa Ana winds in Southern California, and it's focused on those Santa Ana wind events coming down and hitting with the gap flow and everything, so they can kind of get an idea of what the fire potential would be for a fire to become unmanageable. So the weather portion of that index is the wind speed squared times dew point depression. So it's a little different than hot, dry, windy, but it's kind of similar. So what I'm going to be doing is analyzing these indices using RAWS data. I talked to Brian Potter, and he helped make hot, dry, windy, and we talked about maybe me looking at the RAWS station data as opposed to how they were calculating it, because keep in mind this is different than what they did in their study, so it's kind of looking at a local scale, looking at actual surface data as opposed to using model data to scale down to just see how it works. So they wanted to look at it, so it might be helpful for their future research to better refine these indices to see how fires would get potentially large. And we're going to see if that works out. So the RAWS stations that I selected, I made sure to go within a 20-mile radius to the perimeter, made sure not to go past that, just so it was referred by Brian Potter to make sure that it was kind of getting local scale. It was close enough for these fires to, it was close enough for the area to understand what was going on with the fire behavior closer to the perimeter, if that makes sense. So then we have the Carr Fire right here, and you can see the stations that I have around that. And then we go to the Mendocino Complex, and you can see the stations right there. And then we move on to the Thomas Fire progression, and you can also see a lot more stations around that perimeter right now. And then the Camp Fire progression, which was kind of dicey because it's it's hard terrain. Well, all these fires, I'm sure you're all aware that it's very complex terrain out there. So we're going to start with fuel-driven fires. So starting with the car fire, you can kind of see how all three indices end up looking. It's kind of hard to see from up there, so I apologize. But if you look at the green, see it? There we go. So if you look at the green line, that's hot, dry, windy. So hot, dry, windy is going, kind of looks like a diurnal type of thing going on, but then it does ramp up a little bit, as you can see, when it gets to the extreme fire behavior. So this line right here is the start of the car fire, so that's the ignition, and during this extreme fire behavior, that's when we're looking at the highest rate of spread. So the 47,000 acres, or I shouldn't say rate of spread, but total acres burned was 47,000 acres during that time period. So we're talking about pretty fast fire speeds. And you can see that how it kind of dips up a little bit, but this wasn't a wind, it wasn't a weather phenomena that was happening. It was just something that was fueled by those fuels because it was so dense in that area. So you can kind of see maybe it was picking up on the circulation of that column once the fire started ramping up. So maybe some of the stations were picking up on that. And then, but you can see that they're actually quite similar with how they react to the fire weather in general. And then we get to the Mendocino complex, and it looks like nonsense. And it doesn't really pick up on anything during that time period. So it kind of bypasses that 31,000 acres that was burned and the 79,000 acres that was burned as well. You can kind of see them just kind of staggering along, kind of mimicking each other, but it doesn't do too well saying, hey, a large fire was probable for this area at that time. So what was interesting is that when doing the correlations for these indices, they actually are extremely correlated. So we're getting like 0.96, which is outstanding, which that's kind of showing they're nearly the same thing. So, and that was for the car fire. And then we move on to the Mendocino complex, and we're getting something very similar. So this was kind of the drive to move on to wind-driven fires, so we can kind of see what happens with those as well. So the wind-driven fires, you're able to see, so this is the Thomas fire, the Santa Ana event. We all kind of know what happened. That spread really fast with the ignition. So the ignition on the 4th right here, and you can see 130,000 acres burned were in during this time period right away. But as you can see with these indices, let's start with the LFPW from the Sati index. You can kind of see it has a regular diurnal pattern right here. And then once it gets to when the Santa Ana event was starting to ramp up, it actually spikes up, and you can actually see that wind event happening. So using this for station data, it looks pretty feasible for those wind events. And you can kind of see it goes back down, and then when there's like another time for extreme fire behavior, it actually ramped back up again. So looking at the hot, dry, windy index, or hot, dry, windy, my form of it, using the ROS station, you can kind of see it has that little diurnal pattern, and it kind of goes up a little bit in this area during that 138,000 acres, but then it kind of dips back down, and it does not as well as the Sati LFPW. And then you can look at the Fosberg Fire Weather Index, and you can kind of see same diurnal pattern, and it goes up a little bit during that time period for the first extreme fire behavior as well. And then moving on to the Camp Fire, this was a very extreme wind event. So you can kind of see that it has a huge spike right here in like the beginning, but then it goes down. So right when the fire starts, we get that 70,000 acres burn in the first 24 hours. And you can see that all three of them really responded well to that wind spike, and which makes sense. It's all taking into account the wind. So it's doing pretty well right there. And then it goes back down, and you kind of have little spikes, but this was the most crucial region that we were able to see. And then going to the correlations again, you're able to see that they're actually not as high as they were for the fuel-driven fires, but they're still pretty substantially the same. Well, at least correlated, I should say. So that for the Thomas fire, and then also for the Camp Fire. So to summarize, weather indices shouldn't be the only thing that we're looking at when we're talking about fire, obviously, because fire is a part of an Earth system. It's not solely weather, so we can say, but we can try to work on focusing to get these weather indices better, well, at least using it in conjunction to other things like topography, looking at different aspects of a fire, and in order to understand when it becomes large or unmanageable. And what I've noticed is that hot, dry, windy is essentially LFPW. It's very similar in that sense. I have my own opinions, of course, if like the wind speed should be squared. Wind speed is often correlated, and I've had conversations with Tom Rolinski about this. It's similar to topography in a sense that you can get it up the slope, and it kind of accounts for that. And LFPW was created a little bit before hot, dry, windy, so I'm wondering if they talk to each other about it, although hot, dry, windy is calculated in a different way. I suppose like it's going through the first 500 meters of the mixed layer. So maybe there needs to be more discussion amongst all of us. But there was a question about vapor pressure deficit and being more beneficial to use that instead of dew point depression. And it actually turns out that, well, I've had a couple conversations with people, and we were talking about maybe vapor pressure deficit was correlating more so to large fires as opposed to dew point depression. So maybe from there the SAW-T can possibly improve in that aspect as well. So all three indices worked well on the wind-driven fires, obviously, but they didn't work very well on the fuel-driven fires. And that's pretty easy to understand only because it's only one aspect. If you're only looking at fire weather, it's not going to take into account the fuel loading you have. We're not taking into account the topography, the steep slopes, the complex terrain, and all of that. So yeah, so my future work. So what I'm doing is I'm analyzing the percentiles for the three indices during the 4 fires. So that's going to be a part of possibly my presentation next week at the Albuquerque, if anyone's going. And then I'm going to calculate hot, dry, windy, Fosberg Fire Weather Index, and the LFPW, and I'm going to grid it over WRF because I have some WRF runs, and going to grid that over the area, at least for the Thomas Fire, because that's a fire that I study more so than the other ones. And I want to do a further analysis into more indices because I think it's beneficial, because we all have the same goals. We're trying to predict how a fire can get potentially large, and if we can understand getting to that, if we can get to that point to where we can actually protect land or property or the firemen that are going out there, then that's going to be the main goal, and that's where we're all leading to. And also exploring the indices to incorporate live fuel moisture along with dead fuel moisture to maybe add that to NFDRS or kind of look into adding all of that together. Thank you.
Okay. Are there any questions? We have time for one question for Heather.
Scott?
Well, I already asked one, so if you want to go. I can ask. All right, thanks, Heather. Is this thing on? Oh, you can hear me? All right, yeah, so you showed a fascinating slide on the Thomas Fire. If you can go back to that. So I know that Fosberg Fire Weather Index and the LFPW they both kind of square the wind, so they're highly sensitive to wind, but there's a divergence between Fosberg and LFPW, and I'm suspecting, that's obviously dew point depression. So do you know what was kind of happening in that situation right after, I guess, the fire started?
See, that's something that I've been starting to look into, because there is a difference between those indices and how that one just takes in relative humidity, well, Fosberg's does. So I think that's somewhere where I'm going next, because diving into more of the background into the SAW-T, because the SAW-T I recently added because it was interesting how it was so similar to the other indices as well. So we can talk offline if you'd like to talk about that as well.
Yeah, thank you.
Okay, thank you. Let's thank our speaker. Thanks, Heather. I put this program together, but I got to make sure that I'm on the right. I know what I'm doing here. Yep. Okay, our next speaker is Richard Bagley, and he is a meteorologist with PG&E. He did his bachelor's and master's degree here at San Jose State, and he'll be talking about nocturnal drying events in coastal California. You have to adjust that, and then just click through.
All right, good morning, everybody. Yeah, so today I'll be talking about nocturnal drying events in coastal California. And this is a unique phenomenon in which some of the driest air in the United States originates off the coast of California, above the marine layer, and it affects and moves inland overnight with that marine layer, submerging the higher elevations in single-digit relative humidity. I first learned about this through folks at CAL FIRE when I was an undergrad, and they were very well aware of these situations, but they didn't really know the cause behind it. So I went on to study these for my master's, and I'll share some of the results with you. So nocturnal drying is simply defined with single-digit relative humidity coincides with dew points less than minus 10 degrees Celsius, occurred between 8 o'clock p.m. and 8 a.m., primarily occur during the summertime. And climatology was established using 30 stations over 15 years, primarily focused across the upper slopes, the terrain in coastal California, as well as Sierra Nevada and Oregon. And NFDRS RAWs were used as much as possible. So here's a map representing the spatial distribution and frequency of these events. And you could see they're really concentrated along the coastal strip of California. Some of the larger circles, that's the event count of 20 to 30 times per summer. So these happen quite often. Extending all the way generally south of the San Francisco Bay Area. Occurs in the LA area, San Gabriel Mountains, San Bernardino Mountains, as well as San Diego County, Mount Otay. And if you focus on this portion right here, kind of zoom in on the Bay Area, you can notice they're concentrated above 2,000 feet. You can see we have, this is Middle Peak, which is Mount Tamalpais, Mount Diablo, Rose Peak, and Ben Lomond. They're all above 2,000 feet, and they experience the highest frequency of these drying events. So kind of focusing on those four upper elevations, here's the frequency time of year. The overwhelming majority of these occur during the summertime. They start picking up in June and really peak July, August, September, and then start dropping off in October. And looking at the time of day, so the lowest relative humidity doesn't occur in the middle of the afternoon in these elevations. It occurs overnight. And winds associated with these, they have a definitive onshore component, right? Generally between northwesterly and southwesterly. Rose Peak there in the bottom right, that's not as exposed as the remaining sites, so the winds there are a little more terrain driven. But notice there's really no eastern component to these winds. Wind speeds aren't especially strong. Sometimes they could reach above 20 miles an hour, but generally in the 5 to 10 mile an hour range. How dry does it get? Here's relative humidity. Just want to highlight a few things. We're looking at Los Trompos, Ben Lomond, Middle Peak, Rose Peak, and Mount Diablo. Again, these are all the Bay Area sites. Kind of organized from lowest elevation to highest elevation, left to right. The red line, that's the average summertime relative humidity, so about 30 to 50%. The red circle at the bottom, that's the average relative humidity during these nocturnal drying events. So we're talking about 5% range. The red tick at the bottom, those are minimum values. 1-2% is how dry it can get. I've actually seen 0% at Mount Diablo once, less than 0.5% RH. So these aren't really necessarily localized events. Oftentimes you'll see them occurring at all or couple of these sites at the same time. So kind of indicative of a larger scale weather forcings in effect. So the Bay Area has a pretty good setting to study kind of synoptic events. We have several groups of RAWs, right? The same primary ones I've been discussing, and balloon sounding launched from Oakland Airport, right from the middle. So 87 significant events were identified subjectively between 2004 and 2015. And a synoptic composite, or just kind of average of the weather pattern during these events, was looked at. And so here's 500 millibar and surface analysis. This might as well be the synoptic composite for summertime in the area. You notice the darker, bolder lines are the 500 millibar height, so you can see subtropical high pressure there over the desert southwest, and a weak shortwave kind of approaching northern California. And the thinner lines at the surface, that's Pacific high, the dominant summertime feature. And then looking a little more closer at these, this is a 925 level, about 2,500 feet. You can see a strong low-level jet there, another very common summertime feature. And that red shading represents divergence, so you have a large mass of air being removed from that area. And then at the 500 level, notice a zone of convergence, air converging. So those two features amount to air sinking from the higher elevations to lower elevations, warming, drying. And looking at the relative humidity field, you can see that source region dry air, this 925, forms right to the east of that low-level jet. And again, this is during the nighttime, so you can see that inland extent has spread through that coastal barrier in the Bay Area into the Central Valley. And it's even more well-defined at the 850 millibar level. It's about 5,000 feet. And even 500, still dry. It's just that whole column above the marine layer is just incredibly dry. And then a composite sounding from those events. The signature for these, right, for this sound, it's like a football field goal post. You can see the temperature is on the right, dew point is on the left. And where they're very close together at the bottom, that's indicative of the marine boundary layer. And then right above that marine layer is that region of dry air. And also notice the wind barbs on the right. The wind direction is westerly. That's your onshore wind component. Again, speeds aren't that strong, around 5 miles an hour. I want to talk about the Devil Fire incident. This happened August 29th, 2003, associated with the nocturnal drying event right here in our backyard. It's a part of the Santa Clara complex, originally started by lightning strikes. And then a couple of days later, Devil Fire is one of the northernmost fires there. This is a satellite image from the day. You could see some of the marine layer well established off the coast, kind of fingers shooting through the bay there. Well, this resulted in one of the largest fire shelter deployments in U.S. history. 52 crew members, actually an inmate crew was involved on this fire, For those who are not aware of the fire shelter, it's kind of a last resort fire crews will take. It's a small individual-like tent shelter. They clear the area of brush, deploy these shelters, and the fire kind of goes around them, hopefully. Thankfully, no deaths, just really minor injuries. But what happened in this situation, they were trying to do a backburn. You can see the red shading right there is where the fire was actively burning. And that region circled is where they were set up, trying to initiate a backburn to go into that fire. They had no luck throughout the night, so they're just kind of hunkered down there. And then the dry air settled in, northerly winds came in, and the fire took off. So they were forced to deploy their shelters. From the report, there were 95-foot flame lengths, spot fires over 1,300 feet, and hard upslope runs over 980 feet in 2 to 3 minutes. So this fire went from nothing to very critical situation in no time. Here's a look at the time series. This is from Rose Peak nearby. That vertical line represents the time of the fire shelter deployment. So you can see this is kind of the 5 days surrounding it. You can see the diurnal temperature change, and then you can see these really two abrupt plunges in in relative humidity and dew point. One, actually, there was a nocturnal drying event the night before this shelter deployment. It didn't really seem to have the same effect on the fire. But both of them happened right shortly after midnight, middle of the night, and relative humidity abruptly lowers. Fire shelter deployment was around 0:01 in the morning. And then you could see daytime, right? once the sun comes up about 0.6 or 0.7, you have improved relative humidity. So it's kind of really counterintuitive because typically you would expect higher relative humidity during the nighttime and lower relative humidity during the daytime. But in these cases, exactly the opposite. And here's a mesoscale model WRF analysis of the Devil Fire. We're looking at, we're kind of looking north. You can see Santa Cruz on the left, San Jose kind of right in the middle of the Santa Clara Valley. The top one is moisture. You can see the blues, that represents your higher relative humidity associated with the coastal stratus. And above that, those yellows, those are low relative humidity, 10% values. And the bottom picture, that is potential temperature. And that's just kind of showing where the lines are closer together. That's your inversion height. And notice how that inversion is terrain following. So during the daytime, you actually get upslope flow, bringing moisture relief to the higher elevations. But at nighttime, a couple of things happen. First, that marine layer will advect inland. And second, the boundary layer, that will settle overnight and allow those upper elevations, those higher elevations, to be exposed to that extremely dry air. The Soberanus fire was plagued with these nocturnal drying events. And simulations for this showed the pretty much same thing happening. You get that higher moisture content during the daytime, and that boundary layer collapses overnight, and that RH values really plummet. Here's a sounding from the Devil Fire. Again, this wasn't really an extraordinary dry event. Relative humidity got down to 5%, which isn't exceptional, but really enough. And then here's a satellite image on the right, and you could see that well-established fog bank and the inland extent as well. Just kind of wrap it up here with some of the extreme values that can be reported. This is Mount Diablo at the top. This is from last year. Dew point scale, temperature on the left, you can see minus 100 degrees dew points. And again, single 1% RH. Meanwhile, Los Trampus, which is about 1,500 feet and very close to Mount Diablo, had relative humidity at 100%. So you can really see this contrast in fire danger. You have virtually no fire danger at certain elevations, and then critical fire danger at the higher elevations. And here's a sounding from that day. Again, really that classic. You see the marine layer, the small dew point depressions near the surface, the dry layer aloft. And right on cue, we had some nocturnal drying event last night. If you look at this morning's sounding from Oakland, you'll see something similar. Rose Peak, Ben Lomond got down about 2 to 3%. So this very common feature. It has more to do with fire behavior, not really fire danger, meaning it's going to exacerbate existing fires. It's just simply a smaller geographical area that this affects. So it's not going to be associated with a lot of fire starts. But very, very critical for fire agencies to be aware of, and of course, fire planning. It's tremendously difficult to forecast. But just to summarize real quick, the source region of extremely dry air originates off the coast, right above the stratus deck, so about 5,000 feet. And that dry air advects inland and moves inland overnight with the marine layer. And the events are more pronounced in the San Francisco Bay Area, but occur really up and down the coast of California. So just some of the forecast challenges. It's really similar to forecasting for stratus, right? You have to estimate what the inland extent is going to be, what is that height, what elevations are going to be susceptible to drying. And really the biggest challenge is the offshore moisture quantification. We just don't know how dry that air is, where that source region is. Mesoscale modeling is another challenge because models, they know the dry air is there. They just don't know how dry it is. They just have a difficult time picking up on it. But I'll leave it here for any questions. Thank you. Yes.
I want to thank you for modeling or doing the Devil Fire. That SEU complex had a lot of it on the various fires in that complex. They saw the anti-fire south of that, and there's not much that's been written or even documented about that. It was kind of kept quiet and can't find much on it at all. So it was pretty interesting. Being there, it was setting up in between the hour intervals that we were taking weather out there. So it's set up pretty quick. We always just called it a thermal belt. We got a thermal belt lowering onto the fire now. But it's a pronounced, drastic change when they're trying to put fire in the ground and only the grasses are burning, not brush isn't taking. But as soon as that RH took off, fire whirls, brush taking off, and it starts running pretty hard. So, yeah, it's a dangerous thing that we talk to our firefighters about, and not a lot's been talked about that area. But a lot of seasoned CAL FIRE people always said, "Oh, these fires on that range is pretty tricky and technical sometimes, especially at night." So, thanks.
Thank you.
Oh, so what's happening on meteorologically on the days of these nocturnal drying events that isn't happening on the average day? As you showed, the synoptic weather pattern is typical summer, marine layer, stratus coming in, typical summer day, but something special is happening when these nocturnal drying events occur.
Yeah, I mean, they can occur pretty much anytime you have the marine layer established and moving inland, but they're most common kind of days like today, kind of what's associated with an onshore push, right? Kind of the tail end of a warm spell. You get that marine onshore push, a little more inland extent. But there are many different kinds of flavors, right? They could last for just an hour. They could last all night. But just a change in elevation, it's all. I mean, there's a lot to go into it. But yeah, it's really kind of when you get that good inland push, but they occur quite commonly. But meteorologically, it's at that same setup. You get that dry air established offshore.
Sorry, I sprained my ankle the other night. Anyway, stop being a klutz here. No, it's great that somebody else is using the field goal post terminology because I've used that before. It's good to know that I'm not crazy. But I was curious if anybody's looked into a connection between the severity of these and perhaps subsidence inversion development, that type of stuff, in terms of providing the really low RHs up above the marine layer versus a run-of-the-mill type event.
Right. Yeah. No. Absolutely. Still a lot of work left out there on the table that can be followed up with. Yeah. Definitely subsidence. I also think that, now I haven't proven this, but I also think that a lot of this dry air will actually originate off of far northern California, maybe north of Shasta, right at the top of that thermal ridge that gets developed and gets kind of recirculated. Kind of evident when we had some of the smoke. You could see it last year. It'd move offshore, and they would come in with the sea breeze overnight. So when we do get these critically low dew points in RH, I don't think it necessarily all be related just to subsidence. I think there is a distant offshore component with these. I haven't proven that yet, but I think there is something there to it.
Great. Thank you, Richard. Let's thank Richard again, and we'll go to the next speaker. Okay, we're actually right on time. I don't know how that happened, but we are. I need these. So 2 more talks, and then we're going to be able to have an hour break for lunch. So we're going to start our break at 11:40. I know we're skipping a coffee break. I think we're out of coffee anyways, so just hang in there. We're almost through to the afternoon. Okay, next up is Matthew Brewer, who is a first-year master's student here at San Jose State in meteorology. He received his bachelor's degree in atmospheric science at SUNY Albany and came out to California to study wildfires and fire weather. So, here you go.
All right. So, like Quick said, I'm Matthew Brewer. I'm a first-year grad student here at San Jose State, and today I'll be talking to you guys about the meteorological conditions associated with the campfire extreme fire behavior. So, quick outline of my presentation, I'll just give a little background on the campfire, give a synoptic scale overview of the conditions, then we'll look at a high-resolution atmospheric simulation, and then move on to look at some model observations from raw sites and do some model verification, and then wrap it up with summary and future work. So just getting into the background for anyone who doesn't know, the campfire started on November 8th, 2018 at approximately 6:33 a.m. It was contained 17 days later on November 25th, 2018. Total acres burned was 153,336 acres. There was 18,793 structures destroyed, a death toll of 86 civilians with 3 firefighter injuries. And as you can see on this map, right here, right here is the first day of the fire on the 8th, where 69,000 acres burned in one day. And in the boxes is some raw stations surrounding the campfire. So moving on to the synoptic scale overview, first we'll look at October precipitation anomalies. So for the month October, there is a departure of -2.5 to -1.5 inches of precip based off the long-term mean from 1981 to 2010. And the lack of precip that helped to give, or didn't provide any relief for already dry fuels. And you can see that in the 100-hour fuels that was calculated based off NFDRS. So you can see at the start of the month, the fuels were high, and throughout the month they decreased with only a little bit of relief at the end of October here. But throughout the first week of November, the fuels decreased, reaching a relative minimum of between 4%, 8% during the first day of the fire. So moving on from looking at fuel moisture contents, we'll look at the upper level flow pattern. So this is the half-degree GFS analysis, 700 millibar relative humidity and color fill, geopotential heights and contours, and winds and barbs. So first off, you'll see a shortwave here, which was propagating over the Pacific High. Look at here. And as this shortwave continued to propagate over the ridge, we started to get an anticyclonic wave breaking event. And this anticyclonic wave breaking event, here we started to get cross barrier flow, or the flow from the anticyclonic wave breaking like this, which led to strong cross barrier flow across the Sierra Nevada. And this condition is very conducive for getting strong downsloping winds on the westward side of the Sierra Nevada. So this is at 10 a.m. on November the 8th. And this condition persisted throughout the day and into the evening. And as the anticyclonic wave breaking continued to propagate eastward, the flow weakened, but you still have the curvature in the flow, but much weaker winds at crest height. So this is when the downsloping winds started to subside. So in addition to the upper level support, or upper level flow, there is low level support from the synoptic pattern. As we've seen in a lot of other talks, there was this thermal ridge located over the Central Valley of California. And this, or inverted trough, this inverted trough helped force northwesterly winds down the Central Valley, in addition to providing extra forcing for flow to come off the Sierra Nevada. And this condition persisted throughout the day. So you'll see the northwesterly flow in a lot of the raw stations that were located in the Central Valley. So moving on from our synoptic scale overview, we'll look at the high-resolution WRF that I ran. I used model physics similar to the operational NOAA-HER model. It was a 48-hour simulation with roughly 12 hours for spin-up. And I used 3 domains. You can see here the outer domain of 3 kilometers, an inner domain of 1 kilometer, and my finest domain of 1/3 of a kilometer grid resolution. So what we'll look at first is my 1 kilometer WRF domain. And here we have 10-meter winds and vectors and 2-meter dew point temperatures. And overlaid on top of this is KBBX Beale Air Force Base, California, level 2 base reflectivity. And just to give some context, you can see the approximate location of Paradise, as well as roughly the location of the ignition point of the fire. So throughout this animation, be on the lookout for the northwesterly flow down the Central Valley being forced by the surface inverted trough, as well as the strong northeasterly flow coming off the Sierra Nevada due to the downsloping winds from the upper level anticyclonic wave breaking. So getting into the animation, first off, you see there's a lot of ground color early in the morning, but once the plume starts to show up on the radar, it's very distinct, and you can see a first puff coming right off the plume as the fire intensifies. In addition, you can see how elongated and well-defined the plume is with the strong wind direction or wind speed from the northeasterly flow off the Sierra Nevada. And as the winds start to subside a little bit, you can also see that the plume starts to disperse a little bit and be less defined as it was when the winds were strong first thing in the morning. And we'll go through this animation again so you can look for that. But you notice when the plume really shows up on the radar, there's a first big initial puff. You can see it propagating northeasterly with the predominant wind direction from the downsloping winds off the Sierra Nevada. You can really see how well defined the plume is here, and then as it starts to get dispersed as the winds weaken from the downsloping winds starting to subside a little bit. So we'll move on and look at some particular times. Again, just to give you some context, here is roughly location Paradise and the ignition point. So this is at 7:20 in the morning. This is roughly when the plume starts to become visible first on the radar. It's easier to tell now because I know the plume was there, so someone might not have noticed that if they're just looking at the raw radar. But just 20 minutes later, you can really see the plume start to show up much more distinct on the radar. And you can also see how the strong northeasterly flow coming off the Sierra Nevada, how much stronger it is, roughly 10 meters per second or greater in the area of the campfire. And you can really see the winds here. As a closer view, you can see that the smoke plume itself is almost directly aligned with the northeasterly flow coming off of the Sierra Nevada from the anticyclonic wave breaking. So moving on to a couple hours later, we'll look at, this is 11:30 a.m. local time, just a number of 3 hours later. You can see how much more defined the plume is. And giving a closer in view, you can see how the plume is very much directly in line with the predominant northeasterly flow coming right off the Sierra Nevada from the anticyclonic wave breaking and downslope windstorm. In addition to this, you can also see there's a fire front structure showing up in the radar reflectivity. This just looks similar to the classic wind-driven fire model that you see of a fire front progression from wind-driven fires. But you can see how strong the wind is at this period and how elongated and centralized the plume is, with the highest reflectivities being really centrally located, and just a big fall off from very high reflectivities to weaker reflectivities. And this is compared to when there's a period of weaker winds at 1600 local time. You can see here zoomed in winds of less than 10 meters per second, probably roughly 5 meters per second in this time period. And the winds, or the plume, is much more dispersed. There's much more gradient between the high reflectivities and the lower reflectivities, and it's much less elongated compared to the previous time, which you can see here, how the plume is much more aligned with the winds, very condensed, and not as dispersed. So moving on from looking at the surface conditions, we'll look at a cross-section of winds. So I used my high-resolution domain for this, a third of a kilometer. And I took the cross-section roughly northeasterly through the predominant wind direction through Paradise. And the streamwise winds were calculated at 30 degrees. This is similar to what Carrie had showed earlier, but this is for the campfire instead. So starting off with the animation, you can see the strong winds starting off very early on. This red dot, kind of hard to see, this is roughly the location of Paradise. But you can see that there's constant strong winds of greater than 10 meters per second throughout the entire simulation. In addition, you can see the strong northeasterly flow over the Central Valley, which is helping to continue to propagate the smoke plume north or southwestward, like we saw in some of the reflectivities. So we'll let this play through again, and you can really see the very strong winds early on in the morning, right as the fire started, which really helped to make it very explosive fire, very wind-driven. And you can see the rotors here, indicative of a strong downslope windstorm. In addition, you would expect this since there's the northeast or northwesterly flow due to the surface inverted trough here. So we'll let this finish playing through, and then we can look at some RAWS observations. And so I used 3 RAWS sites. The Openshaw RAWS site that was located more in the valley, the Jarbo Gap RAWS, and the TR-145 RAWS site. These were the same RAWS I used for the 100-hour fuel calculations. There was very limited site selection due to a lot of outages, so unfortunately this is the best I have for the RAWS sites. So first off, we'll look at the open shaw RAWs, which again, like I said, was located in the Central Valley with the northwesterly flow. And comparing this RAWs site, here you can see the predominant northwesterly flow during this time period and very weak winds, roughly 2 meters per second. And this is in good agreements with what the my wharf run was saying, or simulating, with the weak northwesterly winds, much less than 10 meters per second during this time period. So moving on, I also compared it to the Jarbo Gap RAWs, and this was at 1600 when there was the lull in the wind speeds. Here we got less than 4 meters per second and more northeasterly winds. And this is in good agreement with what the wharf was resolving with the weaker winds, much less than 10 meters per second, the northeast flow. So it's just helping to show that the wharf is actually resolving what was actually happening at the surface pretty reasonably. So finally, we also have a RAWS located on the top of our mobile LiDAR truck, like Craig showed earlier. And you can see the weather station here and here. This was actually where the samples were taken. This was on Pence Road, just south of Paradise. You can see helicopter flying really close to us. There's a pond where they were picking up water. So just looking at the wind speeds at this time when we were sampling at 1900 local time, we weren't experiencing very gusty winds where we were located. Pretty weak winds, but very constant. As you can see, roughly between 2 and 4 meters per second, but with the very constant northeasterly winds located at the surface. And this is in good agreement with what we were experiencing here. This vector shows our approximate location of where we were sampling with the mobile LiDAR truck, which is we should have the northeasterly flow pretty weak, which is pretty good agreement with what we were seeing from the RAWs. So in addition to just having the RAWs on top of the truck, we also took LiDAR wind profiles to get the vertical profile of wind. And again, you can see our approximate location right around here where we're taking these vertical profiles. And comparing these profiles to what the wharf was seeing, you can see our vertical profiles of the winds were showing between roughly 17 and 10 meters per second throughout the lowest 1,000 meters. And this is in pretty good agreement with what the wharf was seeing at this time period. And this black box indicates roughly the same depth that the LiDAR was recording, with pretty good agreement between roughly 10 and 20 meters per second. So the wharf might have a slight high bias, but it's showing that it's resolving what's actually happening in real life with reasonable approximations. So moving on, just a quick summary. On a synoptic scale summary, there is less precip than climatological normal, which gave little relief to the already dry fuels. And from this, there was the relative minimum in the 100-hour fuels just prior to the ignition. Additionally, there was a shortwave ridge propagating over the Pacific High, which led to the anticyclonic wave breaking event, which provided the upper level support needed for the downsloping winds. In addition to the upper level support, there was the surface inverted trough, which provided the synoptic support for the northwesterly flow down the valley and additional forcing for flow off the Sierra Nevada. And a summary of the wharf, our 1 kilometer wharf domain was able to resolve winds well compared to RAWS observations. Additionally, the wind field helped to show how wind-driven the fire and the smoke plume were. Our vertical cross-section shows the strong, persistent downsloping winds experienced throughout the day on the 8th, with the highest wind speeds located just above the surface. And our wharf streamlined winds were in similar agreement to what our LiDAR wind profiles were showing of between 10 and 15 meters per second. The model does have a slight high bias. And just some future work, we'd like to add some more vertical levels to the wharf run. In that wharf run, there's only between 8 and 5 vertical levels in the lowest 1 kilometer. So we'd like to increase that to 15 to 20. We'd also like to implement an even higher resolution topography and land use field to try to resolve the topographic flow better. And finally, test a number of different model physics to see if we can resolve the winds better, particularly look at the planetary boundary layer physics schemes and the surface layer physics schemes. And with that, I'll take any questions.
Great. Hi, Lisa.
Thank you. Very interesting. Can you talk about geography a little more specifically with reference to Jarbo Gap? Apparently, it's just famous for its winds there. And then second question would be, I'm a journalist, I've heard different reports of what the wind speeds were at Jarbo around the time of ignition. Do you know what they were?
I could tell you what they were, and if we go back and look just at that figure. One thing to note, however, is the Jarbo Gap is not the best site to use just based off the fact that it's a gap, so you're going to have stronger gap flow, which might not be necessarily very representative of what's actually happening closer to the fire front. There's going to be much stronger winds located in the gap flow because you get the funneling of the winds.
The ignition was pretty close to Jarbo, wasn't it?
Yeah, from what I know, it's very close to Jarbo, but I don't know much about the actual site itself. And it's hard to say because there's a lot of, like, the topography has strong influences at the surface. So it's hard to say. That's the thing.
Hey, sorry, I'm stealing all the questions. Scott, PG&E. Just a quick question on your model initialization. Did you use like GFS 27 kilometer?
I used NAM 12K.
NAM 12. So one of the things I would potentially encourage you to do, maybe, and maybe I'm jumping ahead to the future research side, is to look at, you know, different initializations and which ones, you know, capture the event the best. But
Another question for Matt?
So Jarbo Gap in Concow area has a long history of extreme fire weather, fire behavior. Did you do a forensic analysis of any of those other major fires?
I have not taken a look at any other fires. Just particularly, I was looking at the campfire and simulating the campfire. That would be something interesting to look at, see how the winds in Jarbo Gap are related to the extreme fire behavior located in the area, if there seems to be a correlation.
Great, thank you, Matt. Okay, so we're down to our last talk for the session, and lunch is going to be brought in just a few minutes, so we're right on time. Let me get you sorted here. Okay, so it's a pleasure to introduce Dr. Ali Tauhidi. He's a wildfire scientist at One Concern, a company here in Silicon Valley. Ali received his PhD in applied fluid dynamics at the Clemson University, and his research specialties are in wildfire spread mechanisms, firebrand research, and aerodynamic properties of fire spread.
Hi everyone. Thank you, thank you all for being here today, and thank you, Dr. Clemens, for introduction. Today I'm going to talk about review of firewall science, which is a work that I've done before joining One Concern, when I was a postdoc and working with my colleagues, Dr. Goldner and Dr. Yao. And before we move on to the details of the talk, I would like to thank Fire Weather Research Laboratory for putting together this exciting and interesting workshop and giving us the opportunity to present our work. So today I'm going to go over formation mechanisms of fire wheels and also talk a little bit about their structure. But before I do that, we do need to realize why do we study fire wheels, and not just because they are very different from burner fires or pole fires, because they have some characteristics that really differentiates them from normal fires, and they have consequences. They present very intense heat and radiation when they form. They have a very high vertical axial velocity, which causes or might have the potential to cause long-range fire spotting, which poses a lot of dangers and threats to firefighters. And their abrupt and sudden formation, when they form, you can't really deter them from forming. And again, that itself causes a lot of problems for our firefighters and people who are in that area. With that, I would like to give a very brief definition of fire wheels. And as you all know, they happen to occur in a variety of different scales spatially. So coming up with a definition that can be extended to all the scales is really difficult because it encompasses a lot of different parameters. But a very simple thing that we can say is whenever you have localized intensification of combustion, which is coming along with the flames, swirling flames, and associated plume on top of it, you can call that phenomena a firewall. And that can be extended to firewalls that we have seen in lab with flame length of 1 or 2 centimeters, all the way to large wildland fires that you see in the field. Firewalls have been studying extensively in fluid dynamics community. They've been called fire tornadoes, fire devil, fire nado, fire twister. I really don't know if these terminologies really accurate, but they're all referring to that simple definition that we introduced here. Unfortunately, they are really common in urban conflagrations, and that's because of the characteristics of the urban area, which has a lot of potential for cavity flow. And once that happens and you have a swirling mechanism, it is highly likely that you end up with a fire wheel. Some of the historic events that have happened, they include the Hifukushu auto fire wheel, which happened in 1923 in Japan after an earthquake, and caused a lot of fatalities. 38,000 people died. These phenomena have been seen in Canberra, Christchurch fires in New Zealand, and as I mentioned, they have been studied very extensively in the field, but we are still not really understanding them well, and that's mainly due to the fact that studying fire is really hard. But fire wheels are even more challenging, and that's because of it's really hard to probe these phenomena because they are inherently unsteady. They are periodic. You can't even put a probe in them to get good observational data. But if we go back to the literature, there have been 2 major studies that really moved the field, and we have started to get some theories out of it. One of them was done by Byram and Martin in US Forest Lab, where they studied formation of fire wheels in enclosures, as you can see on the left. And the other one later is done by Emmons and Ying. I guess they were in Harvard. And they generated the fire wheel by putting a rotating mesh around the pole fire, and then developed some theories around this. If you look at the literature and we summarize the essential conditions for fire wheel formation, we can kind of summarize it in these 3 factors. You do need to have a thermally driven fluid sink, which causes a negative pressure. And by that, I mean a simple source of fire that moves the air on top of it and causes the negative pressure around it. Then you have to have a swirl or eddy generation mechanism, which is combined with a surface drag for developing the radial boundary layer. Unless you don't have any of these, it is very unlikely that you see this phenomenon. And I'm showing this video to kind of emphasize on the presence of these 3 essential conditions when these things happen. And as you can see, we not only see the swirling mechanism and thermal sink, but also these streaks that we see at the boundary layer really pronounce the presence of the radial boundary, which is sometimes missed in the literature and its importance. And then next, the car fire, the fire that everyone knows here happened very recently. Again, you see the presence of the radial boundary layer, very intense axial velocity, which caused a hydraulic jump in the atmosphere. And unfortunately, we had 1 fatality. I just want to draw your attention to this very bright object that is being entrained into the fire plume, which not only shows the intensity of the radial flow through the fire column, but also shows the high potential of the long-range spotting. I don't know if you can see it. And the size of this particle is very significant if you compare the size with the houses in the image. So having said that, and discussing the formation, essential conditions for formation, fire wheels can happen over a variety of forms and scales. You can generate them in lab, for example. Case A and D are generated in our lab in Maryland. 1 or 2 meter size, and the D case was only 1 or 2 centimeter over water, actually. And you can even see them forming from in the flanks of the fire plume in the form of shedding vortex. These are also called fire wheels, and they don't necessarily need to have the swirling flame inside them. They can happen in over the discrete area of fires, and also, again, any configuration that gives you the potential for swirling flow. If I want to quickly go over the physical mechanisms that are involved in this formation, we can start with the initiation of the fire wheel from a normal pool fire. As a normal pool fire is happening, the hot air tends to go up and creates a vortex ring. And this vortex ring, as it goes up because of the velocity difference and also density difference, if it observes or if it receives any swirling mechanism, this ring tilts and becomes a vortex tube. And after that tube receives persistent swirling, it starts to be stretched, and at some point all of these tubes start to converge to each other and elongate the flame. As you can see in this evolution image, from a very small pool fire all the way through stretching and flame elongation. And these two mechanisms, which are two main mechanisms of the fire wheel formation, tilting and stretching, can be intensified by any baroclinic term, where you have this eccentricity of mass concentration from your origin or centroid of the sourcing, or any traction forces, for example, boundary layer or electromagnetic fields. Knowing the physical mechanisms that lead to formation of fire wheels, we can kind of classify them based on one characteristic, actually, on a high level. The ones that you see the flame or the flame column on top of the source, and the ones that there is like an offset of the flame or the smoke column from the source. Then there's another classification, which is basically talking about the types of these fire wheels. And that happens when you have open configuration or enclosed configurations, where you see type 1, which is the stable on source fire wheel, similar to what you are seeing as in the video on the right, and type 2, which is the unsteady or periodic fire wheel, which kind of moves along a line or flanks of the plume. And type 3 is again a stable, but kind of forms off source of the fire wheel. And there are some studies that kind of characterize the fire wheels based on the length of the flame. And this image kind of summarizes all the types, where you can see the formation of these different types. For example, in the L-shape configuration or any kind of configuration that you see you have the potential of the cavity flow, you see type 1 persistently happening at the very ends of it, and also type 2 in the flanks of it. and sometimes at the end, very close to the main direction of the wind field. These are periodic, they're not stable. And also you might even see type 3 where the flame is entrained into the middle of the stream, and you see kind of a stable condition there. As I mentioned, you see type 2 being generated as the vortex columns on the flanks of the fire. You can see the type 1 forming over discrete fire area, which is mainly due to any asymmetry in the flow field. Or you can see it in over the lee side of the hills, which is usually type 1, but sometimes people have reported type 2 as well. And fire wheels over the line are mostly type 2, which are periodic. They move along the line. So I guess I kind of summarized the different types and formation mechanisms. But if we want to look at the structure of the fire wheels, this picture can kind of summarize it. Basically, you would have a region, or the flame type is the non-premixed flame, where you have the reactions being really controlled by the turbulence mixing at the edge of the core of the fire wheel. So basically, you have a core which is swirling, and then outside of the core, you would basically have a irrotational flow field. But almost everything is happening around that edge and within the core. And again, the radial boundary layer is really important. And as I mentioned, a lot of theories are missing on the importance of the radial boundary layer. If you want to talk about the velocity distributions, the azimuthal velocity, these are like normal velocity distributions. But what you see inside the core, especially in the azimuthal velocity distribution, is the Berger's vortex theory kind of characterizes it really well. And also you would have a Gaussian distribution at the axial level with some minor differences at the very edges. But this is the velocity field structure base that we can talk about. Also, if you look at the structure vertically, you can break down the height in 3 main zones. The zone where you see a continuous flame. And this is the zone where you get to have maximum radiation and maximum heat, which is very dangerous, being close to this zone. And then you would have a zone where you see intermittent flame. And then after that, it is basically becoming like a plume, a normal plume, which depending on the amount of circulation or circulation magnitude, its virtual origin can be either in the intermittent flame or continuous flame. Then on the radial axis, we can characterize it based on the radius of the excess temperature that we can observe, or radius of the azimuthal velocity, where we observe the maximum azimuthal velocity, or the radius where we can kind of characterize the average axial velocity, which are respectively shown by B sub T, B sub W, and B sub A in these profiles. Then at the very last, I want to emphasize on the radial boundary layer and kind of compare the difference between a normal pool fire, where you don't have the ability to kind of have an Ekman layer being formed at the base, whereas the case that you have that ability to have an Ekman boundary layer. For a normal pool fire without Ekman boundary layer, the flame forms and you see the normal behavior. But once the Ekman boundary layer forms, which is a perfect balance between the drag force, hydrostatic pressure, and also Coriolis, which is here in the smaller scales, the rotation, it kind of tilts the frame and bends it in a way that it can be more attached to the fuel. And that causes a lot of heat generation and also intensification of the combustion reactions, and kind of creates this column that you see. This is a experimental result, comparing the different behaviors that I just described from the Washi's work. And as you can see, this Ekman boundary layer kind of do the same behavior that I just mentioned. With that, I'll leave the conclusions here, and thank you all for listening. I'll be happy to take any questions.
Thank you, Ali. I invited Ali to give a presentation here because I thought fire world science would be really useful for this community, so thank you. We've got time. They're running slightly behind on delivering the lunch, but it'll be up. But let's do a little bit of questions, and then we can do break and stretch our legs and get on the patio. By the way, I didn't do this in the beginning. For safety, you want to exit out the doors here, and you go down the stairs. And there's also an exit down this hallway here. The signs are exit route on the side here. Bathrooms are right next to the room here through the hallway. Okay, question here.
Very good presentation. I think for everyone in the Bay Area who watched the fire whirl during the car fire, the operative question that comes to mind is, could something like this happen in the Bay Area? I'm really a geographics guy. I'd really like to know if weather patterns have been tracked enough that this is potential. Now, just a couple of weeks ago, we all saw on TV a video of a wind whirl in a schoolyard, and all you'd have to do is add fire to that, and you'd have a fire whirl. But I'm just curious to see if there's been any tracking. Would these potentially occur outside of the inland dry areas where people can say, oh, that's in Redding, that's a very hot climate out there. Are these being seen along the coast down at Santa Monica in Southern California? If you could give a little bit of color on that, that'd be appreciated.
Sure. Very interesting question. Again, it comes back to these three essential conditions that I just mentioned here, and persistence of these conditions, all together. And once you have all of these, you have a persistent source of fire that is happening and a persistent source of swirling mechanism, and that ability to for the boundary layer to form. Yes, there's a potential always to for some phenomena like this to happen.
Here's a question.
I know one concern has done a lot of work with earthquake modeling, but where are you guys with your fire modeling? Is that still working on that or done?
Yeah, actually, I joined One Concern just to after Nick, who's my colleague, sitting right there, to work on wildfire problem. And the way we approached the problem was to work on the response part of it, because the company's vision is basically addressing the resilience problem. And if you don't have a really good response model to the hazard, you can't really talk about other aspects of resiliency. So far we have been working on the response part, and hopefully soon you will hear about the products that we've been developing.
Just a little comment about this. In April of 1926, lightning struck a massive oil tank farm outside of San Luis Obispo, and the resultant fire developed a fire whirl, which traveled some distance from the fire. It struck a shack that two people were in, and they were killed. Not so much from, it was wind damage associated with the fire whirl that destroyed the shack that killed them, not inflammation of the wooden material. And that is the closest thing to deaths from a tornado known in California. So it wasn't meteorological, but it was two fatalities from a tornado-like feature, and it was a fire whirl.
Yeah. Thank you.
Another question.
This isn't really fair because I sit next to you at work and I can ask you this all the time.
Sure.
But I wanted to get your thoughts in front of the room, maybe on the effect of canopy, because that's obviously going to massively influence the drag and the ability for these sort of the radial boundary layer to form. So is there sort of a cutoff involved with canopy, and could you see these happening in tall coniferous forests?
It has definitely happened in tall, canopy forests. Actually, I had another video which shows formation of this firewalls over a canopy, and that was because of the fire which happened in a lake. And the reason that is happening in a lake was it was a whiskey factory very close to the lake. They got leakage, and the whiskey went on fire, and then it kind of transported to the the tall canopy. The height of the canopy definitely makes a difference, but it depends on how dense the canopy is there and how effective it is in kind of disrupting the turbulent, the development inside that boundary layer. If you can have that balance of force, which basically a command type boundary layer, and the other two conditions persistent, yes, it is highly likely to again have that phenomenon happening.
Okay, let's have one more question.
Could you explain the difference between perhaps a rolling vortex like we saw in the Valley Fire or maybe the Moonlight Fire and a fire whirlwind?
Rolling vortex? Oh, rolling vortex. Okay, yes. The physical phenomena are very similar, but the main difference that comes to my mind now is in some enclosure fires, mostly structural fires, it has been seen that the firewall can actually convert to like a rolling vortex, and that has to do with the ambient domain, velocity field, and how these things changes. And the main theoretical difference that I can think of now is basically referring to this. The rolling vortex, according to Kelvin Helmholtz theory, they always need to have ends. So it should be attached to some, ends. But what you mostly see is basically this part that is being characterized as the rolling.
Excellent. Well, thank you.
Thanks.
Let's thank all our speakers for the morning session. I know it was a long morning. We didn't have a coffee break, but I wanted to get all these talks in. And so now we have an hour break. Lunch is just about ready, just about a minute or so. Let's take this time. We'll be back here at 12:40, and you can take your food out. There's seating downstairs. There's outside. There's inside. So we'll meet back here at 12:40. So we're basically on time. It looks like people are getting settled back into their seats. Some people will be coming in. I want to thank all the speakers again for keeping their presentations on time. We didn't have a timer, and it worked out perfect. So thank you. Hey, Adam, real quick, I want to introduce everybody to Dean Kaufman. Michael Kaufman's our College of Science dean. He's going to give us a few words about the vision of the college and kind of came to visit our workshop here, and then we'll get started with our session.
Can I use that mic? Or?
Yeah, use this one. Whatever one you want to use.
Good afternoon, everyone. Like Craig said, I'm Michael Kaufman. I'm the Dean of the College of Science. And I wanted to mention a couple of things that are going on in this campus. First of all, how many of you are graduates of San Jose State University? Okay, we're scattered around here and there. Got a few more. How many of you has it been a while since you've been on campus? Any impressions? Yeah, it's changed a lot. We've had some pretty remarkable transformation here on the campus. Most of that transformation has been on the student support side, so the student Recreation and Aquatic Center, which just opened up last week. This renovated and expanded student union, which opened up, I think, about 2.5 years ago. And there's also a student wellness center on the other side, plus our landscaping is just looking a lot better. And yesterday, we broke ground on what will be the first new academic building at San Jose State in about 3 decades. Okay, so it's been a long time coming. That building is called the Interdisciplinary Science Building, and it will primarily be for wet lab teaching and research labs for molecular and microbiology, and organic and analytic chemistry, but it will also have spaces where computational science will go on broadly across the campus, and it's and lots of collaboration spaces where people who are working across different fields will be able to get together and brainstorm and solve problems on a massive scale. And of course, Craig and this conference are people, you are all people who are well versed in the idea that you can't solve problems from a single attack, right? Craig's not just gonna forecast fire weather and solve the problem of wildfire in California. You need firefighters, you need brush management people, you need forecasting, you need AI to figure out where the riskiest places are. You need social scientists to figure out how to get people to respond to emergencies and recover from them. You need the insurance industry, right? I know you got some of those people here in this room. Full disclosure, my spouse is in the insurance industry, and when Craig and his wife come over to our house, I may as well just fade into the background because they geek out over fire and insurance in the most extreme way. Anyway, you all know that this is an interdisciplinary problem, and we know it's an interdisciplinary problem. And I'm happy to share with you that we're in the final planning stages of an interdisciplinary wildfire research institute here at San Jose State University. Myself and several other deans, the Dean of Engineering, the Dean of Social Science, we're trying to get the Dean of Business involved, but we'll see if we can do that. But we'll be making some hires in the coming year to bring together faculty from across all of these disciplines who can approach wildfire from the myriad angles that are necessary. So I don't need to teach you about that. I'm sure I could learn a lot from this session. Unfortunately, my duties drag me off somewhere else. But I'm gonna do my best to make it to the roof of Duncan Hall at 4:30 so I can pick all your brains about all the myriad things that you do. So thank you for coming to San Jose State University today. Thank you for all the work you do for California, whether you're in industry or startup or academia. And I hope you have a great rest of the afternoon.
Thank you, Michael. Appreciate it. We'll see you at the happy hour on the roof. Great. Okay, let's start off our next session. So this session is, we have 3 speakers focused on numerical modeling aspects of fire behavior. And so our first speaker is Dr. Adam Kochansky from the University of Utah. He's a research assistant professor there and conducts modeling using the WRF S-Fire modeling system. Dr. Kochansky is probably one of the most world-renowned coupled fire atmosphere modelers. He's co-developer of the WRF S-Fire system. He did his PhD at the University of Nevada, Reno in atmospheric science. And thanks for making it all the way over here from Salt Lake. There we go. I think that'll work. This thing's kind of goofy.
Okay, thank you, Craig, for introduction, and thank you for inviting me. It's a great pleasure to be here in San Jose. So I will be talking today a little bit about WRF S-Fire and some recent work that we kind of completed during the summer months, and in general I will describe kind of what the system is. So so if you have no idea about what the WRF S-Fire is, don't worry, and I will just provide some kind of introductory kind of slides so we know where we are and what we are working on. So let me just start from just very basic thing, which is kind of what this coupled fire atmosphere model is, and most of you are familiar with this classical way how we approach fire spread modeling and in forecasting, where we have so-called uncoupled system in which we just have information about fuel, about weather, topography, and we just feed this information into our fire model, and the fire model just generates for us the forecast. So in this framework, you have all those components, but there is really not much interaction, especially between the fire and the atmosphere itself. So there is another way how you can approach that, which is the coupled fire modeling. And in this case, situation is slightly different. Because you have information which are provided from the weather model to the fire model, but also there is a feedback, and you have heat and moisture fluxes, from the fire impacting local weather. So that's another level of coupling that you implement, and also you can have also another loop through the fuel moisture model, where you can just have information from the weather model just driving your fuel moisture computations and then being used by your fire model. How is it done, in Warface Fire? So the Warface Fire is built around, the weather research and forecasting model, and there were a lot of presentations today based on WRF, modeling. So here is basically, the weather model, and the weather model provides information like, for example, wind speed and wind direction into the fire module, and the fire module computes the actual fire progression and computes the amount of heat and moisture released by the fire as it progresses, and this information is fed back into this atmospheric component of the system, so the local weather actually responds to the presence of the fire itself. So that's kind of one loop of the coupling, but there is also another one that I mentioned through the fuel moisture model. So information about air temperature, relative humidity, precipitation is used by the fuel moisture model, and this fuel moisture model computes the fuel moisture, and this information is again used by the fire model to compute how fast the fire propagates through the landscape. So knowing how fast this fire moves through the landscape, we can compute also what are the emissions, how much smoke we have, how tall this smoke plume is gonna be, how it will disperse, and also a couple of new things that we just added very recently is that we also have this coupling with the WRF Chem, with a chemical module, and it may be very useful for looking at the things like, for example, radiative impacts of smoke shading, inversions induced by the smoke, and all things related to that. There are way more capabilities in terms of kind of physics, because you can imagine that smoke also interacts with like microphysics and clouds. So those are the things that kind of are in place, but we have never tested them. So the capability is there, but I mean we are just kind of starting and just kind of scratching the surface in terms of how much we can do in terms of the coupling within the system. So you could ask a question, okay, why to go into this so complicated system with so many boxes if we could do the same thing just using like classical approach with uncoupled models. So there are some benefits coming out of the fire atmosphere coupled modeling, and the first one comes from the fact that we can account for local weather modifications induced by the fire. So all things like fire-induced winds or like acceleration of the surface flow because of the vertical mixing induced by the fire itself. Those are the things that we can account within this framework. Also, things as I mentioned, related to the presence of the smoke and how smoke enhances local inversions, for example. That's another element that we can take into account as well. Another point is that within this system we have very strong coupling between the fire and weather, and strong coupling I mean that we exchange information between the fire model and the weather model very frequently. So that's in the order of seconds. So you can imagine that the fire model can respond to really rapid changes in the wind direction, to the wind gusts, and that kind of gives a lot of information about particular fire behavior in certain places of your domain, and how it kind of changes in time. Also, because we base everything on the weather data and on the gridded data, we also use different information in different places of our fire. So you can imagine that once the fire progresses through the landscape, it may have experienced completely different wind direction or different fuel moisture from one place to the other, and that's also something that kind of comes from this coupled model. Another element which we kind of get from the system is very high resolution local weather forecast. And if we are talking about interactions between the fire and the atmosphere, we really need sufficient resolution to be able to actually resolve the plume rise and how the fire actually impacts local meteorology. And that basically means that we have sub-kilometer scale very high resolution, and that allows us to resolve a lot of terrain, all the complex circulations and like microclimate, some microbursts and whatnot, all the things that you could potentially miss from this regular large scale weather forecast, or even like high resolution weather forecast at 3 kilometers. Now we are talking about a couple hundreds of meters, so that's a different capability in terms of the level of details that we can get from the model. So now you could ask the question, okay, so why this fire atmosphere coupling is actually important? And here is just a cartoon showing like 4 fires, and for all those 4 fires are driven by the same surface wind of 5.5 meters per second. And the only difference between those 4 fires is just the vertical profile of the wind speed. And you have just on one side it's this logarithmic profile, and that's the fastest one. We have a constant wind profile. That's just wind speed that decreases with height. And here was this case where we had actually like 2 layers of flow in different directions. So you see that if you just look at those surface winds at 6.1 meters, and that's what we normally do. I mean, you can miss a lot of variability because of the actual coupling between the fire and the atmosphere. So let me show you some examples of the coupling from the standpoint of the fuel moisture, because that's another element which is important here. So here I'm showing a simulation for the setup for Washington 2012 Barker Canyon fire. So you see this bunch of boxes. Those are those nested domains that allow us to go from relatively coarse resolution to something very high resolution and very detailed picture of what happens in the fire domain. Here I'm just showing you like the observed and simulated perimeter, and let's look what the model does in terms of this simulation. So here the color field that you are looking at, that's the fuel moisture, and this fuel moisture just changes from those blue colors that represents really high fuel moisture during like nighttime, and those warm colors, they represent like very dry fuel during the daytime. And if you look, what happens is that whenever you have, those warm colors, the fire kind of starts, moving, and we have a lot of smoke. And then again, when during the nighttime we have fuel moisture recovery, we have decrease in the activity of the fire. It slows down. We don't have that much smoke. So that's, there's another kind of, layer of coupling that we are talking about, and that we can kind of account for in a coupled framework. And the same thing is shown here on this time series. So you see this purple line that shows you how the fuel moisture changes, and this red line, it represents how the fire area grows. So you see that when we have those high fuel moisture hours, we have almost no fire progression, this flat line, and then when the fuel moisture goes down, the fire starts progressing, and like day by day, the cycle repeats. The interesting thing is, and I have to point it out, of course, it's not like a universal thing, yes? I mean, it is for this particular fire, but it's going to be completely different for Santa Ana fire, for example, which will be just, roaring day and night, at similar speed. So having this, physical representation in the model and the coupling, I mean, it means that we don't really have to make any assumptions, what the fire actually is gonna do, afternoon, and is it gonna slow down or not. We can, to some degree, at least, looking at the meteorological conditions and what the fuel moisture variations are gonna be over next hours or a day, we can kind of estimate what the fire activity is gonna be. Another thing that is really interesting here and can be studied and also to some degree forecasted within this framework are those radiative kind of interactions related to smoke. And here I'm just showing you an animation of 2015 California fires, and you can actually even see the smoke kind of being stuck in those deep canyons. for like many days, and that's something that really has a lot of impact on local meteorology and what happens with the smoke. So here is just like a kind of diagram showing the feedback mechanism that we see here. So if you look at those plots, that's just like a snapshot showing integrated PM 2.5. So that's just a measure how much smoke we have. And then we have on the other side here, we have solar radiation, and all those blue patches, that's like the reduced solar radiation because of the smoke shading. And as a result of that, we have cooling near the surface, and that's like up to 3 degrees of Celsius. So like we don't have that much warming in the ground. And as a consequence of that, we also have less vertical mixing. We have lower winds near the surface, so it's even harder to mix out the smoke. And also we have lower PBL height, so it also reduces this layer over which we could potentially mix out the smoke. So at the end of the day, if you would look at simulations with and without radiative feedback from the smoke, it would come out that those simulations with radiative feedback show much higher concentrations of the PM 2.5. So there is like a positive feedback that you can also try to account for using like those couple atmosphere models. So from the standpoint of practical applications, we tried a couple of years ago, and we worked a lot on putting together like a system that could take advantage of those coupled models and provide the actual forecasts. And here's how this system works and how it's built. So it's called WRF-X, and we start from meteorological input data, just regular numerical weather forecast, some data providing all the information about fuel, topography, surface observations of dead fuel moisture, and the new thing that we just added over the last summer was infrared fire perimeters. So we can also simulate fires, not just from the ignition point, but just also to continue simulations of ongoing fires. We can have user-specified ignitions or also VIRS or MODIS satellite detections. So that kind of defines all the input data into the model, and then we just do all the processing to get files ready for our simulations, and that's fed into the WRF-Fire model, and the WRF-Fire then just generates simulation and generates output, which is being visualized on the fly and just posted on the web, so user can just take a look and then see the animation. So those kind of the coupling that we are talking about and the model itself, I mean, it's something that can be run like fast enough to really have a forecast, and we have an infrastructure actually to easily show that to people interested. Now, from the standpoint of the dead fuel moisture, that's one of the really important things for the operational fire forecasting. So we have the system that integrates, that assimilates data from remote automated weather stations, and it generates basically those nice spatial maps for 1 hour, 10 hour, 100 fuel moisture, and then they are just collapsed into total fuel moisture that then is used by the model, and that's a standalone actually product. And another kind of new thing from this summer is that this system was running operationally, and it is still online, so you can just go to this website and see that's our kind of assimilation product. So there's like a nowcast showing what the fuel moisture is right now, and that's based on RTMA data. Now you may think, okay, so how complicated is it to run those kind of coupled simulations? It doesn't really have to be that complicated. And here I'm just showing you the controller. There's like the web portal that allows you to actually start those simulations. You just put the name of the fire, you put the location, or you just click on the map. You have to decide when you want to start your simulation. Once that's done, you just select the length of the forecast that you would like to have, and after selecting the so-called profile, which defines how big is your domain, what resolution you want, you just hit this big red button, and everything starts kind of running in the background. So the system at that moment starts downloading all the data needed by the model to generate all the input files for WRF. And once all the files are just downloaded and processed, this job is submitted on a computing cluster, and we have a running job that just provides output. And once we have the first output frame in the file, we just start doing visualization of this simulation. So even before the actual whole forecast is done, just on the fly, we just keep adding frames as the simulation progresses. So then on the web portal itself, you can just select things like the wind field, the fire area, or whatever you are interested in. You can look at the smoke, where smoke is gonna go, how the fire is gonna grow, and all things like that. So that kind of allows us to relatively in an easy way set up simulations, and also share them with other people. And we are kind of trying to really slowly, but we are really trying to make that kind of useful and bring it from like the really research kind of stage to something kind of more operational that at some point may be used by other people that would need and would appreciate this kind of information. Another interesting thing is that using exactly this web portal that I just showed you and the controller, we did a lot of simulations over the summer. So that's just the list of the fires we simulated, and I will just show you one example. That's the Paul Creek fire from 2018 near Utah. So you see those those are like 3 nested domains. So that's the fire domain here, and that's two outer domains. So that also the system allows you to actually have this long range transport of smoke. It's not just this high resolution picture of the fire itself. And that's something really useful, and that's one frame that just shows you like the finger of smoke, in the morning hours being just injected into the valley, into the Salt Lake, and that's exactly what we also observed, in the station data. So that's just a graph showing PM2.5 concentration from our forecast and from the sensor that actually captured the smoke. And here are just two figures that's simulated plume top height, just showing you the orientation of the smoke, and here on the right side there's like a satellite image. So just to sum up, those are the new things that we put together over last like probably year or so. So we have those a lot of new things that we just added, and we are kind of moving forward. Next steps, we will need definitely to work on a simulation of other satellite data and things like that. I'm a little bit, I think, running out of time. It's like 18 minutes already, so you can just read that. And if you have any questions, I will be happy to answer. And just to relate to the talk about the fire wheel. That's the fire wheel that we by an accident simulated using WRF as fire at some point. So I'm ready for your questions. Thank you.
We have time for a couple questions, quick.
We've talked a lot about wildfires, but would your system be useful in for a rancher or Forest Service person doing a prescribed burn and wanting to forecast where that prescribed burn would go? And does it include spotting?
Well, so yes, I mean, actually, the original idea, behind, the system and this portal that you saw was actually the prescribed, burning. So you just, select, location, ahead of time when you want, to burn, and you just, get a forecast where the smoke is gonna go and where the fire will go. So that, yes, absolutely, that's absolutely possible, and that's the kind of, the original idea behind it. The wildland fires actually was kind of, extension of this original idea. In terms of the spotting, we are working on that, but we don't have at that moment the spotting per se in the model. So that's something that we are working on right now in terms of how to parameterize spotting. But we have a lot of elements already in the model, especially those vertical velocities in the plume. So we are kind of well positioned at least to work on this problem.
Right here. And thank you for that very informative talk. And
I've been very interested in your research since I'm working with Tim Brown on the CANSAC model over in DRI, and really we're trying to implement things like that. So my question is computational time. Our wharf runs about 6 hours. How much time would it take to spin up something like that?
So those simulations that I was showing you that we ran for 2018, we normally issued nominally like 48-hour forecast, and this forecast from like the beginning, kind of pressing the button till the moment when the forecast was kind of completed, and online it was about 3 hours.
That's great. And where do you get your emissions data?
So the emissions are computed just from the fuel consumption from the fire model itself, and we use FIN fire emission inventory emission factors to compute the exact emissions. But in those forecast runs, I mean, we don't really run the full chemistry, because that would take really a lot of time. So it just does like PM 2.5 as a tracer, and it's not really with like the full chemistry.
Okay, thank you.
Take one more question, then we'll move on. Hello, check. There we go. Yeah.
2 questions. One is, I just hopped on the openwfm.org, and it says it needs a username. How does one get one?
Well, I just shoot me an email, and I will give you the username and password.
Okay. And can you use different fuel LCPs rather than landfire if you have better data than that?
Yes, absolutely. That's what we kind of have processed, so far, because this system is actually kind of universal in a sense that we are ready to simulate a fire anywhere in the CONUS. Yeah. So that's what we have done and what we have ready. But yes, generally speaking, as long as you can provide the data in a GeoTIFF format, we can really easily ingest it into the system, actually without any problem. It's just it takes GeoTIFF file and it automatically will just update the input files with your fuel data.
Great. Let's move on to our next talk, and we can catch up with Adam at happy hour on the roof. Thank you, Adam.
Thank you.
Okay, let me get sense. Okay, our next speaker is Sen Chow. Sen's a professor of meteorology at Department of Meteorology here at San Jose State, and he is also the director of a NASA institute or center called CARE, the Center for Applied Atmospheric and Education Center. And so Sen came to San Jose State in 2009? 11. But he's also the chief scientist and PI of the new HPC, High Performance Computing Center, which has 1,800 core and runs WRF. So he'll be talking about the computing capabilities here that we have going. So take it away, Sen.
Thank you. Thanks again. Since I'm from San Jose State, thank you again for coming to San Jose State, and this is great. So what I'm going to show you, or what I'm going to present to you, is sort of like a working in progress in terms of computing, in terms of the thing we are doing right now. It's more on along the line in terms of high performance computing. So just like Craig mentioned that we got into a NSF MI grant, so we were able to build up the first high-performance computer on campus, and ironically, we are in the Silicon Valley, but now. So I'm going to talk about a little bit HPC here on campus, and then show you a little bit in terms of the capacity and what we can do, and then I want to touch a little bit in terms of from the data science perspective, how we actually utilize the HPC and then to tackle the issue in terms of not only the fire, but also maybe some other things as well. And I'm show you some kind of sort of like work, the real-time capability right now we have to answer the previous question in terms of running. We are running 72 hours. Within 1 hour, you get a result. I can tell you that. So, and then a little bit in terms of machine learning as well. That's why. And also feel free to stop me if you have any question when I'm presenting this. So this is HPC right now we have on campus, even though it's only C3 chassis right now, but it's just, this is the thing we are trying to do, combining numerical model and machine learning. So it's sort of like a hybrid capacity that we want to build up in terms of early warning and forecasting capability here. So as you can see, in order to answer the questions, how strong is the wind, or where's the fire spreading, and how and why we are going to prepare for that. Those are the questions that, in terms of management, in terms of the firefighter, in terms of the frontline person, how we actually handle those things. So ideally, that's what we're trying to do is we try to provide a solution. So again, working to quantify a small scale in terms of predictive weather forecast. That's the fundamental we do, right? That's the essential we do. And then we also want to provide wildfire real-time monitoring. And one important thing is probability forecast. I think early this morning someone mentioned about that. So we want to come up with that kind of capability that we want to show what's the probability based on the AI machine learning things that we can provide. And certainly at the end, that information that send it to the safety and risk management, and we provide some sort of solution. So this is the things we're doing right now here on campus. Craig and myself and other colleagues from computer engineering as well, we're doing this. So again, analytics connect in terms of visualization, the website, and risk management, and information management. This is also another important part of that, in terms of how we actually store the information, how we actually process the data for the future purpose as well. So, so user cases here is, as I say, right now I put a website here, but I'm probably not going to the website. What we are doing right now, again, mainly besides the fires, and we actually do, again, we do 1 kilometer. This is pretty much the domain here. This is hard dry windy yesterday's result. So we do 1 kilometer simulation 4 times a day, 0, 0, 6, 12, and 18. Providing all different kind of products from the result. As I say, this is a little bit different approach in terms of we call it hybrid modeling. So we basically plug in the first 18 hours using HER, and then from the 18 to 72 hours we plug in NAME model, NAME 12. So it's so that's why we do the 12. We do different model as a forcing data to drive this 1 kilometer. And then again, as I say, 72 hours take less than an hour to finish that. We do 4 times a day on that. Nothing that fancy though, but I mean in terms of our ability to provide real-time data and real-time focus. Craig, is this online on Wi-Fi? I'll just. Oh yeah. Yeah. So this is actually work in progress website. As you can see, this is today's temperature. Everything. Of course, we don't have precip. Luckily, we finished the rain season. And different level of the wind, fires. So for example, here, if I click on that, can I have that? All right, here. So as you can see, you basically move the, well, again, as I say, we're trying to make this website fancier. So we move the cursor, you actually, on the hour, you actually see the result difference. Day like this. All right, so enough for that. Let me close this one. All right. As I mentioned earlier, one thing important is that early warning, right? So one of the challenging question is that how are we going to know before the fire season, even like right now, what is the outlook will be for the fire season in this coming fire season. So that's just one critical point in terms of how we do provide early warning. So looking into, this is actually the example, looking into different products from satellite, NDVI, and the vegetation index, water content, and soil moisture. So this is the campfire example. So this is the typical satellite data, you see it. But what we are going to do is we combine different data, different results. Now, of course, you are seeing this is actually already happened, right? But the key point here is that how are we going to do it before it happened, right? So you look into the season though, because the NDVI or other satellite data, soil moisture, you look into the season, you look into a different time frame. You sort of like compare weekly, for example. You sort of like comparing what is the soil moisture look like this week versus last week or versus last month. So that's actually the way we try to bring in that information into the machine learning model that can provide give a better solution on that. Again, as I said, this is sort of like a work in progress. Computer engineering students are working very hard right now, so they are not here, I guess. So I'm going to meet with them next week. But this is sort of like a given idea in terms of how we actually want to come up with the result. Again, as you may already know, from the machine learning perspective, you basically cut into all different cells. You want to see what is this individual cell look like in terms of the percentage of the possibility in terms of fire. So that's actually what the direction we are going right now. It's basically, as you can see, we're kind of combining different climate information, the real-time information, satellite, and even in situ measurements and other statistics data into the system. We call it Spartan Wildfire Watch. So this is a working in progress product. Hopefully, I can show you something in the very near future. All right. So what I'm going to again show you here is to provide the solution. A mesh network alerts, so lead time and the accuracy of fire weather forecast and the warning in the Western United States. That's the ultimate goal for Craig Clemens and in terms of our fire weather research here on campus. That's what we're going to do. So in other words, what we are going to, again, this is the thing. We try to improve the lead time and the accuracy. Combining all different kind of results from a model, from the satellite, from the machine learning, from the in situ measurements, that we're going to do that to all this. You can read it yourself, but again, as I say, we want to provide a better solution. That's our goal. Using our facility on campus, we want to provide a better solution, and then we can do it that way. Thank you.
Do we have any questions for Sen? There's a couple. 2,000 core, that gets a lot of questions there.
Now, Ryan Welburn with the Weather Service. I don't even know if I have a question, just a statement. Because I think most of the talks today and the people in this room, we see the Sundowners, Santa Anas, high-level ERCs. We all kind of know what the basic parameters are. I feel like the next step is that the day where if you woke up and you said there's a 90% probability that an extreme wildfire is going to impact you, where we're kind of going to that next level of there's not a lot of surprises with the parameters, but figuring out those 1 or 2 days a year when those events happen. So I guess I feel like we're kind of ready to go to that next leap with the AI and learning, and that there's other stuff that can kind of take us there. So,
yes,
just
thank you for the comment. I think this is an important concept, conceptual things that what's next in terms of go beyond the modeling and then how we do it. Yes.
Well, I got the microphone. Hold on. No, you posed an interesting question because we just bought a computer up in DRI, and You know, Silicon Valley's right here. Why do you need a supercomputer here? And what type of cost are you looking at? Because we're looking at AWS trying to get into the cloud, and really because obviously it's a lot cheaper now to do things, but I seem to be in that same loop of buying a supercomputer every 5 years. Is there a strategy or something where we can partner with some of these groups out here to get better results in terms of our computing needs?
This is a good question. Actually, we internally we have a lot of discussion in terms of are we going to pursuing the HPC on campus. Now I can tell you one critical things in terms of outsourcing on the AWS, the Amazon Cloud Computing System, or even Microsoft, is that the on demand, when you need it, when you need to get a result, and when you need to get a result soon. So that's the critical things, in terms of speed. Now the other thing is that in terms of speed, how fast. Again, keep in mind, those cloud computing, they are not designed for the burst of computing power you need. For example, like this kind of forecasting, you do need a kind of all the sources that actually support the computing and get it soon, get it done. But those cloud computing, they are commercial cloud computing, they are not designed that way. So sometimes you kind of like a trade-off in terms of the time. You are sacrificing in terms of the time. Right? So that's actually why we want to keep certain capacity ourselves on campus that not only serving this, but also other, faculty member, they want to do research that way. Thank you.
Hey, Sen, yeah, thanks for your talk. Yeah, so I'm coming at it from like a utility perspective, and one of the things that I think about is redundancy and making sure you have, complete failover capabilities. So I don't know if you've thought about that, or if there's another, HPC that could be put somewhere else at another state college that you could kind of partner up with, where if you had, because we are an earthquake country, et cetera. Just an idea that I'm kind of throwing out there.
Yeah, this is actually a good question. Actually, I had experienced quite a few. As I said, this system actually also doing other purpose. So we have the AI event coming up, and then the machine actually is, for some reason, just not able to run. So we were not able to provide real-time information to water district. That happened. I was so very nervous on that. How are we going to deal with that? Down the road, even want to do the real-time for fire forecast. But I don't have actually a solution for that actually. But well, we'll try to figure out.
So Sam, my question is, how many years away do you think we are in terms of getting a reliable, useful, predictive analytic platform using all these components that you're doing? Are we 5 years, 10 years, 2 years? I mean, everybody's rushing to get satellite and LiDAR and all this sort of thing.
Well, my personal feeling, I thought about that actually. My personal feeling is that's why I'm sort of jumping on this kind of component. I think in five years, because there's quite a few private companies that are working on that, and other universities as well. So I think somehow in 5 years there may be some kind of breakthrough in terms of how we actually using the machine learning to do this part of things.
One more question.
Thanks, Sen. I guess my question was
I saw you before, right?
Hmm?
I think I seen you before.
Probably. It's hard to miss the hair. The question about machine learning, and you showed the slide where you're looking at soil moisture and a bunch of indices. I'm actually wondering, it's either classification or regression, right? So what are you actually trying to back out of the machine learning? And in that list of satellite sources, you didn't include Sentinel or Landsat, which is going to bring it down to 30 meters. Is that something that's on the horizon?
Yes. Thanks for that question. It's actually, yes. So as I say, this is sort of like a working in progress. We do need to somewhere need to incorporate other kind of data sets, even higher resolution for that as well. Yes, we can talk more about that for sure.
Okay, well, thank you, Sen.
Thank you.
Okay, our next speaker is Natalie Wagenbrenner from the U.S. Forest Service Fire Lab in Missoula, Montana. She's a fire weather meteorologist there, and she's going to be talking about what's going on at the fire lab in terms of fire weather research and applications.
Okay, so I see I'm in the numerical modeling session today, and I will talk a little bit about some numerical models that we develop at the Fire Lab, but I wanted to really give an overview of the fire weather research that's been going on at the lab. And so before I get started, I do want to recognize my co-authors, Brett Butler and Jason Forthover. Brett is our team lead. He's a research mechanical engineer at the lab, and Jason is a mechanical engineer and has a lot of operational experience. He has a strong operational background, so his fire qualifications include division supervisor and fire behavior analyst. So he brings a strong operational background to our team. So the Fire Sciences Lab was established in 1960 as a facility to conduct fundamental wildland fire research and develop tools and applications that can be used by fire management. And so the facility is actually unique in the world. We have a large combustion chamber where we can conduct lab studies where we can burn different types of fuels with different types of configurations on different slopes and make detailed measurements with some key unique instrumentation that's been developed at the Fire Lab. So we do research that's based on lab studies, field studies, theoretical studies, as well as numerical modeling. So there's sort of three key groups at the Fire Lab. There's the fire behavior group, which is the group that I'm a part of, fire chemistry and fire ecology. And so most of the fire weather research that's being done at the lab is in the fire behavior group, although we do intermix with the other groups there. And so we have a number of fire weather research interests at the lab. This isn't an all-inclusive list, but this is a good sampling, I would say, of the research interests that we have. And I'm not going to read through this list. You can see what's up there. I'm going to go into most of these points in detail over the next few slides. So we do a lot of work at the lab that's dedicated to measuring and modeling winds, specifically in complex terrain. We know that local scale winds near the surface are really important for a number of things that we care about at the Fire Lab. So fire spread, smoke transport, ember transport, post-fire wind erosion. These are just a few examples of research interests that we have related to winds in complex terrain. And we use a number of tools to study and winds in complex terrain. So we use numerical weather prediction. We do a lot of work with WRF. We also use diagnostic models, and we develop one diagnostic model in-house, which is called Wind Ninja. So we've been developing this model at the Fire Lab for about the last 15 years. We recognized early on that there was, this was one sort of missing tool in the toolbox. We wanted, Jason was the original developer of Wind Ninja. I joined the team a few years after he started this project, which was actually part of his master's project in the beginning. And he realized from his operational background that there was a need for high-resolution wind modeling that could be applied in the field. So there were a number of requirements that we wanted the model to meet. We wanted it to predict surface winds at spatial scales that are relevant for fire spread, so on resolutions, horizontal resolutions of tens of meters. It needed a simple user interface so that fire managers didn't need a lot of technical expertise or large amounts of training to be able to run the model. We wanted it to have flexible initialization options. So Wind Ninja can be initialized either with coarser scale numerical weather prediction models or with observations, say from a RAS network, or just like a domain average initialization, which can be used for like what if scenarios. It needed to have fast simulation times for it to be relevant for emergency response situations. So you can get results from this model in seconds to minutes, depending on what you're doing. And it needed to run on simple hardware because fire managers in the field, typically are just using, like laptop computers. So with all of those requirements in mind, WinNinja was developed. I'm showing you here a few screen captures of what the graphical user interface looks like. It's free, it's open source, anyone can download it and run it. It comes with tutorials and documentation. And then I'm just showing here some example output from the model. So it's under active development. It's embedded in a number of operational systems. It's in the Wildland Fire Decision Support System and in a number of operational models that are widely used, like FlamMap. Prometheus is the Canadian model. Wildfire Analyst that Techno Silva develops. It's used by incident meteorologists, fire behavior analysts, and long-term analysts, as well as on-the-ground firefighters. Especially recently, since we've been developing, in addition to the desktop version, we now have a mobile version, which Techno Silva is helping us to develop. And the goal of the mobile version is really to get WinNinja into the hands of on-the-ground firefighters that don't have easy access to laptop computers or time to, sit down and run simulations. But they can initiate a simulation on their phone. The simulation is sent off to a server that's actually in Amazon Web Service Cloud. And then when the simulation's ready, the firefighter gets notified and they can view it on their mobile device. So as we've continued development of WinNinja, we've realized that as we want to do continue the development and do evaluations of the model, one of the limitations has been available field data for validation. There just haven't been a lot of data sets to validate high-resolution models in complex terrain. So the data sets that have been available are limited due to the terrain complexity that's been sampled, the spatial density of the sensors, and the meteorological conditions that have been sampled. So over the last 10 or so years, we've been conducting a number of different field studies in different types of complex terrain. We've done 4 or 5 of these studies now so the studies have been focused on different types of terrain features. So one of the sites was sort of an isolated mountain surrounded by flat terrain. We've gone to a steep river canyon that's mostly grass vegetation, went to another broader valley with steeper slopes and forested cover on the ridges there. And so at each of these sites, we've made a number of measurements. The key measurement, I guess, has been surface winds with these 10-foot tall cup and vane anemometers. So we have about 60 of these sensors now that can be pretty rapidly deployed. And so we've put them out in these different field sites and left them there for 3 to 4 months, continuously measuring at 2 hertz. And then in addition to these 10-foot tall anemometers, we've made some other measurements, including near-surface wind profiles and turbulence with the sonic anemometers and SODAR profilers, and we've done radiosonde launches. And with these data sets, we've used the data to do model evaluations. So we've looked into some of the how some of the parameterizations are working inside of WinNinja. There's some thermal parameterizations in there that we've been able to evaluate. We've looked at how numerical schemes are performing, initialization methods. And so what I'm showing you here is just a couple of examples of some WinNinja output where we're comparing 2 different solvers in WinNinja against, you can see the snapshot of the observed data. This is the tall isolated mountain that I was mentioning. And then we've also used the data to evaluate numerical weather prediction forecasts. We've also been using the data just to understand flow phenomena in complex terrain. So we've looked at the physics related to diurnal slope and valley flows, recirculation, on the lee side of hills, flow channeling. And then we've been looking into different types of short-lived atmospheric boundaries, including thunderstorm outflows, gap flows, and gravity waves. And I'm going to talk a little bit more about these things here in a few minutes. What I'm showing you here in this simulation is so this is a valley where we made some measurements in southern Idaho, and we measured a pretty strong thunderstorm outflow event here. You can see it. This is getting towards the end of the simulation here, but I'll start back over. And there were some thunderstorm cells up here north of the valley, and then you can see there's a gust front that propagates through the valley and out onto the Snake River Plain down here. We actually use that data to do some evaluations of the high-resolution rapid refresh model. We work pretty closely with the developers of the HER, and we're working on a paper right now writing up the HER performance for this event, as well as, so this event actually happened, it was around the same time as the Yarnell Hill accident, and so we're writing a paper right now that's looking at the performance of the HER and sort of simulating the flow dynamics associated with the thunderstorms for those events. This other image here is just showing a measured downslope windstorm at night that occurred on this isolated mountain here. So the winds were sort of weak out here on the plain, and then you can see increased winds at the surface on the lee of the butte there. So I was mentioning that we've been working a lot with the HER model, and that we've realized that the HER actually has a lot of potential for fire weather forecasting. It's updated every hour, and it assimilates radar and lightning data, and so it's really promising for forecasting things that are important to firefighters, like which have been historically harder to forecast, flows associated with convective systems and things. And so one of the ideas that we came up with about a year or two ago was to develop what we're calling a fire weather alert system, which we're hoping to turn into another mobile app. It's really targeted for on-the-ground firefighters that don't have time to go out to all these different web pages and different sources to get information related to both weather predictions and observations. So the goal of this application is to combine both of those things into a single interface. And right now we have it up on this web page here that anyone can go and check it out and test it out and see how it's working. Right now it's just a web application, and there's just a simple form that you fill out. It lets the user set a number of thresholds related to the fire weather metrics that you care about for your area. So relative humidity, wind speed, temperature. And then if we go out and we check in the background on a server, we're constantly checking the HER forecast, as well as observations from RAWS and ASOS stations that we pull in from the MesoWest API. And if we detect any exceedances of thresholds that the user has set, you just get a notification on your phone. So an on-the-ground firefighter can just, have these set up in the morning, put their phone away, and then when they're working, out on the line or whatever, they don't have to constantly be looking to see, like, what's the radar look like, what's the observation at this RAW station. They'll just get a notification when one of their thresholds is met. And I wanted to just briefly mention some of the firewall research that's being done at the lab. My teammate, Jason Forthover, is kind of an expert, I would say, in firewall research, and he's been doing this kind of research for probably the last 15 years. So I'm showing you here an image from I guess I can play this video. We already saw it once today. Oh, maybe I won't play it, it's got the sound. But this is the car fire tornado that we saw earlier today, and Jason was actually on the accident investigation team after this event, and I worked with him to come up with a theory for what might have caused the fire tornado to happen. And this is a schematic from the accident investigation report that they put together that basically describes one theory for what might have happened. So this area here is around Reading, and so they had above normal temperatures around 113 degrees that day, and then you have this coastal range barrier here, and then over here is the ocean around like Eureka, California, where they were actually experiencing slightly below normal temperatures. So you had this sort of enhanced thermal gradient that basically you have this cooler, denser air that's getting sucked down into this thermal low over here where Reading is. And what it looks like happened is that maybe so you have these strong downslope winds happening, and then there could have been a hydraulic jump, which would have led to increased vorticity and all of the right ingredients for a fire tornado. So that was sort of the idea that we had. So what I did was I ran some high-resolution WRF simulations initialized with the HER, and so the HER's at 3 kilometers. I downscaled to 1 and then to 333 meters. And this is a slice through the domain around the time that the fire tornado occurred. It was around like 1800 that day. And so the area where the tornado emerged was right in here. And you can see strong downslope winds here. The colors are absolute vorticity, so you can see also enhanced vorticity in the region where the tornado occurred. And what appears to be, looking at the isotopes here and the wind vectors, possibly what looks like a hydraulic jump. Okay, and then the last thing that I wanted to mention is, and this is related to sort of fire danger, fire preparedness. This is work that Matt Jolly is leading, and this is his wildfire hazard projection system. And so what he's doing here is using the NFDRS to come up with a single metric that's based on the burning index and ERC. So the product of those two indices to come up with a single severe fire weather potential. And that's what this map is showing here. So this is severe fire weather potential mapped out across CONUS. It's at 2 kilometers. And I think it goes out for 7 days. So he's using the NDFD grids as well as observations to do this calculation for the combining the burning index and the ERC to come up with this gridded severe fire weather potential. And then what we have here is just showing the severe fire weather potential metric for some of the destructive cases. It's hard to read, but yeah, this is like the Tubbs and the Nuns fire. And basically what he's showing here is that the severe fire weather potential indices were all like above the 97th percentile when some of these most destructive fires occurred. Okay, so that's what I had. I just wanted to give a nice overview of the research that's being done at the lab, and I'm happy to take any questions.
We have time for a question.
Yes, as a Wind Ninja user, I have a question regarding, have you compared the performance of Wind Ninja where you used just surface-based, say, RAWS data, and then you use the profiler data or the Ravensson, you had a vertical profile in the performance, and are there situations where you would warn the user that you, either by distance of RAWs or by number of RAWS stations or not having a vertical profile, that the results are probably questionable?
We haven't done any formal comparisons, although that is a good idea and something that we should do. But yeah, I think it's kind of up to there's a little bit of art in it, I guess, in deciding what the best initialization data is to use. And if you don't have good weather station data, then you might be better off going with the HER, for example, is one of the weather models that can be ingested by Wind Ninja. But yeah, that's a good question. We haven't done any formal analysis.
Great, thank you. Another hand for our speakers. So we're running a little bit behind on time, but we have snacks, cookies, and coffee and sodas. What's the temperature like in here? Do we want to shut doors and try to cool it down, or do you like the doors open? Is it good? People, because I'm the only one with a sport coat and a long sleeve shirt and running around? Okay, so let's take a 15-minute break, stretch our legs, and we'll have our last 2 sessions. 3 more presentations, and then we'll have our panel, and then we can get to happy hour. It's a pleasure to introduce Dr. Edward Heyer, who's a physical scientist at the Navy Research Laboratory in Monterey. He's a remote sensing scientist that studies wildfire using remote sensing and satellite technologies, and he's going to give us a presentation on observations of Pyro-CB. So, welcome.
Thanks everybody for sticking around, and thanks Craig for the invitation to come be here. A lot of what I'm showing here is work that I've done with Dave Peterson over the last few years. Dave Peterson would have loved to be here, but he won an award for the most recent publication in this sequence. So as we speak here, he's actually at a dinner with a bunch of Navy bigwigs at Bolling Air Force Base taking his award. And I'm here talking to scientists and operations people about fire science. So believe me, he's very jealous. All right, so this talk is about the observation side of things. What I want to talk about, of course, are just a little quick background so that everybody knows what we're talking about, what are pyrocumulonimbus and why do they matter, a brief discussion of the meteorological components of it, which is most of the meteorology in this talk, and then a few different considerations for observing this phenomenon, how to detect an inventory, how to quantify the smoke injection associated with it, and then how are we going to actually model what that smoke might be doing in the atmosphere. So pyrocumulonimbus, this is a wildfire-driven thunderstorm. This is a consequence of the wildfire heat and the specific meteorology. It is larger and deeper than a pyrocumulus, hence pyrocumulonimbus. It involves very extreme smoke loading, a lot of smoke carried up to an elevation higher in the atmosphere or an altitude higher in the atmosphere than smoke is ordinarily found. Very little precipitation out of a cloud like this, especially considering its depth. An anvil with a very prolonged lifetime because of that precipitation effect. Strong potential for lightning strikes because of the updraft strength. And this is a phenomenon that has been known about sort of anecdotally and researched on sort of a case study basis, but it is a systematic endemic phenomenon in summer wildfire climates. And so Dave Peterson and I undertook a more systematic study of it using some new tools that I want to describe. So why is the Naval Research Laboratory engaged in this pursuit of pyrocumulonimbus study? Well, it's a means of transport of water and particles and trace gases into the stratosphere that does not currently have any prediction or monitoring systematically. So this produces errors in smoke transport forecasts, which is one of the things that we systematically predict worldwide for Navy applications of visibility and directed energy. And also the extended smoke lifetime in the stratosphere is of specific interest to us because it can have a lot of downwind impacts energetically and chemically. Here's the weather part, okay? This is the conceptual model of pyro-CB development. At the bottom, we have the extreme surface fire danger. You can't have one of these unless you have a very vigorous fire. So hot, dry, and windy. You might have heard that before. A deep mixed layer, an intense fire that's plume dominated, minimal wind shear in the lower troposphere. So that's the first place where we start to diverge from sort of the stereotype of severe fire activity. So the weather conditions that produce pyroconvection are not the same weather conditions that produce the fastest runs. And that was a very important conclusion of this publication in Monthly Weather Review, was that there's a specific set of conditions that allow pyroconvection to occur, and they're not the conditions that are the most extreme for the run of the fire on the ground. You have to have that mid-level moisture source, and what that means in terms of your sounding is that instead of the goalposts, you have to have the inverted V, because if you don't have any moisture at altitude, you will not actually be able to sustain the convection all the way up to the tropopause. And that was a matter of considerable debate. But I think that our systematic study shows that the moisture contained in the smoke itself, the moisture actually released from the burning, is just not enough. It's just not enough to carry the convection all the way up to the tropopause. You have to have some mid-level moisture that's already there. This is observed in non-tropical climates. In tropical climates, the tropopause is just too high to get to. It's not to say it could never happen, but it will not be a normal phenomenon. And this is not a normal environment for deep overshooting convection. So the implications of this are high-based convection and wildfires are coincident in many regions. So pyro-CB is likely to be a significant and endemic feature of regional summer climate. And that's what we see when we start observing them systematically, is that they're happening a lot in wildfire climates in the summer. And the question is, are they potentially a significant source of stratospheric aerosols? So there are a bunch of means of detecting these things one at a time on a case basis. There's a lot of satellite data that flows across people's desks every day, and pyro-CB, people have developed sort of tricks of their own for how to detect a pyro-CB in visible imagery, using infrared remote sensing, using certain instruments, mostly operated by NASA, that produce things like the UV aerosol index. That's from the OMI instrument, that image there. LiDAR observations are obviously extremely helpful, as they give you that explicit profile of particles of ice and smoke in the atmosphere. And of course, where would we be without backward trajectories that allow us to use some sort of observation of some constituent in the upper atmosphere and tell us something about where it came from. But if we want to do this systematically, what we need is a tool that observes often enough to capture this transient phenomenon. So this is a deep overtopping convection. It has a lifetime of a few hours. It does not persist through the night into the morning. So we're going to need pretty frequent observations to get it. And of course, a lot of our satellite instruments are observing close to local noon, which is not the peak of fire activity and definitely not the peak of pyroconvection. So what we've done is we're using the geostationary infrared. And what we see, first of all, is that the pyrocumulonimbus are deep and cold, just like the regular cumulonimbus clouds. But when we look at the 4-micron brightness temperature, what we see is that because they have smaller cloud particles than the regular cumulonimbus, they reflect a lot more sunlight. And that gives us a much stronger signal in that 4-micron wavelength. And that is our distinguisher of pyro-CB as opposed to other types of convective cloud tops. So we apply that inventory. Here we go. We apply this method to systematically inventory these events by basically just pouring through the imagery for every large fire event for the 2013 season was our initial test to identify the occurrence of these pyro-CB and capture some of the statistics associated with how high they got, how large they were, how long they lasted. Yeah. So this is the result of this 2013 inventory, 26 events producing 31 anvils. So this season is above the mean. And certainly there are western fire seasons that produce very little pyroconvective activity. However, going forward, we can expect to see these every year in some quantity in that sort of 10s to 20s number. So not every single day, but enough to probably be a phenomenon worth studying. So each of these detected events, each of these 26 events, has likely stratospheric injection. So how do we quantify that injection? This is an example. This is the example that netted us the publication award. This was a large wildfires. The lowest, the southernmost one is actually in Washington State, and the upper complex is in British Columbia. This is August 2017. This complex produced 5 pyroconvection events, 4 in British Columbia and 1 in Washington. The whole event lasts 5 hours. So using the once a day observing satellites is not going to tell the story of these fires. The meteorology driving this event fits what we described for pyroconvection, and the result was a very large set of pyroconvective clouds. So this is a satellite image from space, and what we're looking at here is this smudge of smoke that runs from Hudson Bay all the way across to Nova Scotia and out over the Atlantic. And if you look over the Atlantic towards Norway, you will see that the smoke signal is there solidly above these high clouds. So this is stratospheric smoke and pretty thick. So this is a pretty major stratospheric event. So we really wanted to try and put some numbers on this and see how that compared to like a volcanic eruption, because that was the nearest thing that anyone could think to compare this to. So this is the aerosol index from the ozone mapping profiler suite that gives us the spatial horizontal extent of this event. And through that, we're going to look at a LiDAR curtain and basically establish that a certain value of this index corresponds to stratospheric smoke. So when we look at the LiDAR profiles, we say, okay, the aerosol index over 15 corresponds to a substantial smoke in the stratosphere according to the LiDAR, and therefore we can use that to get the horizontal extent of this event. And we see that it's pretty darn big up there at 80 degrees north, or 70 degrees north. So the instantaneous area, about 800,000 kilometers squared. And now we want to calculate the mass of smoke in that area. So we go back to the LiDAR image, and we calculate the LiDAR backscattering, and we use the smoke mass extinction coefficient and the LiDAR ratio, which are uncertain. So that they are major terms of uncertainty in our calculation. And I'll get to how we might be able to constrain those better. But that allows us to estimate the smoke mass density and therefore the total stratospheric aerosol mass. So the punchline is this, that the initial injection is comparable to a moderate volcanic eruption with a volcanic emission index of about 3 or 4. Pretty big stuff. The secondary particle formation associated with a volcano, because the major volcanic species is sulfur dioxide, which is gradually converted to sulfate particles in the atmosphere, and that means that you have particle production that extends the lifetime of the particle plume. We don't know, something like that is likely to happen with pyrocb plumes, but we don't have any of the information needed to quantify it. So we only know about the initial injection, and we know that it's comparable in order to a volcanic injection. The 2013 fire season in total was not as big as this one event in 2017, but still pretty significant. These are typical pyrocb events in the bottom, and this Chisholm fire is one that you'll see there's a number of papers written about it. It was the previous benchmark before 2017 of what a big event looked like. It's a lot smaller than the 2017 event. So pyrocb can result in large amounts of mass in the stratosphere, and if we want to understand what that smoke in the stratosphere is doing, we need to know more about what it's made of. So going back to our little diagram that shows the process by which that smoke is going to make its way all the way up into the stratosphere, down at the bottom, we've got a lot of measurements. There's a lot of variability in the composition of smoke. It's not a solved problem by any means, but we've got a lot of data to throw at the problem in terms of what's in the smoke that actually comes right off the fire. But we get problems right away. It's very windy at the surface. How much dust is lifted along with that smoke? We've known for 20 years from Reed and Hobbs that there is a mineral dust component associated with a vigorous fire on the landscape. We saw it again in Seekers. There's enough wind associated with a vigorous forest fire event that you're going to kick up some dust. That's pretty important in terms of the composition when you lift it through the column. We don't have a means of quantifying that without some better measurements. This column here is almost entirely ice. There's very little liquid content in this uplift. So how much liquid processing of these smoke particles is occurring in this column? What are the rules for secondary aerosols when you lift the precursors all the way up to the top? We're getting into some high degrees of freedom unknowns here because we do not have many measurements at all to apply to these questions. And finally, how can we estimate from observations the potential for overtopping the tropopause? So these are questions that now that we have framed the problem, we think that a lot of observations are applicable to these questions. But one of the most exciting things that's happening is NASA and NOAA having a FireXAQ mission later this summer. Well, they'll be flying aircraft around where Western smoke is. And we have developed a strategy for pyrocb sampling in conjunction with that mission, where Dave Peterson is actually the forecasting lead for that mission. So the nowcasting team identifies a likely pyrocb event. We determine whether we're going to sample it today or tomorrow, based on our best chance of finding the smoke. If we're going from downwind, we want to fly under it and look up at the smoke on our way towards the fire. And then we want to see how close we can get. That's always what these things come down to, is how close can you get. So continuous guidance from the nowcasters, and of course the experience of the fact that these things are occurring around active events that are being actively suppressed in many cases, makes this a logistical challenge on a few levels as well as a scientific one. We're hoping for a lot of opportunities to increase our knowledge. FireXAQ is a good opportunity, but it's certainly not the only one. You know, now that we sort of know what measurements we'd like to have, I think that there's lots of opportunities to get them besides this mission. So this is my concluding slide. This 2017 event had 5 total pyro-CB. The stratospheric impact was comparable to a moderate volcanic eruption. The pyro-CB developed with conditions that are similar to high-base dry thunderstorms. So we expect them to be a significant and endemic feature of regional summer climate. We do not expect them to be blue moon cases. And we're building the capability to systematically inventory them on an ongoing basis, as well as detect them in near real time as they happen. So there's publications that Dave Peterson has wrote about this, and we do have a web page that generates in near real time the imagery I showed you that detects the occurrence of the pyro-CB clouds. And we're working on developing that more this summer with the help of some interns from Craig's group at San Jose State. Thank you very much.
Thank you, Ed. Any questions?
Just curious, what's the lifetime of the smoke in the stratosphere?
Yeah, so Mike Fromm and Pat Kablik at NRL wrote some papers on that, and they found that I want to say it was in order of 10 days. But, you know, I would have to go and look that up precisely. But I can find the reference for you. My recollection is that they were saying that the anvil persistence was about double for non-fire related stratospheric intrusion, stratospheric anvil.
Is this process more important for pyro-CBs in mid-latitudes or in the tropics?
Yeah, so to this point, we have not been able to observe this phenomenon in the tropics. In the tropics, the barrier to actually convection to smoke reaching in a dry column all the way up to the stratosphere is a very high barrier. So these phenomena we've observed a lot in Western North America, several in Russia, and as well as in Australia, and there was one in Southern Africa. But we haven't observed any within 20 degrees of the equator, because I think that would require a really exceptional circumstance of energetics.
We have time for another question. Oh, great.
Can you talk just a little bit more about the research goals of the flight this summer with NOAA? Will that be with the hurricane hunting setup?
Okay, well, for anyone who's not familiar, the FireXAQ mission is a combination of the flight component of the NOAA FireX mission that included a large laboratory component at the Missoula Fire Lab, and now this summer has a flight component measuring chemical species that will allow them to corroborate some of the findings from the lab about the composition of the smoke and the relation between fire behavior and smoke composition. Those instruments will be on NOAA aircraft as well as on the NASA DC-8. NASA will also be bringing their own instruments to look specifically at the chemistry of smoke plumes.
Great, thank you. Plug in. You want to start plugging? Yeah. Great. Okay, our next speaker is Nick McCarthy. He's currently from the sorry, is that okay? Here we go. So Nick's currently at One Concern as a wildfire analyst, data scientist, but he's wrapping up his PhD at the University of Queensland on radar observations of wildfire plumes in Australia. So Nick and I met, I don't know, 4 years ago in Australia when I was down there for my sabbatical, and he's also one of the only scientists basically chasing wildfires with remote sensing tools in a mobile fashion. And so Nick's worked with a lot of interesting groups down in Australia, and I consider him probably the foremost expert on radar and wildfire plumes. So thank you for being here, and you're going to have to speak
Directly into the mic. Got it. Thanks, Craig. And thank you so much for putting this on. I was saying to Craig beforehand that it's just so awesome to have such a diverse audience of like end users and scientists. You rarely would really get in a conference, and as well having like a community that's a bit more geographically constrained and sort of common interest there, which I know is ironic because I'm presenting all my work from Australia. But the work, as I said, is part of my PhD, which is hopefully done in a couple of months out of the University of Queensland. But I spent most of that time at the Bureau of Meteorology in Australia. And then there was a pretty large fieldwork component to my PhD that was sponsored by the Country Fire Authority, New South Wales Rural Fire Service, and Queensland Fire and Emergency Services. So these three firefighting agencies that are sort of equivalent to CAL FIRE in Australia really helped me along both with the field component and financially to get this work done. So massive thank you to them. I thought it would be useful to start off with just a very quick primer on the Australian wildfire season. None of the rest of the presentation is going to be about this, but I thought it might be a bit of an interesting insight. A lot of our critical fire weather is prefrontal. So the roaring 40s beneath Australia get a big subtropical high in between Australia and New Zealand, which I didn't indicate on this, and then that'll sit there for a while, the country will dry out, and then we'll have a big cold front rip across. And that affects most of southern Australia. Now, they've got the seasons on here, which obviously isn't very useful for you guys, but I've put the months in there just because I thought it was going to be interesting to highlight some of the changes that we're seeing in the Australian wildfire season are really around this sort of when you guys have your worst weather. So in Australia, what we're seeing in Queensland, my home state, is the wildfire season is becoming much more severe. It's usually a subtropical environment, but it's getting to be less and less like that. And then down in southern Victoria, you really shouldn't, or in the south in Victoria, you shouldn't see the wildfire season really kicking on until like January or even February. But the problem is they're losing prescribed burns and locking up lots of resources in the east of the state when they should otherwise be probably doing the prescribed burning. So there's this bit of a cruel cycle setting up. And we have a lot of exchange going on. So firefighters from Australia came out to help out with some of the North Bay fires. But that's probably going to be pretty hard as these sort of critical times overlap. Yeah, I just wanted to highlight as well, downslope winds far less common in Australia, but there's a couple of regions where we do have evidence of that, some of that sort of fire weather. Now, I just wanted to talk about what I'm going to try and do really simply. So here's the Waroona fire in Western Australia, a bit too far to drag my trailer to, but a nice illustration of the sort of high temporal frequency of these events. So a lot of the stuff we've been seeing has been on like which days do these occur on. But I suppose my research was really trying to look at, well, if we see a big column going up like this, what's actually happening inside that? How does it relate to the fire behavior? That was the objective, but what it ended up being a lot more was like, well, in this radar data, what are we actually seeing? Because I dare say a lot of you guys have seen wildfire on radar before, but it's really not clear. It's an active sensor. What are we actually bouncing off? And just in case you haven't seen that, I put this sequence of images from fire in South Australia that we can see really nicely. This is just the reflectivity field, and you can see basically the elliptical shape of the wildfire spreading out really clearly. A fine line boundary coming up and approaching the wildfire, hits it, flank blows out to a front, and that was a pretty high impact event, but just in grassland. And so in this case, the radar was shooting really low over the surface, so I was able to capture this sort of information. But the thing that's pretty clear about this as well, that it's an extremely messy image. So how do we actually extract intelligence out of this? Because it does offer a lot of value in terms of its high temporal frequency and spatial resolution that otherwise we sort of struggle with in remote sensing. So I wanted to make the case about this pyrometeor, which is actually a term that I borrowed from Adam Chokansky, introduced me to it. But this is the idea that if we look at the actual wavelengths that radar is using, it's an active sensor emitting radiation out. There's pretty much, at like the radar wavelengths that we're used to, pretty much no chance that that's actually bouncing off smoke. But rather it's this larger debris starting about the size of small ash, all the way up through to what we see on the right-hand side there, which is I was field observing back in Australia in February of this year, and this debris was falling from the sky. The fire's spotting out to 5 kilometers, and there's this family just sitting there, and there's this kid walking around picking up these firebrands, and he's sort of like, oh, that's pretty interesting. And I'm like, yeah, well, probably time to get out. But if, you know, it's an interesting scale to be using to like look at the size of this. So bringing this back to radar, it's about yay big, right, in terms of a scatterer. Now, the wavelength of the radar that I was using was 3 centimeters. The typical surveillance radars are 5 to 10 centimeters. So when you're talking about something that big, you only need one of those little bits in a very large volume of air to come up with a high reflectivity signature. So the chances are that it's much further towards this end of the scale in terms of the targets that we're bouncing off. And there's a whole bunch of different processes that are going to affect these things. Now, this goes from the type of vegetation that you're actually burning, the temperature which it's exposed to. So, you know, if you, we saw in this previous image up here, as we expose vegetation to higher and higher temperatures, you get to more towards the point where it's just the mineral structure of that leaf, let's say, left over. And so that's actually going to really determine how that little bit of material responds to the radiation you're sending to it. So there's a world in which we can actually probably tell, you know, the temperature to which different bits of bark and stuff were exposed to based on its reflectivity signature, if we can start to separate out all this sort of mess in the plume that we're seeing. Moisture is a big component there, obviously, and then the shape and then the way it falls. So if anyone's been downwind of a fire, you might have seen ash falling like snowflakes. Well, that's one of the things we can actually leverage to say, well, this is what we expect radar reflectivity to look like a fair way downwind from the plume where it's floating down slowly. But if it's going up, it's going to be tumbling all over the place. So we'd actually expect something completely different based on that. So just a few other different components that can highlight that. But this same fire back in February, I wanted to put this thing, you guys probably don't know what an Australian 5-cent coin looks like, but that's rain droplets you can see on that screen there. I'm not sure how clearly it's showing up. So the paper's actually warped from the rain droplets, and then you're seeing those bits of ash and debris in there. So this is, it's either wet deposition, so bits of bark falling through rain, or it's actually forming as the nuclei in which the rain is falling. So it's like, from the meteorology perspective, we have no idea where to start in terms of profiling how these things should look in radar. But that doesn't stop us needing to find a really good way to use this data, because during some of the massive fires in Australia in the last, you know, going back to Ash Wednesday in 1983, and even just in 2009 with the Black Saturday fires, the radar, if we just look at how the fire is escalating, just in the reflectivity, we can get a sense of how bad it's going to be. And a lot of these, I think it was mentioned earlier today about the wind component of these storms. Like if a wildfire has enough momentum and is you know, essentially a severe thunderstorm, as Ed was pointing out, on top of the fire, you're going to see all these effects. And so radar is really one of the only things that we have to do there. So we're balancing up this. It's really not very good data with, we can actually get a huge amount out of this if we try. So my field campaign in Australia was, I don't actually have a picture of it here, but you can see the little icon trailer in there. We were dragging that around and trying to make sure we weren't upwind of fires, and just scanning as frequently as we could. There's some of the, you know, little bits of information on the radar up there, but I won't get into too much of that now. This is probably the main case that I've been looking at for my PhD work, so the Mount Bolton wildfire, and just showing the isochrones through the space of about 5 hours. It hit 1,200 hectares in that time, so and under a pretty classic fire weather setup for Australia. So prefrontal, it's burning south, wind change hit, and it blows up to the east and north in terms of fire spread. And just those lines in there is where we're actually scanning to try and get cross sections through that. So it's not going to look like the normal radar data that you're used to seeing from some of these things. And just because this is such an awesome video, this is from one of the air observers that was showing during the sort of peak of this fire. It's going to cut around to the second, and we're going to see the plume pulling upwards. And what we're seeing there is spot fires that have been dropped out into the private land ahead of the fire that are then being pulled back in at 90 degrees due to the plume dynamics into where the fire is pushing forward. The chopper then goes around to the other side of the fire and shows the exact same thing happening in the opposite direction. So on both sides of the fire, you've got spotting coming ahead and then being pulled back at 90 degrees. So a really big indraft happening in there as a result of the plume. And so that was what we went and tried and quantified. So this is the perspective that we were looking at, obviously. So really pretty lucky that we were directly upwind and could just take a perfect cross section of it. That's what this data looks like. And so top to bottom, we have the reflectivity field, the height in kilometers, which I'm just going to stick with kilometers. The height in kilometers, the peak of the plume was up about 7 kilometers. And then we have a couple of these dual polarization moments from the radar. And this is the start, this is the part where I get to get really excited about this radar that Craig's got coming. And if I achieve nothing else from this presentation, I really hope you sort of grasp on how significant that will be. Because it's going to be sensitive to exactly the right spectrum of the debris that we're interested in some of these plumes. And on the right-hand side, we just have the traditional radar. So in this little loop, I'm showing the same frames that we'd get during one sort of 10-minute frame of that operational radar. So a huge amount of information in that. And I'll just quickly point out at the bottom, the blue versus the pink is the blue is the plume, and so a pretty messy signature in there. But in the row HV, which is the correlation between the two beams in a dual polarized radar, it's showing that it's perfectly round. The beams are perfectly correlated. And so that's rain, and essentially rain that's been triggered out of that wildfire plume. So I wanted to point this one out, and in terms of the way we can approach this data is actually like pretty difficult because there's all these different things and we actually don't know. We showed all those different processes, droplets forming on bits of bark and whatever. It's really tricky to separate out these different processes. So what we've used here is a machine learning approach. It's an unsupervised classification essentially. So we're basically saying if I lined up buckets along this table, across all these different dimensions, so there's 6 dimensions that we're looking at in terms of the different characteristics of the two radar beams, let's see which ones are most similar to each other. And what we see is the thing to take away from this is the purple, red, and the yellow. And so up the top, we're seeing that's pretty much just the ash that's left over. It's above the condensation light, and it's doing its own thing. But this purple layer in beneath the bottom here is really, really interesting because it's probably telling us something about the size of the debris. And what we would expect in one of these plumes is as the turbulence decreases away from where the actual fire is, you'd expect a sorting. This is what happens in hailstorms, for example. And then there's this little bits of coherent red sort of advecting along there, which I have no idea what that is. But it's a real signal that we're being told out of the radar data. So still working on that one. And then we see in the right-hand side that rain shower we were talking about. And we see a few things that we expect in there, sort of like bigger, fatter droplets towards we get the surface and a bit of attenuation in there as well. Now, if we just compare that to a data set that we took from 90 degrees to that wildfire, if you look closely, and I've just given a short section of this time lapse in here, you can actually see some of the pulsing. And so Ali earlier today talked about sort of the vortex shedding that you see behind some of these plumes. And what we figure out, well, these sort of vortex structures are probably really important for spotting. And in Australia, we get quite long distance spotting. So this particular fire was spotting out to 7 kilometers. And the bits where we see that pulsing happening in the radar is where we saw some of these spot fires occurring. So probably the most interesting thing in here is that on the left-hand side, we've got a bit of short-range spotting about to 1 kilometer. On the right-hand side, it's 7 kilometers out. And you can see that little perfect elliptical stubble grass fire happening there, and you can barely see where the fire is. So if we're trying to get intelligence about this long-distance spot fire spotting, this is probably one of the few ways we have to start picking into the actual breakdown of what this debris is. So definitely still a long way to go there. I wanted to talk about briefly as well, so this isn't a data set that we collected with the mobile radar, but just the operational radar. But looking into some of these more advanced moments of the radar beam, we can actually derive a sort of metric for turbulence. So we're looking at eddy dissipation rate on the left-hand side here. Now, if we just look down that, I want to point out something pretty important. So at the start of that, we actually see this sort of V shape in the turbulence, right? That actually makes complete sense from the perspective of plume dynamics. What you have is 2 vortices coming up like this and turning around. And so you see the most turbulence on the edge of those 2 overturning vortices coming down and out of the plume. I encourage you to look for that if you are, hopefully you're not underneath the plume of a wildfire, but if you do find yourself in that position with the time to look at it, it's worth checking out. So that was before the initiation of the pyrocumulonimbus. And then after that, we see the disappearance of that V shape. So that little V shape, we're no longer seeing a traditional sort of 2 overturning counter-rotating vortices, but rather we're seeing a lot of vertical rotation. And this isn't going to be particularly clear in this slide, but essentially the radar is measuring Doppler velocity, right? So towards and away from the radar. What we see is several vortex couplets forming in this pyrocumulonimbus. So I guess similar to the car fire, Neil Leroux found some of this stuff from the car fire, but these ones were not static over the top of the fire. They were sort of, pulsing up and then they'd move away. But that rotation is pretty contradictory to what we'd expect in the overturning V-shaped type thing, which is probably a really important clue for the initiation of these things, and I'll hopefully get to that in a sec. So anyone familiar with the context of severe thunderstorm splitting? So what happens in the early stage of a thunderstorm, it'll pulse up, and if it's going to become mature and turn into a supercell thunderstorm, that is a thunderstorm that is rotating just as one body, it basically has to split in half. Now the question is, why wouldn't this be happening in wildfire as well? Especially when we see these big initiations above this wildfire. Now, I'm not saying that I have a solution for this yet, but it's probably something that's going to be really important, because if we do see a mode of the fire where instead of two counter-rotating vortices, if one of them can become dominant and sort of spin over the top of the fire, you dramatically decrease the amount of entrainment that can happen in the environmental air. So in the last presentation we were talking about, well, is the amount of moisture from the fire significant in the initiation of the storm? Well, it may well be that this rotational effect, which can decrease the entrainment by half, can actually provide a mechanism for that to initiate, but just a theory at this point. Wanted to show quickly as well an example from a prescribed burn we went to, and linking into this stuff about the inflow you see around a rotating column. So this was, I'm going to skip forward just to show what this actually looked like. I'm not going to do the big reveal. It was a rotating column, right? And it was a 3,200 hectare prescribed burn lit in a grid ignition. So you've got a lot of convergence of fire and some sort of asymmetry set up in this fire where there wasn't a dominant synoptic forcing. So there wasn't like a clear westerly wind pushing. And so we saw that rotation happening. Now what was interesting is that, like, of course, as you'd hope, that was really quite obvious in the radar imagery. So if we look at this little white point in here, if we draw a line out towards that radar, as you're seeing towards and away from, right next to each other. So that's a really clear signature of rotation. And generally, if you are looking at radar scope and whatever, and you see that signature, that's definitely what that means. It can sometimes be mistaken with divergence, but we'll leave that from the moment. If you're seeing either of those things, it's probably not a good time. But what we did have around this fire is weather stations around the perimeter, and we're seeing even out to that, 5 kilometers across, 10 kilometers along, the convergence of the wind field just due to that rotation. I'm going to finish on this case, which is the state mine fire in New South Wales, which was one where we saw, it was probably, it's not really clear if it was download-slope windstorm to me, but it was definitely a wind-driven fire. What we're illustrating here just quickly is that if you have multiple radars around the fire or any meteorological phenomena, you can use just this towards and away from to actually resolve the 3D velocity field. So for this fire, this is 3D gridded, UVW above the top of the fire. And I'll just go ahead and show, we're not seeing significant vertical velocities in this. So, up to maybe 8 meters a second, which, I'll let Craig go into that, but that's probably not that significant in the context of a fire. But the arrangement of the updrafts and downdrafts in this fire is really what's pretty interesting. So just a demonstration of the technology there and hopefully where we can take it. If I was to leave you with some quick points about this work, radars do not see smoke unless it's a very, very fine wavelength of radar. They're not looking at smoke. It's ash, leaves, bark, and all this different debris that we see, and probably bits of soil and whatever else. The Mount Bolton fire, we showed this clustering, so like an unsupervised approach to just bucketing up this data can actually tell us what the regions of interest are within one of these plumes, and hopefully one day take us to the place where we can look at firebrand transport. The Sir Ivan fire, that was where we saw that initiation. We changed from that V mode of sort of the plume splitting up like this, and I chucked this photo in here Just to illustrate that as well, beneath this plume, you can sort of see that clear air in the middle there. That's a pretty good sign that the smoke's actually adhering to where these vortices are forming. So a nice wind-driven fire, but you have to see a breakdown of that for it to switch to this different mode. Then, there's going to be the fires as well where, there's not a dominant wind forcing to begin with, so you're just going to see rotation setting up there. And dual Doppler, I don't have any big conclusions out of that data set other than it's possible, and I think it's a really underutilized data set. So thank you so much, and hopefully you got something out of it.
Thank you, Nick. That's great. Do we have any questions for Nick regarding wildfire monitoring and radar?
With the research that everyone is doing with plumes and fire vortices and such, do you see yourself getting to the point where you could predict column collapse and those types of issues that impact operations for the guys on the ground?
Yeah, definitely. And so the Country Fire Authority funding this in Australia, we're specifically looking to see if we can do that. The tricky part is that we saw some sort of shower development which have downdraft associated with that, but what we haven't seen in an observational data set is actually like a column collapse or a fast vertical motion out of that. So from the scientific point of view, I think that we should err on the side of we'll wait till we observe this stuff, and hopefully it's under good conditions, but there's no question that that's the place we want to take it, because if we're not looking at those problems, then why are we looking at it at all?
One more question? Okay. Well, Nick will be at happy hour, so another plug. Thank you, Nick. That was fantastic. Okay, we're almost out of here. It's almost time. We've got one more. I'm going to do a short talk on some of the things that's happening that we're doing here to follow up with Nick, and then we'll do our panel. And we might even do it a little less in terms of the hour, but I want to get everybody kind of done at 4, so we have 30 minutes to kind of take a break and then head over to Duncan Hall, which is where the happy hour will be, and I should show you where that is. And one thing I need to, before I forget, at the top of the roof at Duncan Hall, it's hard to get up there. We're going to have some signs, but there's trip hazards on the roof. Lots of trip hazards because it's active monitoring. So we have a number of weather stations. We have a lot of tie downs. We've sprayed them with red paint. Okay, and I've got a picture that I can show you what it looked like so you know what to expect. Anyways, we'll get there. Okay, I'm going to try to get through my presentation really quick here so we can move on. Let's see here. Okay. Okay, so usually you don't want to be the last presenter, but this crowd, everybody's been engaged. I don't know if it was because we put the coffee at the very end and kept everybody awake, but everybody's been really engaged, so thank you. What I want to talk about today is rapid response mobile fire weather monitoring and new technologies, and I'm going to kind of end the talk with what I think we need to do for fire monitoring in the future, especially in the state of California. And so I want to highlight the RADFire campaign that we just finished last year, and I'm going to talk about the next campaign 2020 if we get funding for it. And I'll show some highlights from plume dynamics. I'm following up on what kind of Nick was talking about and Ed and some of the data sets. And then this idea of needed infrastructure for fire weather and wildfire monitoring in California. So way back when, Byram suggested the convective Froude number, which was this idea that if you had the power of the fire versus the power of the wind versus the power of the fire, if you have a real strong wind, it's driving the fire behavior. If you have less wind and more heat, that's a plume-dominated fire. Okay, so we can look at it with a cartoon saying, hey, so if no wind, we're going to have the plume kind of stand up. If we have a strong wind, the plume's going to lean over. And so understanding the difference between these two regimes is something we don't really have. We don't know. And so my goal for the last 10 years has been trying to collect field observations to better understand this relationship. And that allows us to use those data for modeling tools to look at how warfast fire performs on large fires and such. So basically, we really don't understand the dynamics of how wildfires create their own weather. We know it's heat, wind, fuel type, but when do we get one regime versus the other? And so the rapid deployments to wildfires experiment, I don't know if any of you get BAMs, but we had the cover issue. It was in December's last issue. Basically, we took our mobile atmospheric profiling system. We sampled about 22 fires in California. We also had an aircraft, which I'll talk about, and we sampled a fire in Boise, Idaho. And we're still going out. You know the project's over, but we're still deploying to fires. This is, I already showed this. So we have basically a Doppler LiDAR on here, which is like a radar, but it uses infrared lasers, so it uses light detection. And so it's more sensitive to smoke particles versus larger objects in the plume that Nick was discussing. And so here's what a LiDAR looks like. It's actually on our roof. You'll be able to go stand next to it, but don't look into it, even though it's eye safe, okay? What it gives you is it gives you velocities away from as the LiDAR points, it gives you the velocity along the beam and towards it back. So we can scan in any direction, vertically, we can do wind profiling, we can scan horizontally. And so it gives us the lower panel is backscatter intensity. This is just basically from the roof of San Jose State. And then the velocities are, you can see the strong updrafts in red and downdrafts in blue. And so we can go to a wildfire. This is the El Portal fire. And we can scan vertically through the plume, and we can actually collect highly resolved observations and get these structures of the plume. The first time we've been able to do this. And so you can see where the truck is located, and you can see the picture of the plume, and yes, those are observations. They look like model output, but they're actually, that's what the LiDAR gives us. And so we can then back out the mean velocity. This is from Leroux and Clements, 2017, Journal of Applied Meteorology and Climatology. And so over here, I'm using this mouse, I can't see it on my computer. We see indrafts. So you can see the reds are away from the LiDAR, which is at kind of over on this point. So those of you can't see it, it's over on the far left panel. So we can see the winds going into the bottom of the plume. We can see divergence aloft. And another thing that Neil did is calculated the smoke variance. So we can see what are the most the strongest mixing where it occurs at the base of the plume. And so these structures really allow us to understand plume dynamics. However, we still need other tools like X-band radar, Ka-band radar. Here's another fire. I can't remember what fire this was, the Rag fire. Carrie, were you on that one? I think that was up in Napa County or Lake County? Okay, so here's what the plume looked like at Lake County. You can see the temperature inversion where all the smoke is trapped. That's just backscatter intensity. And you can see how the plume punches up, comes back down, and that smoke that gets ejected above the inversion layer, it comes back down, but it slides across the top of the inversion, and it doesn't always come back down to the surface. So understanding these kind of structures are very important, not only for air quality, but for just better understanding plume dynamics and role in fire behavior. So we had the opportunity to take the Wyoming King Air, which is a National Science Foundation aircraft, and we had 20 hours given to us for our project, and we wanted to test the radar on it. It's a W band, which is similar to our Ka band. We use those data, and we actually use Nick's paper to justify the purchase of our radar that I spoke about earlier today. And what you see here is a deep plume going all the way up to from basically 5 kilometers deep. You can see a little pileus cloud on top. I can't see the pointer here, and people on the other side of the room won't see it, but that little layer at the top there. The most interesting thing is that the aircraft, the radar worked great. They actually ended up penetrating the plume. And actually a San Jose State grad who has finished his PhD at Colorado State, did his master's with us, was the flight scientist. He didn't wear a seatbelt, and he hit his head because the plane interacted with the plume. It was a 37 meter per second updraft, and we got a text. We're chatting in real time, and we got a text saying, "Oh yeah, I'm bleeding." I'm like, "Oh, that's, I guess, good." So they went back up and sampled the plume from aloft above the plume and measured a 130 mile an hour updraft. We believe it's probably the strongest measured updraft on the Earth, especially in a wildfire plume. So with that, we've submitted another proposal to NSF called RADFire 2. You know, we're going to do it again, but we're going to do it better. And we are going to look at similar questions, understanding plume dynamics. So my collaborators are Dave Kingsmill, Neil LaRoe at UNR, Kingsmill's at Colorado, and Adam Konchansky, who spoke earlier at Utah. And we hope to be based in Reading in 2020, and we're going to bring a suite of assets. I'll skip the science questions. So Reading's a pretty good place to be, I think, because there's a lot of fires in California. We like it because there's a lot of there are many roads. We like it because you go from grassland to shrub timber to heavy timber. So we can get a bunch of different ecosystems. Generally, they burn from one to the other, and we can probably get better line of sights for the radar. And so we are actually going to bring our own radar, the Ka band, our Doppler LiDAR, so that's 2 vehicles from San Jose State, the King Air, and 2 Dow, which are the storm chasing radars. So you see the picture of the blue truck, that's a big radar. It's a rapid scan, X-band, and another X-band. So it would be one of the largest meteorological field campaigns in wildfire science in history if we get funded. Here's the experimental plan, but let's skip that. So the cool thing about this project, and I'm biased because it's mine, is that what we want to do is we want to co-locate a high-resolution infrared camera system in the nose cone of the King Air. It's about this big. It spits out an image every second. It's geo-rectified in real time, so a flight scientist can say, oh, look at the fire. Oh, there it is. And so that information, my next part of the talk is going to be talking about how we can implement this here in California with CAL FIRE and some other assets. But here's what the system looks like, and we can monitor fire spread in real time. And we will have updraft velocity and downward and down forward dual radar, Doppler radar, so we'll get vertical wind profiles around the fire as well. These are things we've never measured, and so this is an opportunity to do this. But do we really just want to do this once every 10 years and we get a data set that we mine, publish a few papers, and it sits on a shelf or on a disk? No. This technology shouldn't be just used for researchers. This technology should be implemented in real observations and real-time monitoring. And so if we were to take a tactical aircraft, you can use these as they're flying around with this system, which is commercially available. You throw it in there. The pilot, once he turns on the aircraft, the thing powers up, starts spitting out the images to an iPhone or a supercomputer or what have you, and it's a done deal. The software is there, the technology is there, it's multi-wavelength, and it doesn't saturate over the fire. It's 5-meter resolution from 15,000 feet, so you're basically outside the TFR. And I propose that every tactical aircraft in CAL FIRE's fleet should have this already in there, and it's just, it just spits it out. Another thing, we have tankers going about 100 feet to 200 feet above the ground. Why don't we instrument those with a MET data system? This thing mounts onto the fuselage. It gives you 3-dimensional winds, temperature, RH, every second. Those data are tilt corrected for the aircraft. The system actually gives you stress and strain data of the aircraft, so it helps with loading. All the functions of aircraft management. They use this in agriculture all the time. That's this business model, is selling these to agriculture, because agriculture planes, they do drops as well, not as big. Not as critical, let's say, but they need those data, and so this stuff is commercially available. This system is less than $30,000. Yeah, I mean, it's probably $500,000 to get it mounted, but the instrumentation, So you just bolt it on, turn it on, and it spits it in real time. Yeah, I think you can use duct tape. I don't know. I think it works, but so this technology is available. I know the vendors. We've been proposing this for 10 years. We need these on suppression aircraft. Okay, finally. This is 1-second data from our truck down in Oxnard during a Santa Ana wind event. If you look at the wind speed, it's the blue line. It's 2 miles an hour, nothing. You look at the temperature, it's a cool 55. That's California surf weather, right? It's foggy. 90% humidity. You've got the marine layer there. And then within just a few minutes, you go from 90% humidity down to less than 20 and then down to single digits. This is the onset of a Santa Ana wind event. And what happens is, this is a scan from the LiDAR. You've got high velocity winds moving from a loft to the surface, bringing that dry air down and eroding the marine layer. So why don't we have a statewide network of vertical wind profilers? The state of New York has 20 Doppler LiDARs in operation right now, and I don't think they have a wildfire problem like California. They don't even have the air pollution that we have, and their Doppler LiDAR network is not working as well as it would in California. You need lots of aerosol for these things to work. They're tiny. You'll see one up on the roof. They're very small, and these new LiDARs can give you 3-meter resolution every 2 seconds up to the top of the boundary layer. I mean, that's probably too much. That's data overload, but this is the technology that's available, and we need a statewide network. So I've drawn some critical areas. You know, let's put a few here, let's put a few there. In addition to having vertical wind profiling LiDARs, what about small X-band radars? We need a network of small X-band radars as well. And so I've been working with a vendor that is building these, or designing these very small radars that you can put on top of power lines, and you can have an integrated network, plume detection immediately, potentially faster than 911, probably more high resolution than a fire alert camera. So the technology is there, we need to adapt it, and this is my soapbox, because if we look at a conceptual model of how we would do this, we'd take all these data, of course San Jose State trucks are in the picture there, we'd bring all that data together, we'd beam it through satellite, it would be in on a smartphone by the end of the the process, and so we could use the San Jose State HPC to do this. That picture, the coupled model, that's Adam Kochansky's picture that I stole from the University of Utah. So the last slide, the last thing we're also doing is we're developing a network of fire weather research field sites, basically testing new technology for an FDRS, potentially. Different ROS station technologies, there's different vendors coming out. We've got a small network. We're co-locating these ROS stations with where we're doing live fuel moisture samples. And so we're trying to build a network in Northern California for that as well. So with that, I don't want to really waste your time with summary. I just want to get on to our next thing so we can get to happy hour on time. So thank you very much for all the presenters. And let's take a 2-minute break, and then we'll get the panel set up. So if you need to run to the restroom, do that now. Oh, wow, it's 3 o'clock. I can't believe it. Everything's on time. No, let's record this. Could we record this? Hey. Sounds good. Okay, so what I wanted to do at the very end here, we can go as long as up to 4 o'clock, or we can cut a little bit earlier. It turns out that happy hour's set up at the lab already, so everything's there. But I thought that, having a kind of since it's a workshop, I thought it would be good to have a group of people that represent different agencies that have to deal with the wildfire and fire weather problem for every day, basically. And so I want to introduce our panel members, and we're going to kind of keep this out open. We're going to let them discuss a few questions, some ideas, their perception, and then we'll open up the audience. So first on the panel is Robin Heffernan, and she's the National Weather Service Fire Program Science and Dissemination Meteorologist. She came in from Boise, where she's located. She's been working with NNWS for, what was it, Robin? I can't. Most recently? Yeah, in general.
Probably, I don't know,
12 years with NWS, and so it's a real honor to have her come out here for this workshop. Thank you for attending. She also serves on several national committees, subcommittees, and teams, including the current chair position on the National Wildfire Coordinating Group's Fire Environment Committee. Next is Tom Rolinski. He was a former GAC employee for many years. He's considered probably one of California's longest fire meteorologists in the state. You've been doing it for quite some time. He's now at Southern California Edison. I consider him an expert on Santa Ana winds and fire potential index. And so thanks for coming up, Tom. Chris Waters is a division chief now with 20 years of fire service with CAL FIRE. He is currently in the Napa? Sonoma Lake Napa unit. And let's see here. He's also for 6 Type 1 CAL FIRE hand crews, CAL FIRE suppression operations, Solano, Yolo, and Colusa counties. He's worked in fire weather, fire danger, fire behavior, and is a qualified fire behavior analyst. He's also assigned to CAL FIRE Incident Management Team 3 as an operations section chief. Scott Strenfell from PG&E. Scott received his BS and MS degree here at San Jose State. He was actually my first graduate student. And after he graduated, he went to Sonoma Technology for a little bit, and then got recruited to PG&E, where he helped develop the fire weather program there for the last 9 years or so.
8 years.
8 years, excuse me. And so his research included satellite fire detection systems, particulate emissions from fires. And so, yeah, he had joined PG&E in 2011. So I thought it'd be great to have Southern California utilities, Northern California utilities, fire weather experts, CAL FIRE, and the National Weather Service and National Fire Program here represented. And so I posted 3 questions to them. I don't remember when. I don't remember what they were, but I can give you the idea of what they probably have them. But basically, I asked them to kind of comment on technology, the future of research, and how they see it going forward in terms of their committee or their agencies and where they see the future going. So I'm just going to let them kind of discuss it, open it up, and then I'll prod them if we need to, but I'm sure they have a lot of opinions. So, okay.
Who wants to start?
We got to turn these mics on too.
Yeah.
Oh, they're all on.
Well, I guess I can start from a kind of PG&E perspective and kind of give you the overview of what we're doing and the general framework and kind of where we're moving. But essentially, we have now a robust climatology across our territory, 3-kilometer resolution. We're running the same model in forecast mode, and really what it comes down to is teasing value out of that climatology. Really, what is the right fire weather indice to use? How do you couple that with fuels, energy release component, national fire danger rating system, and the ultimate combination like a fire potential index like SCE and SDG are using, and running that operationally in forecast mode to help the utility make the right decision at the right time. I mean, that's really the nuts and bolts of it. But, when you kind of look across the literature, I really enjoyed that presentation that I think it was Heather that's on SCE gave, one of Craig's students. Oh, there you are. Hi. It's looking for you. Did on the intercomparison of various, fire weather indices, because it's not very clear when you kind of, when you're in operations, you don't have a lot of time to do research because you got to take something and kind of operationalize it and keep it running, and that's half the battle, right? So having someone kind of look at that information for you and help you decide kind of what is the best fire weather indicator to use is kind of very important. And so I kind of appreciate work in that realm. There's a number of different things we're doing with fire spread modeling and using fire spread modeling in a forecast sense, but you know, essentially I don't want to take everyone's time, so I'll just kind of cut it very short and leave it there.
So let me just tag on to what Scott was talking about from a Southern California Edison utility perspective. I'm kind of the new guy here, so this is I've joined Southern California Edison in December of last year. So I've been hired on to develop a fire program for the company, and we're doing a lot of the same things that that the other utilities are doing, particularly with kind of following on the coattails of SDG&E with bringing on weather stations, high definition cameras. I think we have about 212 weather stations installed currently, and we're expected to have about 850 total installed by the end of next year. So it's quite a network that we're developing. And by the way, about that, I mean, I don't know about some of you people out there, but I'm really excited about that, because not only are we installing 850 weather stations, but SDG&E is, you guys have, I think, about 177, 180 weather stations. And then
do they have 290? No, PG&E.
And then PG.
Oh, he was saying SDG&E.
And then PG&E.
We have 290.
You have 290.
Yeah, we have 290.
Right. So, and then we have over 300 RAWs across the state of California, not to mention ASOS. And so we've got, we're going to have, you figure in another 5 years, 10 years down the road, we're going to have a tremendous amount of data that, you know, we have never seen before. And that's exciting to me as a scientist, that, you know, we're kind of data freaks, right? And we, so that's really exciting to see, and how we'll be able to use that data. And like Scott mentioned, we're, just to give you a brief update on where SCE is, we're bringing on 2 HPCC computers, computing clusters. We're going to be running WARF, NAM, the HER, and then we're going to be developing about a 40-year climatology of both weather and fuels. So we're going to be running all the NFDRS indices back to 40 years or close to it, all the weather indices or weather variables. So we're just building a tremendous data set, and I'm excited to see where that's going to go here in the future.
Okay, so from the Weather Service perspective, we're data geeks as well, and we're pretty excited about our new series of geostationary satellites and the fire detecting and monitoring equipment that's on those. So that, combined with our new polar satellite that was a new polar satellite that was also launched, is really a game changer when it comes to being able to utilize these data to improve our hazard products and services. Our most, the most common one, red flag warning. We talked about that a little bit earlier today. That is a big opportunity for us to partner with our land management agencies, our fire partners, to improve the red flag warning. Not only do we want to bring in this fire detection information to improve the hazard monitoring and our products and services, but we also want to be able to improve our services to the public side. The red flag warning program was never really intended for the public. It was intended for the fire management community. We do know, though, today it is used by the public. It's used by the media. It's used by the public. And being that it was never intended for that purpose, it doesn't quite fit the bill, if you will. And so we've had some social science studies that have been done most recently, and we're going to be taking advantage of that in a shorter time frame to improve our call to action statements in our red flag warnings and our fire weather watches. And in the longer term, be able to improve and possibly even create a new product or service to satisfy the public needs out there for this. As far as the gaps that we see going forward, when we're looking at our hazard products and services, we all know that the threat isn't the weather alone. The threat is the fire behavior that comes from the weather. And that's truly the definition of a red flag warning too, is extreme fire behavior. So when we're looking going forward at how we can improve our forecasts and our accuracy and helping our fire community and the public, we really need to be looking at behavior outputs, not weather outputs. We need to be looking at those breakpoints and then back model and see what those weather breakpoints would be that would get to those fire behavior indices. And that's the future of where we're going, and that's the future of where research can help us.
All right, so my turn. So I'm the ultimate and the end user, and I'm working in a challenging environment. I work with firemen. I'm speaking of CAL FIRE, so don't nobody else, other agencies, take offense. Firemen hate two things. Number one, they hate the way things are. And secondly, they hate change. So everything we do has to be couched in those terms, and it has to be useful, it has to be straightforward, it has to be understandable, and it has to be something that's going to have utility, out on the line. If it isn't, they'll just ignore it, move on to the next thing. They all got type A personalities or partially ADD. They move back to what they used to do, or they go into something else that's out there. So as a wildland fire agency, we're pretty much inexorably attached to NWCG, the National Association of State Foresters, and those agencies that kind of create the industry standard that we work within. And that really falls back on those fire danger, fire behavior tools that we're used to using as fire agencies as a standard across the country. So we're all kind of speaking the same language. In particular, my background is pretty heavily weighted towards NFDRS, and where NFDRS is headed, NFDRS 2016 is really exciting. Most of you may or may not know, NFDRS has never been really a fully funded program. It's funded to the level of one professional and one part-time person out of the budget. And that's Matt Jolly. So this whole thing has been done on Matt Jolly. So for the future to become what I hoped it would always be for the last 10 to 15 years, while they wrote that system in the back of the auditorium at Tucson over the last 10 years, is really to fund that program. You guys know people in decision-making authority or in somewhere where this stuff gets paid for, is to stress that. There are places where there's a lot of money being pushed into tools that are used after the fire started. I want the tools that we use before the fire is started to be funded properly so that we can get the most out of this new system, because there are some exciting times coming. We're right at the precipice of a major change in the way we do business. And how that's going to translate back to our agency, we have a fairly extensive fire danger, fire weather network, RAWS networks. We work with our partners. And we're heavily invested in fire danger, the National Fire Danger Rating System. We were part of the initial inception of the program, and that's policy in our agency, and we're going to utilize it. Being able to apply these tools for decision support at every level of the organization, from the top down to the ground, the dirt firefighter, the guy swinging the tool, there's a whole suite of tools within that system that we utilize to make decisions. And I see us moving forward with trying to improve that. Now, we're coming on the heels of a fairly significant fire season and election with a governor that is obsessed with data. I don't know how a restaurateur, mayor of San Francisco, gets so obsessed with data, but thank God he is, because now there may be an interest to help fund some more, depth in our organization, because in our organization we have one person as well. It's Jana Lewis, and she's going to retire on Tuesday. So there's a lot of opportunities. We got the need. We've demonstrated that from last year. I'm hoping that our department moves forward with some additional funding to make those programs work. I've been ordered to not promise anything. So I'm not promising anything, but I'm hoping it works out. And one cautionary statement to everybody here. If you read any of our accident investigations, or you read any of the FLAs, or the things that we look at when we are doing investigations of folks that are hurt or killed on fires, there's one line, and usually every one of them, it's about communication. So we hear a lot of really exciting work going on, a lot of good tools, a lot of cool stuff going on. But I want everybody to remember, humans are humans, and we've spent the last 60 to 70 years trying to teach people a certain terminology, lingo, accepted standards, and those things that we talk about, burning indexes, the way that we We look at spread rate and all the tools that we have out there is to try to stay as consistent with that terminology and that lingo, because we know communication and being able to speak the same language and making sure folks on the line, especially that firefighter, that company officer that's responsible at the engine or the crew level, truly understand exactly what they're getting into or what they're about to face and all those elements that are going to make their job safer. Because that's really what we're here for, is to make it safer for those folks. Ta-da!
Great. That was fantastic. Let's see here. How are we doing on time? We got plenty of time. How about, so with that said, is everybody here, I mean, are we all on board of getting new technology in the hands of firefighters and for fire management? I mean, it seems like a lot of this stuff is pie in the sky that we've presented. You know, we need this new technology and stuff. But what about these state-of-the-science models, these tools? I mean, the coupled fire atmosphere modeling systems, the new NFDRS. This stuff could be generated, my opinion is that this stuff could be generated at an academic center or some other HPC, and that data can then be, those data can be streamed to fire agencies in real time and useful in that regard. That way, agencies don't have to take that on. It could be done at different institutions. So do you think this pie-in-the-sky technology is really, not what we have now, but kind of this further modeling capability, higher resolution? I mean, I don't think we're going to need another surface station. In 5 years, I don't think you're ever going to be able to get funding for another surface weather station. I mean, we have how many surface weather stations between the three utilities? Probably, what, 3,000? 2,300? Oh, yeah, okay. The person who installs them knows exactly the number. 2,300 plus all the other stations. That's pretty awesome. And what I see as a point is that we're not going to be able to blame. Well, gosh, it's complex terrain. It's a canyon. We didn't know what the wind was doing in that canyon, because we'll have a weather station on every utility pole out there, basically. So, any comments from the audience right now? Good. Yes, Joaquin, I expected you to make some comments and ask some questions. Yeah, oh, here you go. Stand up here. Come on up.
Yeah, thank you. My feeling as a technologist is that definitely what we have seen here, I mean, the amount of people that is here right now in San Jose in this fantastic fire weather lab that you guys have been working the last years, this is really amazing. This is the most important thing that is happening in the last years in regarding data and science and all of that. The community that is growing, because the data, computer power, cameras, technology, and all of that, that is there. Now it's becoming more and more cheaper. For me, the biggest challenge that we have is how to make Chris' lives easier. Because more is not because we can, doesn't mean we should. We really need to help them to do the change in their organizations, try to empower them with the right training, with the right people. I mean, Chief Porter was asking for more people on the field, but also more people at the intel level in this organization that really can help to get the benefits that all this science and all this modeling, all this observation is providing us. Because if we don't get that, in the end, the next new fire, the people will be doing the operation probably the same way. So we need to empower those intel units, the planning units, the situation units, but not only during the incident. It has to be done the whole year. This is a full year job. We really can understand way better now California fire history, because now we are going to have the weather, the reanalysis weather, that can explain that complex problem. Hopefully we'll have the fuels data that help us understand that problem. And hopefully we'll have the data from the population, even from the traffic and the evacuation, all of that to try to understand that this landscape is going to have fire, it's going to keep on having fire. It's not going to be a question of having more engines or having a bigger airplane. We have to live with fire, and to do that, we have to understand it. And to do that, we need this data, this science, and train people on this to help that, to do that transition, because it's going to be a transition. We're going to there's not going to be a senator's Dodge bill that is going to, boom, put a new center where all of a sudden the technology is going to change the way the things are faced. It's not. Anyways.
I'm going to weigh in just for just a minute on, I think, what Craig mentioned a minute ago and what Joaquin just talked about. But one of the major gaps that I see in, I guess, technology and just in data is our fuels, right? I mean, we've been struggling with trying to measure fuel moisture, trying to measure fuel loading, trying to measure, all the different aspects of fuel conditions. And that still remains a great challenge for us. And, yes, we're making great strides in our fire modeling, but, that's all dependent on having the most accurate weather information and the most accurate fuels information. And that's an area, the fuels, is where we're really struggling with. And I think, there's still not great methods. I mean, you look at live fuel moisture, we're still going out to the field and sampling that. It's difficult to get our, to get our minds wrapped around that in terms of assessing live fuel moisture. And we're still stuck on the 60% deal, right, with live fuel moisture. I mean, there's a lot more research that needs to be done and relating that to wildfire activity. So anyway, that's where I see a major gap in our kind of in our tech in our data is with fuel data.
Oh, sorry. Yeah, I was just going to chime in on that. So, yeah, one thing we do is we pull information from the National Fuel Moisture Database, live fuel moistures, so they're clipped out there, like Tom mentioned, in the field. And as of this morning, if you go on the website, you can only find about 8 sites in California that have been sampled and uploaded to the National Fuel Moisture Database. And so when you have a fire danger model that incorporates live fuel moisture and you're only trying to validate on 8 sites, it becomes a very difficult problem. And so I think there's some simple things that we can do to improve the inputs to some of the modeling that we have going on. Another thing that I think is maybe an easier win that's not so technological is improving our fire occurrence data sets that are publicly available. So, and not to call any names out, but there are some. And he's sitting right here. No. It's not Chris. It's not Chris's fault. No, but having a fire occurrence data set that actually has the acreage burned on each day and maybe some sort of qualifiers if if there's a significant backfiring operation, et cetera, would be some useful information, because we're trying to use our 30-year climatology and 30-year history of fuels, live fuels, and FDRS components, and then correlate that to the fire occurrence. But then it gets difficult if you only have one record, for instance, the Soberanes fire, which burned for 2-3 weeks, and it ended up being over 200,000 acres. But the actual fire danger conditions when it first started weren't all that extreme. And so you have to kind of go through the fine-tooth comb through the fire occurrence data set if you're trying to do any analysis and really kind of tease some of those outliers out. And anyway, I would just suggest that as being a quick win, because the better the quality information you have going in, of course, the better quality information you have going out of any process or model.
So I want to re-emphasize the fire occurrence data thing. That's a huge challenge. Not only is every state in the union different, the feds are different. We're all different. We got federal agencies that are different. So fire occurrence data is only as good as how it's collected on the ground, and it's a fire report. It's entered into a database nationally or at the state level. It's wrought with problems. And another good point to bring up is that fire started on a certain day. That may not be the big fire day. It may be 2 or 3 days in. And bringing remote sensing to bear to actually do some detection work and validate some of these larger fires in particular, because those are the kinds of days we're really looking for. When did that fire get up and move? The other thing is the grid weather and getting gridded products. And it's out there already, but something we can take Fire Family Plus and use it in the cloud, grab the fire weather or the fire data, grab the climatology, and do our analysis using the same tools, using the same data sets, so we have consistency in our analysis, so we're all kind of looking at the same thing. If you look at fire danger operating plans across the country, they're all done a little different. You know, when you go to the advanced NFDRS class, you learn the art and science of fire danger, and really it needs to get a little closer to science and a little less art. Now, we never want to exclude the operational involvement, because the minute you go back home to your home unit where you're fighting fire, and they find out that you're building a plan that's going to drive all their activity, they're going to laugh you out of the room because they didn't have any involvement. But we do need to make sure that we try to get as much consistent data as possible so we can get real strong correlation and set thresholds and start doing some real strong decision support. Not that we're not doing that, but it sure be a lot nicer if we could refine it.
Yeah, Chris, I just wanted to add that the gridded piece of it is really, really important. And if I was to state one goal that we had as the NWCG Fire Environment Committee, it would be to go gridded with fire danger products and services going forward. And it's not that technology's not there, it's not that data's not there, it's that the money's not there in order to approve our federal systems. And so it is a big goal of ours, and we're moving there as quickly as we can.
Any reporters in here? You get that? Did you get that? All right.
That's great.
Yeah, I think there's been some really, really great discussions, and I think we're sort of at the cusp of a brave new world here. I think it's arguable that 10 years ago, the entire community wouldn't understand how acute fire weather was, and the intricacies of understanding fire weather is on fire potential and fire risk. And through circumstance, maybe some of that has become much more obvious to us, and we're making investments in it. I just like to reiterate a couple of things that I've heard. Heather's comment about fire behavior as a measure relative to understanding the importance of fire weather. Let's not forget ignition is a component of fire weather. You can have conditions that lead to potential massive rates of spread, but if you don't have an ignition and you can manage those ignitions, that's a really sound risk reduction strategy, right? The other thing I'd like to emphasize is our model development is really increasing exponentially. You guys have seen some of the amazing science that's being put to bear on understanding these complex physical environmental systems. I want to reiterate Craig's plea with regard to instrumentation for validation of models. The current suite of models produces really sexy and presumably remarkably accurate and precise outputs. Those of us that build and work with these models usually are going, don't overread into this. You know, it's a computer-based process. So the information like having the IR scanners in air attack, so we actually can understand fine scale space-time fire progression. It's really important because we can produce those with our models, and the public basically thinks those models are super accurate and precise. Those of us that use the models know they're not. We calibrate them with the known points of position and time that we have. But that's really currently very, very limited. Or it's coarse, like, you know, basically like with MODIS. So, you know, again, just emphasizing, I think we're at the cusp of a brave new world. There's a tremendous opportunity here to bring technology and management to bear on what's everybody agrees is just an ever-expanding kind of fire problem. Fire is becoming more abundant, and the impacts of those fires are becoming more costly and more, you know, almost surreal, really. You know, it used to be in my career, I was really like kind of concerned about wildland-urban interface and house loss. Is this metric? And is there a trend? And talking to national people basically making the claim that, no, there's no trend. Well, that kind of flipped a little bit last year with fatalities, right? Suddenly there's an entire really threatening new shadow or specter of risk out there related to public safety. When you got a fire impinging on a rural town and it basically just being subsumed. So I think that's the nature of the challenge that we've got. And a lot of the opportunity that this group's really brought together is focusing us into a place where we need to go. And I guess to reiterate Chris's statement, you got that because it's going to take some money. Thanks.
No, we can spend it.
So, Chief, question for you as a I'm here in San Jose. Keeping it simple, are we close to a point where someone in the EOC, someone at incident support can get on a mobile platform or a desktop platform and have a shared one-screen platform for evacuation zones where the fire potentially is going with, by inserting an ignition point or an estimated perimeter, you can tell where the fire is going to go potentially in 6 hours to 2 hours, and then also incorporate these evacuation zones if this GIS layer is embedded into it? Because the question is based on, I know that there's Scout, there's other initiatives going on, there's so much information, and for us as a fire agency, just kind of an end state consumer, that decision you're talking about, we're just trying to find that lane to be in, and is it really wait for the development? Are we close, or is it just, are we back to the money thing and we don't know when it's going to be really available as an end product for us?
So there's folks working on stuff like that, but I want to put a scenario together for you, and I'll use, I wasn't at the campfire, but I know a lot of people that were. We're not pulling up the terminal and typing in, where's that fire going to go, and how are we going to get rid of it, how are we going to get these people out of here, how are we going to deal with this situation? You know, the folks that actually initiated that work used pre-planning, they used the local efforts, they'd spent a lot of time talking about it. We've been talking about a fire in Paradise for 100 years. I don't think anybody ever expected that, but that's always been in the back of people's minds. Local evacuation planning and those local risk assessments are getting done. I know there's work on some tools. I've been hearing rumors. There's efforts to bring all this data together, but when you're trying to deal with something like that, there ain't a whole lot of time to go digging around through a computer to deal with that. Now, the AirTac helps out. You have some other resources there. If you're on the ground, actually boots on the ground, all those evacuations had to occur within, a couple hours. That's not much time. So it's about pre-planning. It's about analysis beforehand, risk assessments, pre-attack plans, community education, and all that stuff. Those tools are going to be great. And I know they've tried, what was it called, Scout? Any OES people in here? Yeah. You know, we've used that. We do use it. You'll snap a perimeter for evacuations, but usually that's past that most critical point. That critical point is that right now, let's get people moving and save lives and property as quickly as we can. The plan need the next day or a couple days out, that's when we start pulling up Scout and some other tools. But Scout is the only one that I know where they've actually tried to bring all of those data layers together and make them available. And there's some other tools that are being created to do fire spread modeling too in real time, but that's what I know. You got something to say about that, Joaquin?
Oh, yeah. Yeah, I mean, that is done, that is in the market. We did it for SDG&E, now we're building for the rest of the utilities. There's some interest in the state to do something like that, but I absolutely agree with him. I mean, the power of the modeling is not that it's going to tell you exactly what's going on, because there are limitations in the input data and all of that. But the modeling is good enough to make a community ready, or to do a good evacuation plan, or to do some kind of analysis to tell you, for example, that you shouldn't do a development here. Or, okay, you decide to live here, well, you better be ready. You have a fire 10 miles from here, but because maybe it will be in 3 hours in your town. We have a paper on the task fire, and the inverse modeling on Santa Rosa really was telling you what happened in the past, that you can be ready for that. Because then when the incident happens, it's going to be sexy to have the simulation, yes, and we can do it, but that is not the power of the modeling that we have right now is to be ready in advance, and that is there. Yeah.
Thank you. Sean Weigel, National Weather Service. As an IMET, a lot of times out in the field, I'll give a briefing or whatever, and then afterwards, as I kind of roam around to people, nowadays there's so many apps available with weather information. People say, well, you're saying 70 degrees, but this says 65 degrees, and I really like this app. But building on what Dave and Joaquin were saying, how do we, there's just so much great information coming out. We're really at the precipice of a major change here. But how do we kind of make sure that we don't misinform people by having all these sexy graphics and stuff like that look, like they're really detailed and accurate? How do we prevent a situation where the public is going to look at this stuff and say, well, it's obvious the fire is going to come right at me, and then they go and tell all their neighbors and everything like that. But of course, people who have experience, might know better. So I guess kind of half comment, half question. It's just like, how do we take advantage of the benefits of the development that we've done, but also sort of make sure it doesn't get out of hand in terms of public information?
I think Chris mentioned this before, but we have to have a consistent message, right? And he was referring to NFDRS and using a lot of the same terms. But yeah, there's so much information out there. There's going to be there's so much research that's being done, and when this finally does make it to operations and it's applied, we have to have the same message, right? We need to convey. We don't want to be confusing to the public. We don't want to lead people astray. So that's a really important point.
I was just going to say coordination is getting increasingly challenging. All this data are publicly available. They're on public websites. Anybody can go look at it. Whether they're educated at what they're looking at or they're not, it's available. And so what we need to do as a responsible community is to stay coordinated the best we can on our messaging, like Tom said. And when we build new tools, figure out how to incorporate them into traditional systems, meaning don't rebuild the fire danger rating system, improve the fire danger rating system. If we have new behavior models, improve the system that everybody's using with fire behavior modeling so that we can stay on the same page, but we still take advantage of all the technological advances that are going on out there and all the new research initiatives.
Hi, I'm not here necessarily to talk about the work we're doing at One Concern, but it is, what I will say is it is really heavily focused around this question of where the people are and how does the evacuation work. Hopefully in the next little while we'll be talking much more about that. But I did want to compare a scenario to my experience in Australia where we have thermal infrared line scanning that happens over the top of the fires. And so that'll happen maybe like once a day here in Australia, like assuming there aren't too many fires in a state, they'll be running it back and forth over the fire that whole time. So you're getting like 8, 12 perimeters out of a really fast, hard-running fire. There's still a massive amount of problems with that. That asset and shouldn't think it is being recorded, but like it's viewed in the field as the state office. It'd be like saying it's the Reading spy plane, right? Like so the people on the ground, there's a big disconnect between, even when that information becomes available, there's like, what the fire's doing, what the public's doing, and what the fire agency are doing. And even with all this technology, it's not necessarily as simple as just having that silver bullet to go and answer that question. And so I guess my question would be more about like within the state agencies and different partners that are supporting, how effective is the sort of central command versus the distribution to the field and that information, and is there demand across all those levels for that information?
All right, so more is better. If we could get more, and I have an experience in mind that I would give anything to have what you had or what you're using down there. Y'all remember the Witch and the Wajito fires? You probably heard that, the two fires that merged, and how nice it would have been to know maybe every couple hours where that perimeter was at any given time, because there was about $6 or $7 billion out on a hook for losses related to that fire. For intel, for folks, and we work really close with our law enforcement partners because that's where the responsibility for evacuations lie, and they're not the experts. So we're there as the technical advisors to them to make this stuff happen. And it would be nice to support them and to support the community and the safety. If we could get information like that in real time and be able to make educated guesses more efficiently, because it's bad enough to be evacuated because you have to, but if you evacuate 1 million people and you didn't need to, the amount of trouble that it takes to get those people back home is really, really challenging. You think suppression's hard. Getting folks repopulated back to their communities can almost be as hard. So really trying to get our evacuations dialed in, because when you have some of the images you show, these big pyrocumulus wind-driven fires, not really wind-driven fires, fuel-driven fires, where you have really rapidly moving wind-driven fires, you can't see. Nobody really knows what's going on. And if you ever try to listen to the radio or try to talk on it, I shut it off sometimes. It just becomes overwhelming. So having that buffer where you have some information there that you know that you can count on, and you can ignore, or not totally ignore, but you can partially, filter out some of that stuff that's on the radio, because most times it's chaotic. I mean, there's no question about it. It's chaotic. Even for people who are seasoned, it's chaotic.
Okay, let's. We have time for basically one more comment. Let's. I think it was Charles.
So my question is relative to forecasts from a forecast point of view. There is of course, all the system, the infrastructure uses forecasts out to 7 days or so on. However, there is a very large research effort to explore predictability beyond 10 days, and in many other areas. And because there is evidence that under certain conditions, the atmosphere is predictable to some extent beyond 10 days. So if it was possible to develop probabilistic forecasts that are skillful beyond 10 days, how the energy, the electric companies, and also the state and federal agencies could explore, more information beyond the next 3 days or so on, in terms of preparedness and management.
Yeah, I'll take a first stab at that. Absolutely. If you could provide a forecast that adds skill at that kind of, that zone 10 days and beyond out, I think that would be very useful from a utility standpoint. For example, there's multiple different avenues. So Pacific Gas and Electric, I think SCE has some hydropower, right? But we have 99 reservoirs that we're managing. And so if we knew that we had, let's say, a high probability of an atmospheric river event that was going to occur, and let's say, we had a tremendous amount of snowpack and reservoirs are already full, we could potentially use that information, this is just a hypothetical, right, to start releasing water to begin preparing for that event if the probability was high enough. And so that's just one example out of many that I can think of if we had useful forecasts in that time frame.
Yeah, and I would also add that not only going out to, say, 15 days or something like that, but one of the things in my previous job with predictive services is we were putting out seasonal outlooks, and those are difficult to put together. Very, very challenging. And I think, again, there's a lot of room for improvement there because for utility, knowing what's going to happen 6 months ahead is extremely useful in terms of planning purposes and being proactive with, with the upcoming fire season and how to prepare for that. And there's also been a lot of talk, obviously there's a lot of talk about, our climate models, and we're looking out 30, 40, 50 years from now. But what about 5 years from now or 10 years from now? Those kinds of forecasts have sort of been overlooked. And I think it's important to maybe visit those time frames because they are very important for utilities in terms of looking at acid hardening or any kind of repair work, and prioritizing that is extremely important to us.
Great. Ken, did you say you had? Yeah, I got it. Real quick.
Yeah. And then Ed. Yeah, I'm a boundary layer meteorologist, so I'm here and I'm not part of the fire weather type thing, but I've just got some comments. One is, it's obvious from today, and it's been obvious to me for 35 years, that the upper air is really important when you're out fighting fires. You're in a tactical war when you're out there. And you've got all the surface stations, but do you have the ability to put on site or in the command center some sort of upper air measurements that you can use to guide your decision process? I think that would be really important, and it's been very clear that when we have these marine type inversions, the subsidence inversions that we have along the coast here, and they are prominent. I've seen them since I worked at Vandenberg Air Force back in the 80s. Those are characteristic inversions. Maybe they're not all subsidence, but they sure look like it to me in a lot of ways. But it seemed to me that if you could put somebody out on the line and integrate them into the command center, it would be useful. Now, let me give you an example. In the late 90s, we had a contract with the California Forest Service to provide upper air measurements to them. And we would roll out our SODAR system, and we had a trouble getting it into the field because, well, first off, when you're fighting a fire, you want a bulldozer more than you want to put a SODAR out there, because if you don't understand the mechanisms of what's going on, you don't understand the value of it. And it took us a lot of effort to do it, to get it out there. But when we did, we had an incident in a fire in Santa Barbara where we were able to tell the command center that they had an upper level jet that was now coming down and was going to increase the wind speeds. This was early in the morning. You have your nocturnal jet that builds up, stable atmosphere underneath it, so you have no wind. All of your raw stations are going to do nothing at that point. You need to know what's going on up there, and you need to see how it's eroding. This is wind shear erosion of the jet, and that's going to come down. And when that comes down, some of your firefighters out there who you want to protect are all of a sudden going to find themselves in very strong wind conditions. Now, I don't know what that does, but I know when I'm at home and I get strong wind conditions and I've got a little fire in I'm cooking something in the back, it causes a problem. So I'm sure it does for you. So it seems to me you need to kind of take a paradigm shift here and maybe get Craig's group or some other group, or maybe even, or maybe even, maybe even the power companies themselves need to put together a tactical team that in these situations is ready to deploy and to be out there and to help in the process. It may not help every time, but if it helps 50% of the time, it's a win. You know what I mean? So that's my comment.
Thank you, Ken. I didn't plant him. He flew up on his own dime.
Just really quickly, so along those lines, obviously Craig has been pushing for upper air observations for quite some time, and he assisted the National Weather Service in looking into upper air equipment. So now all of our incident meteorologists are sent out to incidents with upper air equipment. Obviously, they're not continual observations. That would be ideal, but it's much better than not having any, or pipe balls, which is what we had in the past. So.
That's right. Okay, final comment.
All right. While we make California more resilient to fire, there's a lot of interest in developing fuel breaks. A lot of political interest, a lot of dollars, and so forth. And there's, I think, an expectation on the part of the public that these fuel breaks are going to be what they need to save them. Right now, we're designing those with our shoulder-mounted computers, which may not be the high-performance type, but are there any models, empirical models, that could be used to help validate, substantiate the effectiveness of fuel breaks? And it probably pertains to transmission line corridors as well.
Yeah, I can start there, but the one way I would approach that problem is with the historical climatology of weather and fuels, and then you model, fires over that historical climatology, and then with the fuel models, you start to introduce fuel breaks to determine and see if there's any efficacy and what the efficacy is of developing a fuel break in a certain area. So maybe you have, a Diablo wind event or an offshore wind event, and if you put a fuel break, north of a vulnerable community, maybe that would be enough to, protect that community. Hopefully it would. But that's something that you could do with acclimatology.
Be able to say that this field break is good up to a 10-mile-an-hour wind or a 20 or something.
Yeah, I believe. Yeah, you could absolutely test that.
So what he said.
So I'll just close it up with when I was working in Amador, El Dorado, you work a lot of shaded field breaks along major roadways just to provide ingress and egress, access for fire equipment, and a place to park when you need to work. A lot of communities were resistant to that. So the short-term, long-term, and whatever the heck they're calling them now, fire spread tools, is it WFDS now? Yeah, WFDS. So the WFDS tools, and use that as a tool to sell the field break to the community, because oftentimes you get resistance first from the community. And that's the one tool that I have used is you can morph that around to create nice, really cool oohs and ahs for PowerPoint presentations to get folks to buy into it. And that's about as far as I've taken it, at least now. I know the Forest Service does some spatial stuff with their field break projects. They grow fire through it and figure out where to put them and do all that kind of stuff. So that stuff is out there. It's just a matter of trying to apply it to your specific needs.
Thank you. I thought that was great. I think we had a great panel here. I want to thank our panel. We have 2 minutes before 4 o'clock. We're actually on time, but we have to do our drawing for the Fire Weather Lab swag. So I'm going to introduce Taylor Adele, who's... you got a ticket over there?
It's by my
You're free to leave. You're released from the panel.
If he finds it, it's his.
You can stay up here. And then we're going to do this real quick. So Taylor was operating the desk, so she's a first-year grad student with us. She came from Louisiana. She likes these hot days. So shake it up, pick a number, and we will call it. So this one is going to go for the hat. We're doing the hat first. This is a Sims fly fishing hat with our custom logo. It says, "Forget the forecast" in there. Because, the Sims equipment's great. It keeps you dry. That's not really the message we want to say, but, whatever. It's a great hat. Uh-oh. Who threw those in? Uh-oh. Uh-oh. Just pick it. 169019. Boom. Okay, the hoodie. It's extra small. Just kidding. We have all the sizes, so whatever size it does fit you, you get it. Of course, you are going to be, selling our logo here. So, okay, this is the hoodie. What number do we got?
169051.
No, say it again. No, that one. Last two numbers, just
Oh, the last two numbers.
51.
No. Keep going.
Nobody had it? Nobody had 5-1?
5-2?
What about 6-1?
061?
Right.
There's only like 3 numbers in the whole thing, but
69. 069.
so that's it for the workshop. I really want to thank everyone for making it a great day. I know it was a tight schedule. I want to thank our speakers for being on time and giving excellent presentations on different topics. I want to thank the audience for being so engaged. And those of you that want to stay for the 4:30 to 5:30 reception, it's across campus. It is called Duncan Hall. It's a tall building on the southwest corner. There's a couple of anemometer towers on there. We're going to try to meet there at 4:30. So how many of you are planning on going? 1, 2, 3. We got 100 beers. Dave Saps is supposed to bring a keg. We heard. Okay, so I know I should have, but Again, how you're going to get there is you're going to go to Duncan Hall. You're going to get your way to Duncan Hall. There's a huge construction site. So you got to walk around. Once you see a construction site with the big green fences, you're going to walk around it, and you're going to get in Duncan Hall. You're going to go to the 6th floor. Then you're going to find a tiny door, and that door has arrows. That goes up 2 flights of stairs to the lab and to the roof, but we're going to have the drinks in the lab. There will be some signs in the hallway to get up there. If you need a tour guide, I can help you get there, but I'll be walking around. So you're just going to walk south and walk west, and you'll find Duncan Hall. And we'll be there till closing time. So thanks again for everyone coming, and we're going to post the video online. I'll post the speaker bios online. Natalie's was not on the sheet, so I apologize, but everything will be online, and the presentations will be online. I'll check with all the speakers. So again, thanks again for everyone coming today.